From being a beginner at programming to being a coding enthusiast, you would have definitely encountered the term data structures and algorithms. These concepts act as a oil to programming, whether it's any programming language. Its application from operating system to compiler design, artificial intelligence to computer graphics, and mobile app development to networking. Data structure helps store and organize data efficiently everywhere. Being an expert in different data structures like stack, queue, linked list, trees, and graphs would help crack any interview and write an optimized code that can benefit any organization. So, if you want to excel in this highly demanded and basic concept of algorithms and learn the implementation of various operations that can be carried out on different data structures, in that case, you are in the right place. In this session, we will look into the various facets of algorithm that could help you set sail for developing and improving your coding skills. So please put on your learning glasses and join me for a great learning experience. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you don't miss out any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. As it said, knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I will definitely respond to your comments. Hello everyone. Welcome to this course on data structures and algorithms in Java. So let's see what we are going to discuss in this course. That is, we'll be talking about all the concepts that are related to data structures and algorithms using Java programming. The different types of data structure, that is arrays, stack, queue, linked list, binary tree, binary search tree, graph, and hash tables. All these will be discussed, not just their basic concepts, but also the implementation of the different methods or different actions, operations you can perform using these data structures will be talked about in Java programming. The advantages, disadvantages, as well as the time and space complexity of different operations that are done on these data structures will be discussed. Then we'll talk about the algorithmic aspects of data structure. That is, how do we calculate the time and space complexity? That is, how we do the algorithmic analysis of any given code will be discussed. Along with that, the different searching and sorting techniques will be talked about. Divide and conquer programming approach, greedy programming approach, as well as the dynamic programming approach for writing any algorithm or for writing any solution to a problem or a computation will be discussed in this course.
Now let's talk about what is data structure and why do we need data structures. So as you can see, this word data and structure is made up of two words, data and structure. So data is nothing but the information that you want to store in a computer. And structure is how you arrange your data in the computers. Now, depending upon these two factors, right, data and structure, that means how you arrange your data in your computers, you can easily calculate time complexity of your problem. And you can also see, are you using any extra memory depending upon the structure that you're using. Now, if you talk about, let me give you an example of one of the data structures, right, and compare it with another. Now, if you talk about arrays, right, it's a data structure, and the way you arrange your data is different from how you store your data when you talk about linked list. In arrays, you have to always store data in a contiguous memory allocations, wherein if you talk about linked list, if chunks of memory are available here and there, you can use those chunks of memory to store the elements in the form of linked list, or you can use linked list at that point. But if 4 bytes are there, 4 bytes are here, and there are different places, still you can use linked list, but that is not the case in arrays. You need contiguous memory allocation. Now, in both of these data structures, one of them is using CPU much more efficiently. It is using the memory much more efficiently, right? So this is one of the basic difference between the data structure between data structures, right? There are n number of data structures available, and different data structures are used for different applications, right? Now, depending upon these factors, right, how you are storing your data in the memory, you can easily calculate what the efficiency of your algorithm, how efficiently you are implementing your algorithm, how efficiently you are doing operations, right? Are you doing operations which are costly, or are you doing operations which takes constant amount of time, right? Are you using your memory efficiently? Are you using your CPU utilization efficiently? Are you using your CPU efficiently? Are you using your memory efficiently? So all these things can be easily deduced from what data structure you are using. So this is the importance of data structures. Now let's talk about, in the next slide, let's talk about what different data structures. Are there any different types of data structures? Yes, there are two different types of data structures. One is a linear data structure and another is a non-linear data structure. Now let's talk about linear data structure. So linear data structures allows us to store data in a sequential manner, like one after the another. Let's talk about this example wherein we are using arrays. It is a linear data structures where one element, let's suppose this is 5, 6, 7, 8, and 9, and one element is stored, and it is stored after the next element, and next element is stored after the next element. So it is stored, all the elements are stored in a sequential manner. Let's suppose this is the address of the memory. Obviously this will be a hexadecimal number. For simplicity, I'm taking this number as an integer number. Then the next memory available memory location is 104, then 108, then 112. Okay, so these are the available memory locations, and all the data is arranged in a sequential manner. And every element has two neighbors, right? If you talk about this element, right, it has two neighbors, the left neighbor and the right neighbor. And there are always predefined extremes. Like if you talk about array, there will be a starting index and there will be an ending index. So this is always the case when you talk about linear data structures. So in let's talk about another data structure that is there, that which is known as linked list, right? Again, it will have a predefined extreme, right? It will have a starting node that is known as the head node, and it will have the tail node, which is used to keep the track of the endpoint. So now let's talk about different types of data structures, right? That is linear data structures, right? The first one is the array, which is obviously the linear data structures, and all the elements are stored in a linear fashion. Now, this in this data structures, we can store data in a contiguous memory allocation. That means one after the other. In memory, if wherein you have the scenario where all the memory is occupied and you have chunks of memory. Let's suppose you require 4, 4, 4, and you require, let's suppose you require 4 5s are 20, right? So 20 bytes of memory are required. So you have 8 bytes here and you have 12 bytes here. Can you store the array inside these memory locations, right? Let's suppose you are storing 2 elements here and 3 elements here. Can you do it? No, because array require contiguous memory allocation. You cannot store it. Now, what was the drawback? That obviously you cannot store in a contiguous memory allocation. So that is wherein linked list come into picture. Obviously, with array you have a fixed size, right? That is not the case in linked list. The size is variable. That means we have a dynamic size in linked list. Now, if you talk about linked list, if same elements need to be stored in the memory, like these 20 bytes of memory are available, right? 8 bytes are available here and 12 bytes are available here. We can store elements in the linked list, right? So it does not require contiguous memory allocation, right? That was the drawback in linked list. Now stack, if you talk about stack, it follows a principle of what? LIFO, last in, first out. If you have a stack of plates, right? This is an example of stack. Now you have a stack of plates, one piled up over the other. Now, if you want to add an element in the stack, or if you want to remove an element in the stack, you cannot remove any of these elements unless and until you have removed the top, and then one by one you can go down removing one by one these elements, right? Now similarly, you cannot add anywhere, you cannot add here an element because that is not possible. It follows a structure wherein last in is the first out. Let's suppose you want to insert it, you are inserting it here. Now this is the last element that was inserted. Now this will be the first element that is out. Okay, so it follows the principle of LIFO. Now this has restricted how we insert and delete our elements, right? This is the restriction that is there. So this is your stack. Okay, now if you talk about queue, it works in a different manner. Now if you have a queue, let's suppose you are there in a bus station and you want to get tickets, so you are standing in a queue, right? And the person that comes after you will stand behind you. Let's suppose this is me, and the person that comes after me will stand behind me. You will not go in front of the queue. That is not possible, right? Now, and once this person gets his tickets, this will be removed. Now, this one will be the first person. Again, this will be removed. This will be the first person, and so on. So there are two pointers that will keep track of the extremes: the front part and the rear part. Now, from the front end, always deletion take place. It's also known as an enqueue operation. We'll talk about these operations later on this course. Okay. So now the deletion will take place from the front and insertion will take place from the rear. So if you want to add an element, you will add it from the rear side. That means this side. You're adding the elements. This is your rear side. Okay. And if you want to delete it, you are deleting it from the front. Let's suppose this is 5, 6, 7, 8, 9, 10. Now you have 11 and 10, and still you have memory locations available. Now you want to add, you will update your rear and it will go there. And if you want to remove, you're going to remove this element and you'll increment your front pointer to this location. So this is how you work around with queue. So obviously with these two there, stack and queue, we can implement these data structures either using arrays or either using linked list. Okay, both of them. So obviously there will be some kind of difference in the way you are implementing it. Obviously with arrays you have fixed size, with linked list you have dynamic size. With arrays you have to store contiguous memory locations, right? And with linked list, even if there is no contiguous memory location, you can still use your memory very efficiently, right? So these are some linear data structures, and we will cover all of these linear data structures in this course. Now let's talk about non-linear data structure. So nonlinear data structure allows arrangement of data in a non-sequential manner. There can be n neighbors for a single element, right? So let's suppose this is a nonlinear data structure. We are talking about binary tree, or we are talking about n array tree. That means there are no restrictions of how many child this root will have, or this element will have, or this node, rather to be specific, this node will have. So there will be n number of childs for this node, right? So there is no restriction. For the next node, there can be two childs. So this is what is written. They can have n numbers. There can be n number of neighbors for a single element. And they do not have predefined extremes. Like we saw in a linear data structure, there were extremes, right? You have a front end, you have a rear end, or you have a top in case of stack, right? And you have, in case of arrays, you have to define a size. In case of linked list, you have a head and a tail. But here you don't have any extremes. There is no extreme in this nonlinear data structure. You can store them as you want, and it is not specific that every node will have extremes, right? So similarly, if you talk about binary trees, now we are restricting our number of childs that each node can have. So let's suppose this is a binary tree. So this node at max can have two childs, one on the left, one on the right. And this node can have at max either zero child, one child, or two child. So at max he can have two children, like in this case. It can be empty, or it can have one left child, or it can have, the next node can have a different right child, a single right child. So this is a binary tree. Now you can even restrict it further by arranging these data in such a way that you always store on the left hand side, you always store the lesser element than the root, and on the right hand side you always store greater elements than the root, right? So these are different variations. Now let's talk about different types of data structures, nonlinear data structures that are there. So if you talk about binary tree, right, this is a restriction of storing your data in a hierarchical fashion. So you will be storing your data in hierarchical fashion, but every node will have either 0, 1, or 2 nodes, right? It will have left child, it will have a right child, or it can have two. This node can have two children. This node is having two children, right? This node is having 0 children. This node is having a right child, thus it has only one child. So this is a binary tree wherein every node at max can have two children, right? Now we can even restrict it further by saying that you can always have, let's suppose the data stored here is 10. So you can always have elements on the left hand side that are less than 10. That means you can have any number of elements, but they will be restricted in such a way that all those elements will be less than 10. So this is your BST, binary search tree. And all the elements that are greater than 10, that means 11, 12, 13, 14, will be on the right hand side. And all the elements that are less than 10, right, 5, 6, 7, will be on the left hand side. Now, then we have graphs, right? Again, a hierarchical data structure. Then we have AVL trees. Then we have red-black trees. So all of these data structures are non-linear data structures, right? So what is an array? It is a linear data structure. That means elements will be stored in a linear fashion, right? Linear fashion. Now, if you talk about array, let's take an example. Now, let's consider that this is how you represent an array in the form of a row, right? And let's suppose it contains elements 1, 2, 3, and 4, right? Now, with every memory location, there will be some address, right? So let's suppose these are the four elements, right? 1, 2, 3, and 4. And these are some addresses. Let's suppose this is 100, and this is 104, this is 108, and this is 112. Now, if you talk about memory, obviously these addresses will be hexadecimal. And when you talk about this particular array, it will be somewhere in the memory with four, or you can say 4 bytes of memory for each integer. Now, if I consider this integer, and let's suppose integer takes 4 bytes. Now, these 4 bytes are available for each integer. Now, this is an integer, right? Now, it takes 4 bytes. Now, the second address will start from 104, right? Because now again this will take 4 bytes, then 108. Again, it will take 4 bytes, then 101, 112, right? So in memory, it will be somewhere around. But the thing that obviously you might be thinking, okay, sir, let's suppose this is our memory, and now if we have 4 and 4 bytes, that means 8 bytes here and 8 bytes here. But they are available in chunks, right? This is one chunk and this is the second chunk, and rest of the memory is occupied. Can we store this array in your memory, in the memory? No, because it needs contiguous memory allocation. That means when this is the scenario wherein you have memory allocations or memory locations available in a one big chunk, right? That means if you talk about this array, it requires 4 into 4, that is 16 bytes are available, and they are available in a contiguous memory fashion, right? Or they are available in such a way that it is a one single chunk of 16 bytes. Okay, so then only you can store the elements at that location. Now, obviously, for simplicity, I'm taking this addresses as a number, integer number, but in reality, those are hexadecimal numbers. Okay, so it is easier for me. Okay, so now one more thing is that the elements are stored in a linear fashion, right? But can we access elements randomly? Yes, with the help of indexes. So if you talk about this array, right? 1, 2, 3, and 4. Obviously, this there will be a name associated with this array, right? Now we have index 0, 1, 2, 3. Now, why indexing starts with 0, or why there is a 0 and indexing always starts with 0? Now, the question is that, right? Now, let's try to demystify this fact that why indexing starts from 0. Why not it starts from 1? Now, if you remember, right, I told you that there will be a name associated with this array, that is ARR. Now, this ARR is nothing but name of the array, and name of the array represents, right? It represents its base address, right? Now the base address of this was, earlier we spoke about it, so it is 100, this is 104, this is 108, and this is 112, right? So now this is 100. Now, so let's talk about how you access, we will talk about in the coming slides, we will see how to declare and initialize our array. But let's suppose if we talk about how to access this, we use array and then the subscript and then the index. Okay, the the index is 1. Now I told you name of this array represents the base address, so base address is 100. Now plus 1, now this 1 represents 4 bytes. Okay, so the 4 bytes, then what internally happens, it boils down to 100 plus 4, that means 104. Now 104 is not the first location, it is the second location. Okay, now similarly if you talk about accessing the second element or third element in the array, it boils down to what, array of 2, which is nothing but 100 plus 2. Now this 2 is nothing but 8, right? 100, 108. So you will be accessing the third element in the array. Now how can you access the first element? So ARR of 0, now it boils down to 100 plus 0 because there are no bytes, right? So it boils down to this, that array indexing starts from 0, and now you know why. And this is how you can access elements randomly, so with the help of these indexes. Okay, so now you might be thinking, okay, now we have an array, can we store different elements, right? Can we store, let's suppose this is the array, can we store, in this we will store integer, then we will store a floating point number, then can we store a character? No. If you talk about any particular array, let's talk about this array. Now the data type or the type of data that you can store in this array will be homogeneous. That means you can only store similar elements. Okay, so these are some facts, and this is how array works, and what are the addresses, what are the indexes. Can you store different elements? No, you can only store similar elements in the array. Now let's talk about the applications of array. Now you might be thinking, sir, why do we need this array? What is the reason that we are using this array? So basically, when you talk about arrays, now obviously when you have a scenario wherein you want to store your elements in a linear fashion, right? And that too, you want to store them in a contiguous memory locations, right? So that you can use your CPU or you can use your memory efficiently, right? Not the CPU. You can use your memory and you can utilize your memory to the maximum, right? So you want to utilize your memory efficiently. At that time, you can use this. But obviously, it will have some drawbacks, right? It will have some drawbacks. That is why we have different data structures, right? So if you want to store your data in a linear fashion, you can use arrays. Okay. Now it is also suitable for the scenarios wherein you require frequent searching, right? If you want to search an element in an array, you can directly go and access these indexes one by one, right? So in a linear fashion, you will access, okay, is this the element that you're looking for? No. Is 20 the element that you're looking for? No. Is 30 the element that you're looking for? No. Is 40 the element that you're looking for? Yes. One by one, you can access all those elements and try to search for the element that you are looking for. Okay. So it is suitable for applications which require frequent searching. Now let's talk about one dimensional. So if you talk about 1D array, it can be related to a row, like we saw in the example, right? So that is what is a one-dimensional array. It is represented in the form of row, and we have addresses like 104, 100, 104, 108, 112, and 116. And indexing will be obviously 0, 1, 2, 3, 4, and then there will be a name associated with this array, which is ARR, and then you can store the elements in this array. Let's suppose here it is an integer array. Okay, so you can store only integer elements, and the size of this array is 5, and you have stored the elements 1, 2, 3, 4, 5. So now it can be related to a row wherein elements are stored one after the other, like you see. You have 1, then you have 2, then you have 3, and all of these numbers are in a contiguous memory, are available in a contiguous memory allocation. Okay, now when you talk about 1D array, there is only one index used, right? When you try to declare and initialize your array, at that time you will use one subscript. Okay, so how you can use that? So let's suppose if I talk about this special array that I have defined here, right? You will define it ARR, and then the sub or the index is that the number of elements that are present here, which is 5. So only one subscript will be there, or one index will be used. Okay, so this is how you declare your array. So now let's talk about the declaration and initialization of this array. So obviously, when you talk about the array, there will be a name associated with the array, and then the data type. Are you going to store integer values in that array? Then that one subscript or one index that we use, and then definitely the size of the array. So this is how you declare your 1D array. Now, how can you initialize it? There are different ways with which you can initialize it. Obviously, here you are declaring it. Then you might use a for loop to initialize all the elements. Or you can declare or initialize your array at once. So how do you do that? So you will write, and let's suppose this is the integer array, and you don't have to specify the size. You can directly write the elements, right? And those elements, let's suppose those are 1, 2, 3, 4, and 5. In this case, when you're declaring and initializing your array at once, at that time this size becomes optional. You don't have to specify explicitly the size of the array, but obviously the size of this array will be 5. Okay, now since you are declaring and initializing it at once, so this is optional. But in the case wherein you are not initializing it, at that time this size becomes very important, and you have to mention this size explicitly. Okay, now let's talk about two-dimensional array. So also it is known as 2D array. So it can be related to a table like this, or you can also say a matrix wherein you have rows and columns, right? Now in this, elements are stored one after the other in such a way that you can think of it as a 1D array. Now this is what 1D array, right? As we have already seen it, right? And inside this 1D array, you have another 1D array, right? Now this is known as 2D array. So now how it works, right? Let's suppose you have numbers over here, and you have four numbers, 1, 2, 3, 4. Then you have 5, 6, 7, 8. Then you have 9, 10, and 11, and 12. So this is a 2D array of having, and this will be similar to what? Of having three rows, right? You will have three rows, not four rows. You will have three rows, and in those three rows, right, you will have what? Four columns. One, two, and so numbers will be like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, done. So now obviously this will have, let's suppose this is a zero based indexing, and this will have a zero index here, one index here, and one. Now internally what is happening, it will be a 0 0, then it will be a 0 1, then 0 2, 0 3, then 1 0, 1 1, 1 2, 1 3, then 2 0, 2 1, 2 2, and 2 3 indexing, right? So similar to that, we will have this index will be 0 0, this will be like this, and this will be like this. So if you want to access the element that is present at this location, what you will do, you will run two for loops, right? One will be starting with from a, let's suppose one will start from I equal to 0 to the length of this outer array, that is 3 less than 3, right? So and the another from 0 to the number of rows that are there. Okay, so this one will be the outer loop, this one will be the outer loop, and this one will be the inner loop. That means the number of columns that are there. So this is for row, and this will be for column. That will start from 0 to less than 4. Okay. So this is how you iterate, and it will be similar to this. And now what about the addressing, right? What about the addresses that will be there? So this will be, let's suppose if this is 100, now this will be 104, this will be 108, this will be 112, this will be 116, because internally it is treated as if they are again in a contiguous memory location, but this time around you have a 1D array, and inside that 1D array you have another 1D array. So for declaring it, you will use two subscripts, right? So it will be something, the name of the array, then two subscripts. And now this will represent the number of rows, and this will represent the number of columns. So in this case, the number of rows will be 3, and in this, and the number of columns is 4, right? So this is how you declare your what? A 2D array. So dimension depends upon the number of subscripts you are using. So this time around, we are using two subscripts. Now, let's suppose you are using three subscripts, right? So similar to like this, 3, 3, and 3. Okay, so this time around, this is a 3D array. And similarly, you can have multi-dimensional array, right? And you just need to keep on adding the subscripts. That's it. Okay.
Now let's talk about the implementation of arrays in Java programming. So before getting into the IDE and writing down the code, let's try to see what is the problem statement. That is what code exactly we are going to write to learn implementing arrays in Java programming. Now the problem statement is that we have to write a program in which we are going to create one-dimensional array. Okay, it will hold integer values, and those integer values should start from 1 and store till maximum number it can fit into. Meaning, suppose the size of the array given is 10, then it should store numbers starting from 1 till 10. And also we'll learn how to access those numbers once it is stored in a one-dimensional array, and also display them as an output. So this will be the first part of the problem statement, and then we'll talk about how to create a two-dimensional integer array and how to store number into it, integers into it, starting from 1 to the maximum value we can store into it. And as we know, two-dimensional array is a matrix, so it will start from first row and first column and then keep on storing the numbers going across each row till the last row and last column. Once the two-dimensional array is created, we'll be again writing down the code that will help us access those elements. And then we'll implement the search and sort operation. That is, we'll be sorting down in ascending order each element of the one-dimensional and two-dimensional arrays, as well as we'll implement search on the given array. Now let's switch to IDE and implement this code. So I'm using Eclipse IDE to implement this Java code. And here I've already created a class that is array solution. And there is a main method, public static void main string args. Now, here itself inside the main method, we are going to write down the code that will help us create a one-dimensional array first. So as we saw, the problem statement had two parts. The first part was to create a one-dimensional array and access the elements of that one-dimensional array. So how to do that in Java? Let's try to see that. So first you have to define or declare a one-dimensional array. To define that, you have to give a data type first using the square brackets. The square bracket represents that it is a one-dimensional array. One square bracket meaning one-dimensional array, two square bracket meaning two-dimensional array. Then space and then name of the array. Suppose A1 I want to give the name of my array. Okay. Then after this we'll be using new keyword. New keyword in Java helps us to create any object for a given class, or it helps to allocate space in the memory. Okay. So new and then again int, that is the data type for the array, and in the square bracket we should define the size of that one-dimensional array. So here suppose I want the size of the one-dimensional array to be 6, and then square bracket will be closed and semicolon. So this is how we will create a one-dimensional array in Java. Now, how to store the elements. Now comes the point of storing the elements or numbers into it. As it is an integer array, it will store numbers, that is integers. So I have to store integers starting from 1 to the maximum value it can store. So to store the element, there are two ways. Either you can refer any integer by direct the index number of it, right? So the index in array starts from 0 and goes till the maximum. Suppose the size of the array here declared is 6. So it will go from 0 to 5. So either you can refer like A1 and then you can use 0 as a 0th index and assign some value here 4 and then semicolon. This way you can store it for each index, that is A1 0 will store another number, maybe 5. But as our problem statement says that we have to store numbers starting from 1 till the maximum value it can store, right? So for that, it will be easy for us to use any looping condition. So Java has so many constructs where we can loop around a given code. Okay, one of the construct is your for loop. So we'll be using for loop here. So the syntax for loop is for keyword, then any variable which we'll be using to iterate over a given array. So array should start from where? I should start storing numbers or digits from where? From 0th index. So the value of I will be 0 because I is the variable which I'm using for iterating over the array. Then there will be semicolon. Then the next condition in the for loop is stopping condition, like till where this I should iterate over. It is starting from 0 and where should it end? So that ending condition should be there, the second parameter for. Okay, so I should end at the length till the end of the array I have to store, right? So that is the length of the array. So there is a function in Java that will help us create or calculate the length of a given array, that is a1 dot length. Okay, this will tell the exact length. Why I have given less than sign here? Because the length will be 6. That is the size of the array. But as I told you, index starts from 0 and it will go till 5. So we should not store at 6th place, right? Because 6 doesn't exist. It is starting from 0. So it will go till 5. If it starts from 1, it will go till 6, right? So that's why I should be less than only a1 dot length. Then the next parameter in the for loop is by what you want to increment I every time. Okay, by like you want to go to the first element, then second, then third, then fourth, or you want to go to first element, then third directly, or fifth directly. So that condition we have to put as a third here. So this will be I want to go just like increment 1 1 each time. So I plus plus. So I plus plus meaning I will increment each time by 1. It will start from 0. It will increment 1. It will go to 1, then 2, then 3, and so on. After that, you have to give a for loop, curly brackets. Okay, this implies the body of the for loop. In this now I will write a code to store the element into it. I want to store in A1 ith location. I want to store what? Okay, I'm using a variable over here, count. Okay, this count we can initialize it here itself as count is equal to 0. So this count will start from 0. Okay, it should be of type int because that is what we are going to store in this array. So this it will start from 0. So at when I is equal to 0, that is at 0th index of array, it will store the value of count, which is 0 initially. Then it will increment I. Then second location, it should store 2. That is, I should increment this count every time. So I'll increment, okay, as it is, we can start it from 1 because I want to store number from 1 to n, okay, 1 to whichever maximum it can store. So it will start from 1 and then every time I'm going to do count plus plus. It means it will increment count. So it will store 1 first, then at second place it will increment itself and store 2, then increment itself and store 3 and then 4 and then so on till the last place in the array. Okay, so this is how we'll be writing down a code for storing numbers into a given one-dimensional array. I hope this is clear. Now, we'll come out of this for loop. We have to access the elements of this one-dimensional array. To access and display, what we'll do, again we have to use for loop. Every time to iterate over an array, we have to use some looping construct. Okay, and I'm using for loop over here. So again, I'll go from int maybe j this time. You can take same variable also, no issues, but I'm taking different variable, guys. So j will be again less than here a1 dot length. Okay, and semicolon, j will increment every time with 1. And in this, I have to access it. That is, I have to display it. So I can do system.out.println. Okay, SYSO if you type and press control space, guys. In Eclipse IDE, it will write the full form of it automatically. So system.out.println, and then here I should print what? A1 of j every time. Right, so it will display it. And as I have given here print ln statement, it will print 1 in each line. If I want to print all in the same line, you can do like this, plus, and then you can give a space here. So it will give a space between every number and it will display it. Save it and execute it. So once you will execute it, you will see the numbers has been stored starting from 1 to 6. Because 6 was the size of array. So it started from 1 and stored till 6. If you want to change this, you can do suppose 8 is the size. There won't be any other change. You will just uh, change the size here and the for loop will take it till the end of the array, that is till the length of the array from 1 to 8. Okay, so this is the implementation of one-dimensional array. Now coming to the second point of our problem statement in arrays, that was about your two-dimensional array. So once we are done with two-dimensional, then I'll talk about the search and sort over this one-dimensional and two-dimensional arrays. Now I will comment this line here. Okay, and we can go ahead and from here we can write down the code for two-dimensional arrays. So here I'm going to write creation and implementation of 2D array. Okay. So what you have to do here is same thing, data type, that is which kind of data you want to store in the two-dimensional array. Then as it is a two-dimensional array, it should have two square brackets. Okay. Then again the name of the array, suppose A1, again same name I'm going to give here, and then equals to new operator to allocate space to it. And then again this the type of the array which you want to create, and then again two arrays here, I mean two square brackets here. You have to provide the size again, guys. So let's have 3 and 4. So 3 rows and 4 columns matrix or a two-dimensional array will be created. This is how we create a two-dimensional array. To access this, as there are not just a single column or a single row, there are columns and rows. So we need two variables to iterate over it. So first variable will be used for iterating over the column, and then the second one for rows, or first one for rows and second one for column. Depends upon how you write the code. So it will start from 0 in the any matrix. The first value is 0th row and 0th column. So it will start from 0 itself. So it will go till a1 dot length, right? And then will increment I every time by 1. So I plus plus, right? Now this is to iterate over the row. Now to iterate over the column, we need one more variable. So one more for loop. Let's take it as j, suppose. Starting from 0 again, 0th column it will start, and it will go this time till each row it has to start from 0 and go till end. Then next row start from 0, go to the end of that particular row itself. Getting it? So it will go till the length of each row. First row, then second row, third row, fourth row, this way. So every time it should start from 0 and go till end of each row. Getting it? So it will go till where? A1 of I dot length, then semicolon, and it will increment every time only one value. So j plus plus. Getting it? So you have to be very careful here with the ending condition. That is where the loop should end. I will start from 0 and it will end at a1 dot length. And j will start from also 0, but it will go till end of each row every time. First row, second row, third row. That's why it is a1 I of length. Clear? Now in this, to access or to store values, so first let us store the values, then only we can access it and display it. To store the values, the syntax is again same, just that you have to use I square bracket and then j square bracket and equals to, we'll store some value here. Let it be a variable count. So you have to again initialize also, guys, here. Count, let it initialize to 1. And as I want to store numbers starting from 1 till the maximum it can store, that is 1, 2, 3, 4, 5, 6 till the end. So I have to increment count also every time. This is how it will look like. Okay. Now to access it again, this is to insert the element. So now insertion is done. Now let us display the result. To display again, guys, you have to iterate over a two-dimensional array over a matrix. So the same condition, that is for loop, will be used I and j, two variables, to iterate over the row and column respectively. So I'm just copy pasting the same thing from here. Okay. You have to write it down again. Okay. So yeah, to display it again in Java, there is system.out.println is a command you can say, or println is a function. Out is an object and system is a class which has out as an object, which is used for calling the println function. So in this, we can now display or call the array, that is a of ij. Getting it? Now, suppose you want to, like this, if I execute it, you see here what you will get as an output. So you can see it starts from 1 and it goes till 12. As the array was 3 is to 4, 3 rows and 4 columns. So it will start from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? 4 in each row. But you can see here it is displayed as like one element in each line, right? Or each row. I wanted to display it like a matrix, like rows and columns. Then only you will understand that exactly how many rows and how many columns were there. You can little bit of formatting is required here, nothing much. So you can just use little bit of formatting constructs. Once you come out of this loop, you can put again a command of system.out.println, and I hope this should work. Let's see. So yes, you can see here the output as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, as we saw how to create a two-dimensional array, how to store elements into it, and then how to access it. Now, let's talk about the third point of the problem statement, that is sorting and searching. How to implement sort and how to implement search over a given array. Okay. Now, to implement sorting, there is an inbuilt method that is your sort itself that is defined inside array package of Java, which we can directly use it. Okay, and inbuilt this sort method uses quick sort basically, but we can directly use it just calling it as a method. Okay, so we'll see that, and then we'll talk about the search. How can we do over a given array? So here also I will talk about how we can create a array in a little different way. Okay, so in this also you have to define a data type, then the name of the variable, that is array, and then equals to new data type again, square bracket. After this, don't give the semicolon. You can put here the elements which you want to store into that. So now as I am going to store in sorted order, then right now I'll be storing it in some random order so that later on when it is sorted, we can get an idea that, okay, fine, it is sorted. So let's take it 362958 or some more number, maybe 1. Okay. Then you put semicolon over here. Okay, so this is also one way of creating a one-dimensional array by just directly putting the values which you want to store there. Now, inside the array class, there is a sort method. Okay, so you can see here sort, it takes different data types, double, char, byte, float, int. So I have to take int here. So the array it is already taking A1. So that's it. So I have to implement sort over a given one-dimensional array A1. So A1 will go as a parameter to sort, and as it is defined inside class arrays, so you have to call using arrays and then dot operator dot. Now if you want to print and just check that, is it actually sorted or not. So let's do one thing. We can first call or print the elements here itself, and then again after sorting we can print and just check that is it actually printed or not. Okay, it will go till the length of it, and then we'll do I plus plus, and in this we have to call system.out.println and then a1 of I. Okay, again we can call this for loop, so I'm just copy pasting it over here once it is sorted, and so that we can get an idea that is it actually sorted or not. So let's see, we'll execute this code and check. Okay, once again I will just not use println here so that it comes in single line and we can see the output properly. Okay, 1 second. So you can see here earlier the numbers was 3629581, right? And after that the numbers are in sorted order 1, 2, 3, 5, 6, 8 and 9. So this is an inbuilt sort method which you can use to sort the elements of a given one-dimensional array. Now if you have to implement search over it, then how will you do it? Let's write a code for it. So okay, we'll write it inside the main method itself. Guys, to implement search, there is no inbuilt method which I'm going to use here, but a simple logic of linear search can be applied. Don't try to now no worry about what is linear search. Normally, if I ask you to search a given element in an array, like suppose in this array, if I ask you to search where is 2, what will you do? You'll just start looking from the first one and then go until you find 2, right? That's a simple logic which we are going to write the code. So again, to iterate over a given array, we have to use a variable to iterate over it and a for loop. Before that, let's create a method first. So public void search. In this, I have to pass what? The array which you want to search and the key which you are looking for, right? So it is int a, or you can write array itself here, and then int key which you're looking for. And then inside this, you have to write okay guys, so this has to be written obviously outside the main function. You can't have another function inside a function. So yeah, I should have written it here. Yeah, let's see now. So search, let's have a return type to be of int, okay, so that it will return the index once the given key is found. Okay, so here what I'm going to do is to implement search, as I said, we'll need a for loop. Okay, it will start from the initial value, that is 0, and it will go till the length of the array. Okay, and it will iterate every time with just one value. Now inside this there comes the main logic, that is you have to search what, that the each element at a given index starting from 0, is it equal to the key which you are searching for. Then we need what, if loop for that. So if array at ith index, is it equal to the key which we are looking for. If it is equal, then it should return the particular index, that is I. Else, or you can, no need of else loop here, you can just come out of the for loop, and if doesn't found, like it scans the complete array and it doesn't found, then it should return -1, right? And that is your done with the method. That simple was it. Now we'll call this method in the main method here. To call this, we have to store the value returned from it, maybe the index value, into the index value is a variable which will store whatever is returned from the function search. Okay, so we'll call the search function here, and we'll pass two parameters because this function takes two parameters. So what we need to pass, we want to search over this given array itself, A1, and we want to suppose search for let's say 9. Okay, so it will be called. Fine. Let's check with this. Is the spelling correct? Yes. Okay. Okay. So we need to have this as a static because we are calling it from the main method, which is a static reference. So from a static field, we cannot make a non-static reference in Java. That's the reason we have to make it as a static. Now, once it returns, then we have to print it. To print again, I'm going to put a condition here that if suppose the function returns -1, it means there was no element, right? If this index value is equal to -1, it means what? It means that there was no such element which you are looking for. That is element not found. Else, it will print that the element is found and is at index, whichever is the particular index, we can print that. We can print what? Index value, because the index which is returned is stored in the variable index value, right? So this is the small code for searching a given element in a one-dimensional simple array. Let's try to execute and see if this gives the output. So yeah, it says that the element is found and is at index 6. Is it correct? Actually, we have sorted it already, right? So, okay, if I just comment this for you to understand it in a better way, let's comment this, okay? So once it is commented out and when we execute this again, What you found is this is the all the elements of array like 3, 6, 2, 9, 5, 8, 1, and then we are looking for 9 here, and 9 is at index 3, right? 0, 1, 2, 3. And if you search for something which doesn't exist in this, suppose 11, then it should print that element not found. Let's correct the spelling here. MENTS, yeah. Element not found. Got it? So this is a simple code for how to create a one-dimensional array, how to create a two-dimensional array, how to access the elements of a one-dimensional and two-dimensional array, as well as how to implement sorting using an inbuilt sort method, as well as how to implement search. So technically or ideally, we have used quick sort, which is already implemented internally using sort method in Java. And in search, we have implemented linear search, which is a simple comparison of each element of an array to what we are looking for.
Now let's talk about advantages of arrays. So obviously when you have indexes associated with the array, right? We have indexes. So it is easy for us to access any element, right? With the help of this index. So if I want to access the third element, you can directly go ahead and say ARR of 2 in the 1D array, right? So you can directly access elements with the help of indexing. Similarly, it is easy for us to iterate through it, right? With the help of one for loop, we can iterate through all the elements, right? One by one that is there, okay, that are there in the array. And similarly, if you want to do the sorting, we can go ahead and easily iterate through these elements one by one and look for an element. If we are trying to search an element in the array, let's suppose we are searching for 3, so one by one we will search, okay, is this element 3, 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 right? And if this element is 3, we can easily search. And also for sorting, right, let's suppose we want to sort this array, what would it be? It will be simply what, if you have 4 here, 3 here, 2 here, 1 here, and let's suppose you have 0 here. Okay, so now you want to sort this in the ascending order. So what you will do, you will use two loops. One will focus on this first element, and then the second one will compare all the elements. Okay, and then at the end of this thing, you will have the largest element at the end of the array. So sorting, iterations, searching, it is easy in array. You just have to iterate through all the elements one by one. Now it is a replacement of multiple variables. Now what do you mean by this thing? Let's suppose you have an integer, or let's suppose you want to store the roll number of 10 students, right? So what you would have done earlier, prior to what, when you don't know the arrays, what you would have done, you would have said roll number 1, and then it's or you can say S1, S2, S3, S4, and one by one you can store the roll numbers in these integer variables, right? So as soon as our students increase, now let's suppose we are talking about here 10 students. Now as we talk about 100, now what happens if we talk about 500? Are you going to write 500 variables, integer variables, S1 starting from S1 to S500? No, it is a very inefficient way of doing so, right? So instead, what you can do, you can create an array, and you can create an integer array and name it student, and therein you will have the size which obviously represents the number of students that are there, and in this case it will be 500. Now if you want to change it to tomorrow, if you want to change it to 600, you can go ahead and easily change it to 600, right? So it is the replacement of multiple variables. So this is what it means. Now let's clear the screen, and now let's talk about disadvantages. There is one disadvantage that can be easily noticed is the size. Now obviously when you're talking about 1D array, right, the size, or any array, right, the size is there, right? So you cannot exceed this size. The elements cannot exceed this. So let's suppose you have the size is 5, you can only store 5 elements, right? You cannot go more than that or beyond that. Now if you have a size 100, and now you're trying to store only 2 elements, anyway the 100 memory allocations will be there for this array. That means you are wasting your memory, you are not utilizing it efficiently. Okay, so this is what it means, that size is fixed and you cannot store more elements, and if the capacity is more than occupancy, most of the array gets wasted. Okay, so These are two things. Apart from this, you need a contiguous memory allocation. That means if chunks of memory are available here and there, you cannot store an array which is, let's suppose here you have 16 bytes and here you have 16 bytes. Only if you have an array which is of 16 bytes, that means if you have an array of size 4, that array can be stored here. But if you have an array of, let's suppose, size 8, you cannot store 4 elements here and 4 elements here. That will not be happening. Okay, that cannot happen rather. Okay, because it needs contiguous memory allocation. So there is one more disadvantage. And the last but not the least is that insertion and deletion is difficult. Now, why do you say that? So let's suppose you have an array and you are having in this array 1, 2, 3, 4. Now let's suppose you want to insert a value 0 at this location. Now what you need to do, you insert the 0 and rest of the elements, every element will be swapped. So swapping is required, right? Swapping is required. Plus there should be memory available so that you can store that element. Else, if there are only 4 elements and now you want to store 0, and the size is also 4, at that time around what happens, you will store 1 and rest of the elements will be swapped and you will be losing this value. So it is very difficult to insert the value. Now, same thing will happen when you're trying to delete, but at that time you will not be losing data, but yes, swapping is required, right? So let's suppose you want to delete this location. So what you will do, or delete this number, what you will do, you will overwrite this with 3, you will overwrite this with 4, and let's suppose if there is 6, you will overwrite this with 6. So at the end you will have 1 3 4 6, right? 1 3 4 6, and one memory allocation is there and it will contain the same element, that is 6. So next time around, you will just overwrite this. So again, the swapping is required. So it is very difficult to insert and delete an element in the array. Now let's talk about stack. What is stack? Stack is a linear data structure. That means if the elements are stored in a stack, they will be stored in a linear fashion. Now, it follows the principle of last in, first out, also known as LIFO. That means the element that entered at the end or in the last will be the first element that will be removed. As simple as that. Now, you might be thinking, okay, it follows the principle of LIFO. Now, that does that mean its removal is restricted? Yes, it is. So you can only access the top of the element. That means this element is accessed. And how can you keep a pointer or keep a track of this top? With the help of this top index, this pointer or iterator that is kept for the tracking of the top of the element. So once you have entered this, the top will go up. Then you have entered this, the top will go up. That means you're incrementing top. And finally, the top is here when you enter this. Now, since you're removing this, that means only you have the access to the top of the element. You are removing this, then you will decrement your top. Okay, that's it. So with the help of this top iterator, you can keep the track of the last element, and you can also keep the track of the elements which entered in the stack. Insertion and deletion can take place only from the top, which is obvious, right? Let's suppose you're trying to insert the element. What you will do, you will increment your top and then insert your element. And if you want to remove it, you just decrement your top. That's it. So this is what you mean by pushing and popping, right? So the elements that you are inserting, that is nothing but your push operation and you will increment your top. So elements you are removing is nothing but your pop operation. If you take an example of stack of plates, right, one after the other, those plates are stacked upon each other, right, one by one. So you can only access the top plate and you cannot access anything that is in between. So that is the restriction that is there. So in terms of stack, there are four major operations: push, pop, is empty, and peek. So push means nothing but to insert an element in the stack. So you're inserting. And now you might be thinking, okay, what is the time complexity of this push operation? Since we can keep a track of this, the top of the stack, right? With the help of this top, we can have a track of what are the elements that are on top, right? So only, let me just show you. Since the top is here, right? At this, now you want to push. So you just update your top, that's it, right? And you insert value. So this takes a constant amount of time. So inserting a value takes a constant amount of time. That is the big O notation, right? Big O of 1, that is constant amount of time. So similarly, we can remove the element, and it can be done with the help of this pop operation. That means we can remove this top of the element just by decrementing our top. Once we decrement our top, this top of the stack element is removed. So now again, we are just accessing, or we are just manipulating this top in a constant amount of time. Again, this push operation and pop operation, both of these operations take big O of 1 time. That is the constant amount of time. Similarly, if we check is our stack empty or not, we just check the value of this top. If this top is having any value other than -1, that means we have elements in the stack. So we return false. So again, this is empty operation, takes constant amount of time. Similarly, peak is nothing but it is similar to pop. Only thing is that we will not be removing, or we will not be overwriting the top of the stack value. We will just see what is the top element. That is, if we are implementing it with the help of array, we will see that it can be implemented using arrays and linked lists. So if we are implementing it with the help of array, as we have already covered it, and if we are implementing it linked list, we'll see both of these implementations one by one. So let's take an example wherein we are implementing it with the help of array. So what we will do, we'll just return this value. That's it. We will not be either removing it or overwriting this value. We'll be just returning the top of the element. So peak is similar to pop, but the only thing is that in pop we are removing the element, in this we are not removing the elements. Again, this will take a constant amount of time. So all these major operations are taking constant amount of time. That means with the help of this top iterator, we can do all these operations in a constant amount of time, because he is the guy who keeps track of what are the elements in the stack, and with the help of this we can remove the element from the top of the stack, we can add the element from on the top of the stack, we can push, we can pop, we can check if the stack is empty or not based on the value of this top, and we can also peek the element, right? We can take a peek of the element, right? So with the help of this top. Okay, so again, that is in a constant amount of time. Now let's talk about the applications of stack. Now, whenever we use recursion, right? Whenever you use recursion, what happens internally? A stack is created, right? Let's suppose you have a function call, and in that function call, you are calling this function again. Obviously, this will be called from the main function, right? Let's suppose this is our main function. Let me just erase it and write it in. Yeah. So this is our main function, and it's calling this function, and this function is calling this function. That means it's calling itself again and again and again, unless and until a base condition is reached. Right now, once the base condition is reached, it starts popping it out. Right. This is all these are push operations. Right. And now pop is performed one by one, unless and until all the function call return its value, and finally it returns to our main function, and finally then main function is popped out of the stack. So whenever we are using recursion, a stack is maintained. And we also find out, when we talk about recursion more in depth in this tutorial, we'll see how we to create this activation record that is created, and activation records are created, and with the help of these we can easily detect what are the statements that are yet to be executed, okay, in a function call. Let's suppose you have three statements in a program, and one of them is to check the base condition, second is to the function call itself, that is this function calling itself, this is a function outer function, and in that function you have three steps, and then this is a simple print statement, okay. Then let's suppose this is an activation record, and one, two, three. So this is checked, and this calls the function again. Again, an activation record is created. So again, one, two, and three are checked. So this is checked. Again, this calls a activation record. So now these are all push operations. So once it returns, now the pop is performed. Now it returns to this point and it executes this value. that is prints out the value, whatever is the value. And once it is done, so it returns to the function who called it. And once that is done, this will be popped out of the stack, and then once this is executed, it will return to the main function. So in recursion, stack is maintained internally. Now what about parsing? So whenever we talk about automata, right, automata is one of the subjects in computer science. Therein the parsing happens whenever your program is divided into tokens. Tokens are nothing but keywords. What are the keywords in this program? What are the conditional operators in this keyword? What are the constants? So all these in your program, all of these things are divided into tokens, and then parsing happens. Okay. What about the browser, your application? Whenever you open up any website, right? Let's suppose you are opening Great Learning Academy. Before that, you go into the Google Chrome, you type in Great Learning, therein you will get the link of Great Learning Academy. Click on it, it redirects you to the Great Learning Academy. Then in Great Learning Academy, you look for the popular courses, or let's suppose IT and software courses. When you click on it, let's suppose it directs you to the another course that is related to IT and software. In that you have, let's suppose, C. You click on it and it will direct you to the C program. So one by one, these are all push operations: P1, P2, P3, and P4. All these are push operations. Now once you press back, what happens? You pop out, this pops out of the stack, and you go on to this courses. Again, you press back button, you go on to the Great Learning Academy. So these are all pop operations, and finally when you click on the back icon, you go on to the Google page, right? So this is all that happens while we are working in browsers and in editors. Whenever you do redo operation or undo operation, again a stack is maintained. So these are all the applications of stack.
Now let's talk about the implementation of stack data structures in Java programming. Before getting into the IDE and writing down the code, let me tell you what is the problem statement. That is what exactly the code we are going to write for in stack data structure. We are going to write a program which will be implementing the following points. That is, we'll create a stack first. We'll see how we can create a stack in Java and then implement the different methods, different operations which we can perform on stack using the different inbuilt methods which are already there defined in different packages of Java. Then we will see how we can access those elements. Accessing the elements of the stack involves a different concept. So that concept, how we are going to code into, will be talked about. And then we'll be implementing the following given 7 functions. That is push, pop. We'll check if the stack is empty or not. Peek, search, size, and sort. Before getting into the implementation part, I would also like to tell you that stack is an inbuilt class which is defined in Java programming. This is the inbuilt class. Okay. There is a collection framework, or you can say a collection interface that is implemented by stack. Okay. So stack implements the different methods of collection interface, and there is this complete concept of collection framework in Java which will help to implement different data structures. One of them is stack. Also, there is a class called as vector in Java packages. This vector class also has certain methods which stack extends. So stack has different methods. Some will be using from the vector class and some from will be implementing it which are there in the collection interface, and try to see how we can perform different operations on a given stack data structure. Now let's get to the IDE and try to implement it. So I've come to the IDE, that is Eclipse IDE, and here already I've created a file that is having a class called as stack solution, and also the main method, that is the method which is mandatorily required in any Java given code, that is your public static void main. This is written. Now inside this main method itself, we are going to perform all the operations on everything related to stack. So the problem statement we have discussed already. Now let's try to code it down. So to create a stack, we'll be using the inbuilt stack class. And to create a stack for a given class, we have to just simply do that, create an object of a given class. Okay, and the class is your stack. So stack name of the class, space, the object which you want to create for this stack class, that is the name of the stack. Suppose S1. Okay. Then new keyword, every time we'll be using new keyword to create an object that does actually what? Allocates memory to that object. And then we'll be using again stack. This is one way of creating an object. But here there is no way to define, this is an object. There's no way to define which type of data will this object consist of. So there is one more method or one more way of creating stack object. That is stack, that is name of the class. And then you have to give greater than and less than sign. In between this, you should write the type of the data will be storing in the stack. Suppose you want to store all numbers, that is integers, or you want to store all characters, or you want to store all the string values, or floating values, that are decimal numbers. So accordingly, you will give the data type here. Data type should be the classes, that is the wrapper class called as in Java, right? That there is a wrapper class for every data type. That wrapper class you have to use. For example, if I write int here, it won't work. It will throw an error. So I should use what here? Integer. Getting it? And then the name of the stack, that is S1. Then again new keyword. And then again stack class. But here you have to use again greater than and less than sign. And then the round brackets and then semicolon. This will specify that the stack S1 contains all the integer numbers. So this is how we create a stack. Simple. That is creating an object or stack class. You can implement stack using one-dimensional array also, guys. But here I'm using the inbuilt stack class. Now, in this, you have to perform different operations. To perform different operations, the first one is let's insert some value into the stack. To insert some value, there is an inbuilt method called as push. So how to call that or how to use this method? That is, you have to use the stack name, that is S1, using dot operator, dot, then the method, that is push. And in the bracket, you will provide what you want to push into. Suppose I've used integer here, right? So you'll be using integer value. If here, suppose I would have used maybe a character or a string, then I should have given a string or a character value over here, right? Let's insert one more value. 4. Let's do one more just to check. Okay. 9. So this is how we'll be inserting the elements in the stack. Now suppose I want to print and then see that has it actually been inserted. So I can just print, that is system.out.println S1. Now let's execute this and check. So you can see here 2, 4 and 9 are the 3 elements inside the stack S1 which gets printed. Now suppose I have to delete something from this, remove. The operation is called as pop, and even the method name which is there to remove the elements from the stack is also pop. So how to use it? Again S1, that is your stack name, dot operator, pop. And in this we are not going to specify anything, just write pop, that's it. It will remove what? The first element which can be removed. So stack works in first in last out manner. So it will delete the last inserted element first, right? So s1.pop will delete what? See, you can see here first 2 was inserted, then 4 was inserted, then 9 was inserted. So you should pop out what? 9. Let's see. Does it pop out 9? So after that, I'll just put a print statement and check that is it actually deleting 9? So yeah, it is actually deleting 9. It's 2 and 4. Getting it? If suppose I do again s1.pop, then this time it should delete what? And again, I'll print this and we'll check. Okay. So you can see it deletes 4. So first it deletes 9, then 4. Now only left is 2. Okay. I will just comment out these lines. So this was the operation for inserting element into stack. So we inserted the element into stack. And here we did what? We created a stack. by creating an object. Then we've performed here the delete operation on stack, right? Now let's see and check about the other operations which we can perform. So what I'm going to do here is peek operation. Guys, as a no name itself, the literal meaning itself of peek is that to look into. From top, suppose the stack is arranged, and from top, if you look into it, what will you see? The last inserted element will be on the top, and that will be visible to you. So that's the work of this peek method. That is, if you peek into a stack, look into the stack from above, what is that element which will be seen to you? So right now, if I execute this, guys, so right now the elements are 2 and 4 in this. So first 2 is inserted, then 4 is inserted. So if you look from the top into the stack, what will be the element you will be seeing? The top one, that is 4. So it should give 4 as an answer output to me if I use peek. So let's see. So s1 dot peek, if I call and try to print this. Okay, we'll put it inside the system.out.println and let's see what it prints. Okay, so you can see 4 is the output, right? So that's the work of the peek operation. The literal meaning itself, that is looking into the stack over here. Now, next operation which we have to look into is to check is the stack empty or not. Many times you will encounter such situation where you have to check that is the stack empty, is the stack full. Stack full, there is no such concept. Okay, you can insert as many elements you want here, but if the stack is empty, that has to be checked, right? So how to check that? So there is a function called as empty which has a return type as boolean, that is true or false. So we have to use a boolean data type here. Suppose status equals to, and then I'll be calling s1 dot empty, and then I will print this status variable. And let's see, right now is the stack empty? There are 2 and 4, 2 elements here. So it should say what? False, that the stack is not empty. So you can see false is the output. Right here you can see. If suppose I empty out, I perform so many pop operations here and I empty it out. So let's see here. So here I am going to call now s1 dot pop again. And then again I'll be calling s1 dot pop operation. Now I think 2, if I delete, that is 4 and 2 will be deleted. So it's empty now, right? Let's see what. Okay, it still says false because I'm printing it here itself. So I'll be printing again. Okay, let's do one thing. We will put the pop operation above itself, delete everything, and then try to call the status. I mean, check the status, is that empty or not. So you can see here after deleting everything, so 3 pop operations and 3 push operations. That is whatever we inserted, we deleted it. Push 2, push 4, push 9, and then again pop, pop here, again pop here. That is, it is deleted. So status is true, that yeah, the stack is empty. So we saw 4 operations: push, pop, peek, and empty. Now, to implement sorting over here, there is an inbuilt method which you can use over it. But before that, let me talk about search first. Okay, to search also there is an inbuilt method called as search, which has a return type of integer. So whatever you are searching for, that will be found and the index value will be returned. Okay, so how to call that search method? Let's see that. As I said, it has a return type of int, so you should use int variable data type for a variable where you'll be storing the result of that search. So int maybe index found. Okay, and then you'll call s1 dot search. and then what you are searching for. So suppose I'm searching for 4 over here. Okay, I will comment out this pop operations so that I know it's not deleted. There is something inside so that we can get to know that we can search. Okay, so let these pop operations be commented out. So right now there is push operation only. So 2, 4, and 9, 3 elements are pushed into the stack. And now I'm going to search for the value 4. So it should search and tell me the index value. And then that index value I'm going to print here. That is your index found. Let's see what's the output. So you can see here, uh, the last value, that is 2, prints is the output of the last print statement, that is index found. So it says 2. So you can see 2, 4, and 9. Here the 4 is at what index? 2. First is 1 index. So here it counts from 1, not from 0. At 1 index there is 2. At 2 index there is 4. At third index there is 9. So 4 is at second index, and that's what the output is over here. So this is an inbuilt search method that is implemented over stack. We can directly make use of it in our codes in Java programming. Now let's see how we can iterate over. So right now, to print any value of a stack, I'm just using system.out.println and that particular stack name, that is variable name I'm giving, that is S1 over here. But what if I want to iterate each element one by one and then check or perform some operation or anything? In that case, we have to iterate over. So in other data structures, for example, in arrays, if you want to iterate over, we use a variable and a for loop and we iterate it. In stack, there is a different provision which we can do. That is, we can use a method called as iterator. How to use this method? Let's try to check that. So iterator is a class. You'll create an object of this class. Okay. And then on whichever stack you want to iterate over, using that stack, that is S1, I'll call the function iterator. Getting it? So now what happens is that this S1 becomes iterable because iterator is a method that is called over the stack S1. And how we'll iterate over it? That is how we'll scan over it using the object IT of class iterator, which we have defined here. So this is done. This part is clear. Now, so here, first of all, I'll write a comment that we are talking about how to iterate over a stack. Okay. Next is to iterate over here, we'll be using while loop. That is while there is next element in the stack. Like we'll start from first and we'll go till the end. Till where we'll go? Till where there is element in the stack. Once there is no more elements further, it should stop there. So to do that, we'll use while loop. While IT, that is the object of iterator class, has next. So has next is an inbuilt function again of the iterator class itself, which we are using it over the object of iterator class, that is it over here. It is the stack having more elements? So has next, is there a next element? Is there a next element? It will keep checking. So that is what has next does. And if there is next element, then we are just going to do what? Print it, right? And to print this, we will use it. Okay, we'll do one thing. We'll create an object over here. S2 maybe equals to new. Okay, no. IT dot next. And here we will be printing S2. It means what? This next function is used now to do what? It will just store that next value every time into S2 object, right? And then we are going to print this S2 object. So this is the complete concept of iterating over a stack. That is, you have to create first object of a iterator class, that is it over here, and using a method iterator will be making the stack iterable so that we can access it one by one. Then using while loop, we will traverse from beginning to the end of the stack, and has next is a method that helps there. That is, has next does what? It keeps checking that is there next element in the stack. And then next is a method which is used for fetching the next value from the stack. and it will store it in any object, that is S2 over here. You can give any name, any variable name for that object, and then we'll print that. Okay. Let's see the output for it. Okay, I'll just give print over here, not print ln, so that it comes in a single line and we can watch it properly. So you can see here 2, 4, and 9. It's not 249, it's the elements of the stack 2, 4, and 9. As I'm no here, see, you can see the how it was printed 2 comma 4 comma and 9, because I was printing the complete stack. But here I'm fetching single values from the stack and then I'm printing it. So it prints like this 2, 4, and then 9. Okay. The last statement here is the output of the last print statement. So this is how we iterate over a given stack. So we have discussed, I guess, all the elements here, that is push, pop, empty, peek, search. Okay, size and sort as the two methods which is left to be discussed. Let's talk about that. So we'll use here itself to know the size of a given stack, like how many elements are there, how many kind of spaces occupied in the stack. To do that, we have a inbuilt function called as size. So s1 dot size. Okay, we can put it inside the system.out.println and we can see what is the output of it. So I'll put it inside this. So if I print this, the output should be 3. Okay. So you can see the last output, that is 3, is the output of the last print statement. That is the size of the stack. And size of the stack is, there are 3 elements, 2, 4, and 9. So it tells 3. Okay. Now let's see the last function or operation over the stack, that is your sort. So to implement sort also, we will use s1 dot sort inbuilt method. In this inside, you have to tell the comparator basically. So as of now, I'm not putting anything that like there is no comparator which I want to give. So it's null. So it will sort it out, and let's print the stack again. That is S1. I'm not iterating over, you can do that as well, but I'm just directly printing the value. So initially the value inserted was 2, 4, and 9. Guys, it is already in a sorted order. Let's like rearrange it in an unsorted order a little bit so that we can get an output as a sorted one. So you can see here the elements are 2, 9, and 5, right? 2, 9, and 5. And now it is 2, 5, and 9. Okay. The you can see the index value here is -1 now, because the value which we are searching, that is 4, is no more there in the stack, right? That's why you can see in the output is -1, this value. This is the output of this particular statement, that is search, this one. We're searching for 4, but 4 is no more in the stack. That's the reason it gives -1 as an output. But need not worry. Our point is here, sort, right? So we sorted it, and after sorting, the elements are properly arranged in the stack, that is 2, 5, and 9. Earlier it was 2, 9, and 5. So we saw all the different operations on the stack data structure, how to implement it in the Java programming. And those operations were push operation to insert the element, pop operation to delete the element, peek operation to just look into the stack from the above, what is the element. Or you can say it helps you get the last element of the stack. That's where peek will be used. Then empty is a method which will help you check, is the stack empty or full, or is there any element or there isn't any element. That is what the job of empty function or a method is. Then there is a search method. This is also an inbuilt method which you can use for searching a given value in a given stack. Then there is a sort inbuilt method which is used for arranging in ascending order the given elements of a stack.
Now let's talk about the advantages and disadvantages of stack. If you talk about advantages, it maintains data in a LIFO order, right? The data is maintained in a LIFO order. That means the last element that is there in the stack is readily available for us to use. So one of the readily available, right? So one of the applications of using stack is it can be used to evaluate expressions, right? Therein we require this feature, that is LIFO. right? And all the operations that are performed in stack, like push, pop, and then is empty, and then pick. All these operations take constant amount of time, which is very important while you're playing around with competitive programming or while you're doing competitive programming. At that time, these are very important that you program in the most efficient way. Programming in most efficient way is important and it is very crucial for your selection, right? In competitive programming. So all the since all the operations are performed in a constant amount of time, so these the stack is used oftenly when you are doing competitive programming. Now, what are the disadvantages? Since we are restricted, right? There's a restriction that we can only add and remove elements from top of the stack. So this is one restriction that is there. Thus, it is not very much flexible, right? It is not flexible. If you talk about the flexibility of how we are storing data in the stack, it's not very much flexible. So these are the disadvantages of using stack. Now let's try to understand queue linear data structure. What is queue? Queue is a linear data structure. That means all the elements in the queue are stored in linear fashion. Now, it follows a principle of FIFO. That means there's a restriction that whatever is the first item in is the first item that is to be out. Okay, so now let's try to make a queue. Let's suppose you are in a queue and you're waiting for a movie. You're waiting for a movie ticket to buy. Okay, so there is one person, then there is another person, right? So these are few persons here, right? And you're waiting in a queue. So now the first person who is in the queue will be the first person who will get his ticket, right? Makes sense, right? So he will be the guy who will get his movie ticket first and he will be out of the queue. Then the next person who is in the queue is the next person who will get his tickets, right? And let's suppose a new person comes in, he's not going to go ahead from this person, rather he is going to go behind this person. Then the next person comes, he will go after this person, and in the same way. So this is nothing but a FIFO principle. Okay, the first person in is the first person out. Okay, now insertion will always take place from the rear end. Okay, and if you talk about deletion, it will always take place from the front end. Okay, so this is our front end and this is our rear. Cool. So, for examples, buying the tickets from the counter, or it can be a movie ticket, or it can be a bus station. You are in front of a bus station trying to get tickets for your bus, right? These are some examples. Now, there are four major operations when you talk about queue. What are those major operations? Let me clear my screen. So, enqueue. So you are going to insert an element in the queue. This is what you mean by enqueue. Dequeue, you are going to delete an element, okay, from the queue. Then peek first, that you are going to peek the first element that is in the queue. And peek last means that you're going to peek the last element that is in the queue. So you will have two pointers. One is front and another is rear. And with the help of these pointers, you're going to enqueue, dequeue, peek first, peek last. You're going to perform these operations. Now, one major advantage of these operations, these four operations, is that all of these operations are performed in a constant amount of time. That means the time complexity of performing these operations is O of 1. So that is why when you talk about competitive programming, Q is most commonly used data structure because of these things, right? Because of its time complexity, right? You're able to perform your operations in a constant amount of time. Now let's talk about applications of queue. So it is used in scheduling algorithms of the operating system, like first in, first out scheduling algorithm is there, round robin is there, and we have multi-level queue that is there. In all these algorithms, queue is used, okay, for storing the data or the processes. It's also used in maintaining playlists. Like when you have a playlist, let's suppose you have 10 songs in a queue, right? And after one song, the next song which is in the queue will be played and it goes on for like this, right? So for maintaining a playlist, again, a queue is used. It's also used in interrupt handling. Let me take an example here. You know the process state diagram of operating system. So it is also used at that time. So when you have an interrupt and therein, if your process is being executed at that time, that process is preempted out and it is stored in a queue. Now, the next time when this priority or this interrupt is handled, once it is done, then it starts picking up the process which was in the queue and starts executing that. In the meanwhile, if there are some other processes, that those processes will also be in the queue. So a queue is maintained, and once the interrupt is handled, they will start taking out that process that was being executed earlier and executes it and completes its execution and terminates the process. So it is also used in interrupt handling.
Let's talk about the implementation of queue data structure in Java programming. Before going to the IDE and start writing the code, let me tell you the problem statement. That is what exactly we are going to implement under queue data structure. So the program which we'll be writing will try to create a queue there, okay, and implement it using classes and inbuilt methods. And once the queue is created, we'll be implementing certain functions which will perform some operations on the queue. That is your enqueue, dequeue, is empty, size, and display. So enqueue and dequeue operations are basically inserting the element into the stack, deleting the element from the stack. Enqueue is inserting, dequeue is deleting the elements. Is empty is a method to check whether the given queue is empty or not. Size will tell you the size of the given queue, and then display will display the elements of the queue. That is, it will help you access the elements of the queue and display it as an output. Before going to the implementation, few things which are important with respect to queue data structure under Java, let's try to see that. And that is, there is an inbuilt interface with the name of queue. So queue is already a interface defined in the Java package. Okay, and as it is an interface, it has to be implemented or extended by various other interfaces and classes. Okay, some of the interfaces and classes are linked list, priority queue, and so on. Although this queue belongs to the collection framework of Java, but it is a interface which has to be implemented to implement various other methods. Now, the functions which we are going to write or the methods which we'll be writing in Java is enqueue and dequeue. Enqueue is inserting the elements into the queue. So as you already know that, queue data structure follows first in, first out logic. That is, whatever is inserted first will be deleted also first. Suppose this is your queue. So this will be called as your front end of the queue, right? And this is called as your rear end of the queue. Fine. If I insert any element, it will be inserted from the rear to the front. Then I'll insert another element, suppose 4, which will be inserted here, then 9, and so on. The point here to understand is before implementing enqueue or dequeue operation, there is a condition check which has to be done. And what is that condition check? Initially, guys, for any queue, if it is empty, front and rear, both of these will be pointing to the same place. Yes or not? Because there is no element in this. So this is only the front and this is only the rear. Because right now nothing is there in the queue. Okay, this is one thing to be kept in mind. So when we insert anything and front and rear both are pointing at the same point, it means there are no elements. We'll insert the first element to the queue. Now if I insert the first element, that is 2 over here, front will be still pointing at the same place, but rear will shift to this location. It won't be pointing to this anymore. It will point to this location now. Getting it? Now suppose I insert another element 4 here. Now front will remain same there, but the rear will be pointing now to this location. Getting it? So this is how the front and rear pointer moves. Now, when will we find that the queue is fully occupied? When it reaches to the last. Suppose the size of the queue, like we'll be using one dimensional array to implement this queue. Okay, and one dimensional array has a fixed size. So suppose the size of that one dimensional array which we are using to implement queue data structure is 5. Let's assume. So when the rear points at the fifth location, when the rear points at the maximum location, that is fifth location, it means the queue is occupied, is full, right? So when the queue is full, you cannot insert any more element into it. So what you have to check here, that if your rear is same as your capacity of the queue, or you can say size of the queue, then you cannot insert anything into it because the queue is already full, right? Now, this is a condition you have to keep a check for inserting elements into the queue. There is a condition which you have to keep a check for deleting elements from the queue. Will you be able to delete any element from the queue if the queue is empty? There is not at all any element into it? No, you will not be able to delete, right? If there is something into it, then only you can delete it. There is nothing inside it, then definitely you cannot delete anything. So that is a condition check which you should do. And how can that condition be defined in terms of front and rear, these two variables? If front and rear both points to the same location, it means there is nothing in the queue. Queue is empty. Or you can say when rear points to the first location, that is 0th location, 0th index, it means there is no elements in the queue. You cannot delete anything. So for deleting or dequeue, we have to keep a check for this. That is, if rear is equal to 0, there is no element, we cannot delete. For enqueue, if the rear is pointing to the size of the queue, it means that the queue is full. You cannot insert any more elements into it. So these are the two logics which you have to keep in mind, and always keep in mind in Java, queue is a interface which implements various other interfaces, as well as which queue is implemented or extended by many other classes and interfaces further, but it belongs to the collection framework of Java itself. Now let's go to the IDE Eclipse and try to write down the code for the problem statement which I right now explain you. That is, we'll create a queue and implement all these 5 given methods. So you can see here already there is a class created with the name of queueSolution, and there is a main method in this, that is public static void main, which is a required method inside Java programming. We'll be writing our main code inside the main method itself, but before that we have to implement queue, and for that I'll do it in a different class. Okay, so here I'm going to create a class with the name of queue using arrays. Okay, in this class I will be having a variable for front and rear, two variables we need to track down the queue. So front of queue, okay, and then rear of queue. And then also we'll have the capacity of queue, or you can have a like this, capacity of queue. Okay. Now we'll try to initialize these variables by having a constructor defined for this class. And to define the constructor, we have to just use the class name in Java. This is how we define a constructor. So queue using arrays. And in this, I'm going to pass the size of the queue. Okay. So I'll just write size. That's fine, I guess. I'm using longer variable names to make it more explanatory, guys. You can use shorter variable names also. Queue using array is a constructor here for the queue using array class itself. And in this, I'm going to initialize all these variables which are there for the class queue using array. So capacity of queue will be initialized with the size which is passed to this constructor. Okay guys, we are going to implement this queue using a one-dimensional array. So I'm going to define that one-dimensional array as well here. Let that array be maybe q1, which is equal to new. Okay, we'll do one thing. We'll let it be as of now like this and initialize it inside the constructor itself. Static int q1. and we'll be initializing it over here. That is q1 is equal to new int, and here it will be capacity of q. Okay, so every time the size which is provided while making an object of this class, this constructor will initialize the array size to be of whatever size is passed here. Okay, so that's it, done with the constructor. Now let's implement the methods. So first I'll write the method enq and then deq, and then to display we'll be writing a method. Okay, so to enq we'll write a method void enq. Let it be this name itself. Okay, and in this I'm going to pass the value which you're going to insert. So int value. Okay, now I've told you that to insert an element into the queue, we have to have a condition check. And what is that condition check? That is, if the queue is full, then you can no longer insert elements into it. Okay, so you have to keep a condition check that if rear of queue is equal to capacity of queue, then it says that queue is already full. You cannot insert element, right? So this is your if condition. Now coming to the else condition. Now if suppose there no capacity of Q and rear of Q is not same, then in that case we should go to else condition, and that is your, and if it is not same, like there is place to insert, then we'll be inserting it, right? And to insert the element, what we have to do is in the array Q1. Okay, in this also guys, we have to insert at Q of rear, Q1 of rear of Q. And what we should insert here? The value which we want to, which we have passed to this function, that is value. Okay, so this will be inserted here. Once it will be inserted here, your rear should be incremented one place, right? That's what we saw when I explained you the logic. So rear of Q should be incremented each time. Okay. So this is your condition for NQ. I hope it is clear. Now let's write a function for DQ of it, that is deletion of it. To void function name, that is DQ, and we don't have to return anything from this function, so let it be a void return type. And in DQ, what should be the condition check? So in this, the condition check is that you have to see that there should be some element in the queue to delete it. If the queue is empty, then definitely you cannot delete it. So you have to check here if the rear of q is equal to 0, then in that case, it says that q is empty. There is nothing to delete, right? Else, what should be the delete? After delete, what should be the logic? Okay, to understand that, let's go back to the slide. So I'll quickly tell you here the logic of the DQ function. Okay, so one condition check is already there, that is when there is no elements in the queue, that is rear is pointing to 0th location, then you cannot delete anything from the queue. Apart from that, now if there is elements in the queue, okay, suppose this is your queue and these are the elements 2, 4, 6, 9. Suppose these are 4 elements. Now you have to delete, and definitely you can delete only from the front, first in, first out, right? That's the logic followed by queue. So you can delete only 2. So when 2 will be deleted, how will you represent this programmatically that 2 is deleted? What we'll do is we will overwrite in the same queue from the elements that is after the first element which is deleted. So 2 is deleted. So what we'll do, we'll overwrite 2 with 4. That is 4 will be written over here. We'll overwrite 4 with 6. 6 will be moved over here. 9 will be moved over here. That's all. The same queue will be now represented in this way. So as we have overwritten 2 with 4 and then 4 with 6 and 6 with 9, 2 is no longer there in the queue. It means 2 is deleted. So this is the logic which is followed for dequeue operation. Now let's go back to the IDE and try to implement it. So coming back to the implementation here of dequeue function again. So here we have done a condition check, that is if the rear of q is equal to 0, that is there is no element in the queue, then it should not delete anything and it will give a message that queue is already empty. There is nothing to delete. Now let's see if there are elements. I've already explained you the logic behind it. Let's try to code it down in Java. So to write a code for it, you have to run for loop. So for int of I starting from 0 till I less than, as it is a one-dimensional array, right? So we can use a for loop to run over it. Rear of q minus 1, because when we'll overwrite, the last element will become the second last element. So we should not go till the last element. We should go one less than the last element. That is your rear of q minus 1. And then rear of q plus plus. Okay. In this, what we have to do is that in q1, ith element, so it should be small I, ith element should be now, okay, this will be q1, okay, ith element will be now equal to q1 I plus 1th element, right? That's what we are copying, the second to the first, third to the second, fourth element to the third element, and the last to the second last. So this is what the logic will be there, right? After this, at the last, when we'll come out of this for loop, then we should do what? Rear of q, it's capital Q, right? It should be minus of 1, or you can say minus minus, because that's how your number of elements will reduce. Earlier the number of elements was suppose 10, the minus 1 meaning 9. So this is your dequeue function. I hope the code till now is clear to you. Now coming to the main function, we will create the object of the class and try to call these functions of enqueue and dequeue. But before that, it will be better if you could write the display function also along with it. So let's write that as well. So void display. Okay, there is nothing to take as an input. So in the display, what will be the logic? So just the logic should be that if the queue is empty, then there should be nothing to display, else you can iterate over and display the result. So I'll copy paste the same code from here. So Control C and we'll paste it over here, because this logic is going to be same, right? You can say here that, queue is empty, nothing to display. Okay. In the else condition, what should be there? Now, if there are elements, then in that case, you have to just iterate over it. That is for loop will be used as it is an array. So we can use for loop equals to 0, and it will go till where I should be less than your rear of q, right? And then it should go I plus plus. Okay, one mistake. Sorry, here it should be I plus plus. Yeah. So here in the for loop again, now system dot out dot println, and what we have to display here is q1 of I. So it will display all the elements. So for loop is closed here, else loop is closed here, and the function is closed here. Okay. So this is your display function. Now let's create the object of the class. The class name is q using array. So q using array. Okay. This is the class name, just verifying it one. Okay. So q using array, and then maybe QUE, or I can say Q2, guys. Just a small name would be better. New Q using array, and then I have to pass the we have used a constructor, right? So we have to pass here the size of the queue. So suppose the size of the queue is 5. Okay. Now using this Q2, we can call all the functions like NQ. Suppose I have to insert 2 here. Then I can again call this NQ function to insert 4 over here. Then again I can call, the same function NQ to insert maybe 8 over here. And then we can call the display function to just check that is it actually displaying everything or not. So let's save it and run this file. So yeah, okay, so it's println, so it's giving like this. Once again, I'll remove println from here so that you can, and we can put a, this is just a little bit of formatting, guys. You can do it in your code. So you can see here we have inserted 2, 4 and 8. So 2, 4 and 8 is inserted, and the display function, that's how we are seeing the output, that is 2, 4 and 8, right? So it's working fine. Now suppose there wasn't any element and I would have called display function. Then what should it say? It should say queue is empty, nothing to display, right? And so the code is working fine. Sorry, it should be Q2. Yeah. Now let's see the DQ is working fine. So Q2 dot DQ will be called. It means I would have deleted the first element which was inserted, that is 2. So it should display 4 and 8. Now let's call display over it. So if I call display over here and then try to run it, so we get 2, 4, 8 and then 4, 8 again. Right? Okay, we'll separate this over here once again. I can just write here itself, or you can write it anywhere, guys. Just I'm separating it. So you can see here, so display 4 and 8. So 2 is deleted, is removed. Okay, if there is nothing to delete, then it should say the message that there is nothing to delete, right? If I call just this, I have commented out all the NQ operations, so nothing is inserted over here. So if I run this, let's see, it says queue is empty, there is nothing to delete. Getting it? It means the code is working fine. So now, so let me summarize it for you guys. So what I did is I used a class, any name you can give over here. So where front and rear two variables are used to keep track of the elements. Then capacity of queue is being defined, and this is the code for implementing queue using a one-dimensional array. So there's a static array which I've used, one-dimensional. Static because I'm going to refer it from a static field, that is main method, and that's the reason it's static over here. And there are other reasons also, guys, why we have static variables in Java, but that's a different point. So yeah, then we have a constructor where size is passed and then initialize that size uh, to, or allocated the size to capacity of the queue. Then NQ operation, we have to just check that the rear should not be equal to the capacity of queue, because if it is equal to capacity of queue, it means the queue is full. You cannot insert any more elements there. Else you can insert elements over here. Then DQ, same thing. If you have to just check that rear of queue should be not equal to 0, because if it's equal to 0, it means that the queue is empty. There is nothing to delete further. And if that's there, then the opposite, that is the rear of queue is not equal to 0. It means there are elements into it and then you can delete it. And deletion logic is you have to override the elements from beginning again, because the beginning element, the first element, will be deleted every time. Then display function, there is nothing. You have to just use a system.out.println from beginning to the end. That is from 0 to the rear of q. And with the condition check that if the rear of q is equal to 0, it means there is no element to display in the queue, that is q is empty. So that is it. Now here, if you want to know the size of the queue, so as you have used one dimensional array and the size is already passed here as an argument, or you can say as a value of the constructor 5, so the size is already known here, right? So there is there's no need of separately knowing the size of the queue. Yeah, it's already known here. That is, or you can use an array, the size method of the array class, as it's a q1 q2 is the array itself here, and that will tell you the size of the particular array. Okay, although it's known here, so there is no need of separately defining it. If the queue is empty or not. So to check the queue is empty or not, guys, this is the condition which we have already used so many times in the display function. That is, if the rear of queue is equal to 0, it means that the queue is empty. So if you want to check is the queue empty or not, this is the logic behind it. There is no such inbuilt function which we could use it over here, but the logic itself can be helpful in knowing that the queue is empty or not. So this is how we implemented our problem statement, that was of creating a queue and implementing the functions of enqueue, dequeue, display, that is accessing the elements of the queue, and then knowing the size of it and to check that this queue is empty or not.
Now let's talk about advantages and disadvantages of queue. First, we are talking about advantages. So it follows a principle of FIFO, or the elements are stored in a FIFO manner. That means, let's suppose this is a queue, and in this queue you have elements. So the deletion will take place from the front, right? And the insertion will take place from the rear side. So this is known as dequeue, the deletion, and insertion is known as enqueue operation. And both these operations are performed in a constant amount of time. So that is one of the advantages, right? And the insertion from beginning and deletion from end takes a constant amount of time. Plus, if we want to do peak first, peak last, all these operations are performed in a constant amount of time. And this is most widely used data structure when we talk about CP, that is competitive programming. When we talk about competitive programming, this data structure is most commonly used because of these features, that all the operations that are performed like insertion, deletion, peak first, peak last, enqueue, dequeue, all these operations are performed in a constant amount of time. Now let's talk about disadvantages. Since we are only able to delete or insert from the front and the rear, that means deletion from front and insertion from the rear. So the restriction of insertion or any manipulation, right? We have a restriction over these, right? What these operations, insertion and deletion. So this restriction is always there, and so this data structure, that is the queue, is not much flexible, right? We are fixed. We can delete and insert element in a fixed pattern or in the FIFO manner. Thus, it's not much flexible. Now let's talk about linked list. Let's understand what is linked list. It is a linear data structure. That means it is storing its elements, or the elements are stored in a linear fashion. Now, if the elements are stored in the linear fashion, that means all the elements can be stored as per the memory availability. Now, what happened in array, right? If we have this memory location, that means if we have a 16 bytes of size available in the memory, only then we can store four elements here. If the chunks of memory, right, there were, let's suppose 8 bytes here and 8 bytes here, and we want to store these 16 bytes of memory or 16 bytes of elements. That means there are four elements in the array. We want to store those four elements in the array. We cannot. Since elements can be stored as per the memory availability, that means in linked list, we can use these chunks of memory, which was the problem in array, right? And that was resolved by linked list. That means we can use these chunks of memory. Now, if your memory is available, That means if your memory is available in chunks, we can still use the memory efficiently. Now, this is one thing, right? Now, these two things are clear to you guys. Now, the third thing is that you can access elements on a linear fashion, or you can access elements in a linear fashion only. That means if you have a linked list, let's suppose this is a linked list. We'll talk about this, why it is that I'm writing that. So now, in order to access this, you need to access all of these elements. Random access is not possible, right? So let's suppose if you want to directly go to this place, this node, it is not possible. You need to traverse all the nodes one by one. So in a linear fashion. So one by one, you will go here, then you will go here, then you will go here, then finally you will go here and access this node. Now, like array, like array, if you have this linked list which is of in which you are storing integer values, you can only store, that means the data stored in all the nodes will be of type integer. Okay, you cannot, there is no such scenario where if you want to store a float in this and int in this, that will not be the case. Okay, so you can only store homogeneous elements which is similar elements. So in arrays, there was one more problem associated when we are using arrays. That means the size was fixed. So now in this, the size is dynamic. That means if you have four elements to be stored in a linked list, you can store them without wasting any memory or without having the condition where you cannot store more than four elements, right? So if you want to store eight elements, you can store. Again, without wasting memory or without underutilizing your memory. Okay, or you can also let's suppose if I am saying in arrays the size was 4 and I want to store 8 elements, that was not possible. But here that the size is not fixed, it is dynamic in nature. Now we can easily insert and delete elements in the linked list. Now what you want to do, we want to insert an element in a linked list, right? We just need, let's suppose we want to insert a link node in here. So what we are going to do, we are going to just remove this link, add a node, link this node to this and link this node to this. That's it. So with the manipulation of single link, we were able to insert a node, which was not in the case of arrays. We need multiple swaps. Now, similarly, if you want to delete this element, right? So now let's suppose that we want to delete this node. Again, with the manipulation of single link. Earlier it was linking to this, now it's linking to this. That's it. With the manipulation of a single link, we were able to insert and delete a node, which was not in the case of arrays. We need multiple swaps. And also we need to keep this thing in mind while we are inserting, that there is a size available. Let's suppose if four elements are there already and you want to insert a fifth element, that means even if you're swapping it, the fourth element that is there, the last element will be lost. That should not happen. Okay. So again, now there's one more thing that is associated with linked list and which is very important, that the root node, that is this node, is the key. Right? What do you mean by this thing? That this is the head of the linked list. That means if this head is lost, right, this is the pointer which is pointing to the first node, and this is the guy who is responsible or who makes it easy for us to traverse through the entire linked list. So we always keep the track of our head node, and it is generally termed, or root node is generally termed as the head node, right? And if head node is lost, your linked list will be lost. Okay, now if this head node is lost, your whole linked list will be lost. So you always keep track of this node, and even if you want to traverse, you always store this head in a temporary node and then change this temporary node, not this. It will always point to the first node of your linked list. Now let's talk about applications of linked list. So as we have already seen that if the memory chunks are available here and there, let's suppose 4 bytes are here, 4 bytes are here, 4 bytes are here. So we can use these in order to store four or three elements, right? And we can link them later on. So if you have a system wherein your memory is very limited, right? And you want to, memory is limited and you want to use that memory to its full extent, right? It is suitable for those applications or the condition where your memory is very limited. So you can easily go for linked list. Also, we have seen that since there is not much manipulation required, right? When you're trying to delete or insert an element, let's suppose you are trying to insert a node, what you will do here, you will manipulate this link, you will link this to this and this to this, right? And then what you're doing with the manipulation of a single link, you were able to insert the element. And same goes for deletion. If you want to delete it, you just have to manipulate this link and you are linking this node to, obviously, in this case, you are linking it to this node. So with the help of a manipulation of a single link, you are able to insert or delete the node. So it is the application which requires frequent insertion and deletion operations. It is also suitable for those applications. You can easily go for linked list because you know you will be saving a lot of time as compared to arrays. Now let's talk about types of linked list. So we have three types of linked list. We have a singly linked list, we have a doubly linked list, we have a circular linked list. Now let's talk about singly linked list first. So in singly linked list, there will be a pointer which is always pointing to the first node, right? That we have already seen. And that pointer is known as the head, or you can say the root of the linked list. And it is very important that you do not manipulate this head. If somehow you have manipulated this head, then you will get undesired results. Okay, so now this is how your node looks like. This node contains two parts, right? There are two parts associated with this node. One is the data part, another is the link part, or also known as the next. So this data contains the value, that is the homogeneous nature. That means if you're storing an integer value in this data part, you will always store data integer value in this data part. So this is what you store. Let's suppose you're storing 5 in it, right? So this is the data part. Now there will be some address associated with this singly linked list, right? Let's suppose it is 1000. Obviously, it will be hexadecimal number, but for simplicity, I'm taking this number as an integer. So now, and this address will be, or the reference will be stored by the root node, which is 1000. So this address is here. So now this link will always contain the address of the next node, that is this node. This will obviously have some address. Let's suppose this have 2000. So 2000 will be stored in this because this is pointing to this node. Okay, so similarly this node will also have some data. Let's suppose it is 10 and it will be pointing to the next node, which is, let's suppose the address of this node is 3000. So 3000 will be here, and this will contain also some data, that let's suppose 15. And now since this node is not pointing to anything else, we will store null in it. Okay, done. This is how your linked list, singly linked list looks like. So you have this data part and you have this address part. So these two parts will be always there when you're talking about a singly linked list node structure. Okay, so also this pointer that is pointing to the first node is the head pointer, and your last node will always contain next. In the next part, it will always contain null value. So this is how your singly linked list looks. Now let's talk about doubly linked list. If you talk about doubly linked list, there are two pointers or two things associated with it. So obviously this head node will always point to the first node that is there, right? This is the first node. And this will again be the key or the root of the linked list, or this time around doubly linked list. So this will store the previous address and this will store the next address. So in this case, there is no previous address, so it will be null. And this will contain always the data part, which will be again homogeneous. So if you are storing integer, all of them will contain integer. So in this case, let's put a value in it, 20 and 30. Done. Now what happens after that? Let's suppose now this is its previous is null. What about its next? So it will have 1000 in it. Let's suppose the address of this is 2000 and the address of this node is 3000. Now again, Just like we saw in single linked list, this will always contain null. Okay, the previous part. So you have next part. So this next part will always contain null, and you have this previous part. You have this previous part. You have this next part. So then let's first see how we can move in the forward direction. Now there was one drawback with singly linked list, that you can always move in a forward direction. So only one direction. You can move only in a single direction, that was in the forward direction. There is no way you can move in the backwards direction. So doubly linked list avoided, or mm, it rectified that problem with the help of this previous and next links. So previous links will always go help you to traverse in the backward direction, and obviously when you have this next in place, it will help you traverse in the forward direction. So now what happens, this, or let's first talk about the next links. So obviously now this node is pointing to what, 2000, so 2000 will be stored in the next part. So again this will be stored in 3000, and this will be storing finally the null values. Okay, done. But uh, what about the links which help us to move backwards? Those are previous. So it will point to the previous node, which is nothing but 2000. It will point to its previous node, which is nothing but 1000. It will point to its previous node, which is nothing but, in this case, it is null, because it is not pointing to anything else. So if we observe carefully, so there are two things that you should keep in mind, that the first node, its previous will always contain null, and the last node's next always contain null. So previous helps you in moving backwards, which was not possible in singly linked list, and next will always help you move forward, which was obviously the scenario in the singly linked list as well. Now let's move on to the circular linked list. So in circular linked list, again, this is the head node or the root node of the linked list. In this case, it is the circular linked list. So again, this node part will contain two things, the data and the link. So data will be, let's suppose data is 10, 20, and 30, right? Now this will have some, obviously some address. Now let's suppose these are the three addresses. Right? Obviously, there will be hexadecimal addresses, but yes, for simplicity, I'm taking this as an integer. So the link will contain the address of the next node, which is nothing but 3000, 2000 in this case, and 3000 in this case. But what happens in the circular linked list? Now, the last node, right, will point to the first node that is there. So the first node that is there is at location 3000. So you will store 1000 in it. Now you might be thinking, sir, this is similar to singly linked list, but the only thing that is different in this is that the last node in singly linked list was pointing to null, and in this case the last node is pointing to the first node. Is that correct? Yes, absolutely. Okay. So the last node is pointing to the first node in circular linked list, but in terms of when you talk about singly linked list, at that time around, this will be null. In this case, in circular linked list, it will always point to the first node, and head will always point to this node, or it will always store the address, that is 1000, and it will always point to the first node of the linked list, be it in any of the linked lists, be it circular, be it doubly. So again, it will store 1000, or be it singly linked list, it will store 1000. That is the first node. So with this, we are done with the types of linked list. So there are three types of linked list. One is a singly linked list, another is a doubly linked list, and the last is the circular linked list. So the only difference between singly and doubly is the last node, which points to the first node in the circular linked list. Now, in doubly linked list, it is similar to singly linked list. That means it has some features that means we can move forward, but it has some extra features with which we can move backwards as well with the help of its previous part. and with the help of its next we can move forward. It was in the case of singly linked list, and it was a new feature which was added to the doubly linked list, with the help of which we can traverse backwards.
Now let's talk about the implementation of linked list in Java programming. So before going ahead with the coding directly, let me tell you the problem statement of the program which we'll be implementing. So here you have to create a linked list and then implement it using the various concepts of classes and methods which are predefined in the packages and libraries of Java. And then we'll be implementing certain functions on it. Functions like after the creation of linked list, we need to insert elements into it. And then we have to insert the elements at the beginning of the linked list, at the end of the linked list. Similarly, deletion process will also see how to delete the elements of the linked list. And then we'll write a code to display the contents of the linked list. And similarly, we'll explore various other methods like how to, look for or search for any given element in a linked list, and also how to, uh, if at all, suppose you want to transfer the content or all the elements of a given data structure to any other data structure, like from stack, you want to copy all the elements to the linked list, or from linked list, you want to copy to stack. So how can you do that? There is a predefined method for that as well for linked list, and that how to use that method we'll see that as well. So that's the whole idea of the code which we are going to write for understanding the linked list implementation in Java programming. So let's switch to the IDE, that is the Eclipse IDE. So here you can see that I have already created a class LList, and there is a main method already defined, public static void main string args. In this itself, I'm going to create a linked list and then perform all other operations on the given linked list. Now, to create a linked list, you need to understand first here that uh, list is a class which is already defined in the Java packages, and that belongs to your collection framework. And to create a linked list, there is also a class called as linked list, of which we'll be creating an object, and that's how we'll create a linked list. So let's see how is that done. So as I said, linked list is a class. L1 suppose equals to new. Okay, again here, like in the stack data structure, we use the type of data you want to store in the linked list or the stack. So similarly here also you have to define the data type for the elements which you will be storing in the linked list. So here in this linked list, suppose I want to store integer elements. So integer will be the type here. Then name of the linked list, that is L1, which is equal to new. Again, new keyword is used to allocate space for the given object or allocate memory to the given object. New, and then linked list. And again, the two less than and greater than signs, and then round brackets, and then semicolon. So here we have defined a linked list L1 or created a linked list L1 using the linked list class. So let's see what's the error over here. Sorry. Okay, so you have to import java.util package, guys, because this linked list class is inside this java.util package. So you have to import either java.util.star, or you can write directly java.util.linklist also. So yeah, once that is done, the linked list is created. That is, you have created an object L1 of the class linked list, which contains elements of type integer. Make sure you provide here the wrapper classes for each data type, not the primitive data types. That is, you should not write here like this int. You can see it gives an error saying that there is a syntax error, insert dimensions to complete reference type. It means what? That the basic or the primitive data types are not supported. You have to provide the wrapper classes. That is, for every data type, there is a class defined in Java programming. So you have to use that class. Now, once this is done, we have to, next step is we have to add the elements to this linked list. To add the elements to this linked list, there are methods already predefined in Java programming. And what are those methods? Let's use that L1 dot add. So add is a method. You can see here the various, options which are being provided. So you can add an integer over here. Then there is add at particular given index what element you want to add. So we'll explore all these. Let's see. So here I'm suppose trying to add 3. Okay. So this will be the first element that will be added to the linked list. Now suppose I want to add another element, maybe 7. Okay. And then another element, maybe uh, 10. Okay. So these 3 elements I added to the linked list. So this is how you will add the element to the linked list. Now, there is another one more function which is related to addition or insertion of the elements to the linked list. But this is when you want to update something, like you have added at location, like first you added 3, that is at 0th index, then 7 at the second first index, 10th at the second index. So that 3 elements you have added. Suppose at some given index you want to update the value now. So for that you can use add. And then the second one, add int index and integer element. So here you have to add the elements and provide 2 parameters. One is the index at which you want to add, and the second one is what element you want to add. So this is generally used for updation. Like you have inserted already some value and later on you want to update that to a newer value in the linked list, then that this is the function which you'll be using, or the method you will be using. This method, that is add an integer and integer element, 2 parameters, one, this returns void as a return type. But the add methods which we already used for adding 3, 7 and 10, it returns boolean, that value, that is true or false. If the addition is successful, it returns true, else it returns false. So we can use this one here. So suppose at location second index, I want to update the value from 7 to maybe 6. Okay. Okay, until unless we print this, you'll not be able to see it. So I'll tell you also how to iterate over the elements of the linked list. That's the different thing. I mean, we'll do it later on. First, let's understand the primitive operations here. This is done. That is, the insertion is done. Now let's understand how to remove the element from the linked list. Okay, to remove the element from the linked list. Okay, so I'll put a comment over here. This is adding elements to linked list. Now we'll see how to remove elements from linked list. Okay, so let's see how to do that. So again, L1 dot remove itself is a function which removes the elements from the linked list. Okay, so just write L1 dot remove. It's going to remove the element from the linked list. Or there are other functions also, like no, you want to remove from the first, or you want to remove from the last of it. So that also you can do. So you can see here all the methods are being listed. That is, remove last is also there. You want to remove from particular given index, then from there also you can remove. So let's use a remove first here. Okay, so it will remove the first element of the linked list. If I suppose I want to remove the element at the second index, then you can provide the index number over here and it will remove the element from that particular index only of the linked list. Okay. Similarly, L1 dot, you can have remove last as well, to remove the last element of the linked list. Okay, so these are the methods which we'll be using. The very simple, very easy inbuilt methods which you can directly make use of. Guys, I'm not saying that you cannot write you know, a complete linked list implementation on your own. We'll do that as well. But as of now, you can use inbuilt methods also, which are predefined in Java library. And that's what I'm doing right now. That is using these predefined methods. It is adding, removing, and all that. Okay, before going to the next any other function, let me just tell you how to access the elements of the linked list, how to iterate over it. Okay, so again here the concepts comes is of iterator class to make the elements of the linked list, or to make the linked list iterable. So there is a iterator function which is defined inside the iterator class itself. So we'll make an object of iterator class, and over this linked list we'll call the using this linked list L1 we'll call iterator uh, method, which will make this linked list iterable. So let's see that what I'm telling you. Iterator. Okay. So iterator it is equal to it is a object for iterator class. Okay. So L1, that is the linked list dot iterator. Okay. And then semicolon. Done. So this makes the class iterator. Okay, it's again, okay, you have to import this as well. That's why I said you can directly do java.util.star over here. You need not do it again and again for every single class. You don't have to import that. But okay, no issues. The Eclipse IDE has itself figured out for me to provide that import statement. So I'll go ahead with that. So yeah, now in this, what I should do is again use while loop to iterate over it. So while there are next elements in the linked list, like next meaning, we'll start from the first and keep checking, is there next element, is there next element, is there next element, and until there are next elements in the list, it will keep printing it or keep accessing it. So for that, the while loop is being used. While uh, it, that is it, the object of iterator class, dot has next. So this tells that is there next element into it or not. If there is, then I'm just going to print what? It's going to print it dot next. So it will print the next element in the list. Okay. Let's see. So what I'll do is I'll just comment few lines here to just tell you that exactly how it works. So let's see right now, just uncommented lines are that I'm adding these 3, 7, and 10, and I'm running over it, accessing the elements 3, 7, and 8. So let's see what is being displayed over here. So you can see 3, 7, and 10 is being displayed. Again, I'll put a little bit of formatting over here to make it little representable. So yeah, 3, 7, and 10 is successfully inserted in the linked list. Now I'll add at second location 6. Now let's see which one is being updated from here. So you see here at the second location 6 is inserted. It means what? 0 first and then second. This was the second location, second index where 6 is inserted. And the elements after that are shifted one step ahead. So this is used for inserting it somewhere. Getting it? So that's what I said. So later on, suppose you've created your linked list and later on you want to update something, you want to insert somewhere in between some elements. So that you can do using this add different variation of add method with having two parameters. One is index number, other is element which you want to insert. Now let's see the remove one. I'll uncomment this again, and so that you can figure it out. So let's see one by one what is being exactly removed. So if I run this, so you see here it remove at the second index, that is we inserted 6 at the second index, right? So it deleted that. It's only 3, 7, and 10. Now if I say remove first, so the first element should be deleted, that is 3, right? So let's see, is that element being deleted? Yes, it is deleted. 7 and 8 is left. So remove first deletes element in the linked list from first. Now last meaning 10 should be deleted according to the current linked list elements. So let's see that. So yeah, 10 is deleted. So only 7 is left as of now. Okay. And as we are able to see this, all these elements, because this particular code is working fine. That is, we have created the list, linked list iterable so that we can iterate over it and access each and every element one by one. Okay. So till here it's clear, I guess. Now let's try to see the other methods which how we can implement over it on this linked list. And those methods are to search the elements into it, and also to find out the size of the linked list. Okay, so let's see now how to find out the size of this linked list first, and then how to search the element, I'll tell you. So this is the closing of this while loop. Okay, now after this, so to know the size of the linked list, there is a simple function that is called as size. So L1 dot size is what you can call it over from here. Now let me just comment out these lines so that it should not remove everything, okay, from the list. Let's have some elements in the linked list. That's the reason, then only you can get the size. So you can see here uh, it prints the size over here, that is 3. So this last element which you are seeing over here is your nothing but the size of the linked list. So you can see I printed in the next line. So 3 over here is a size. There are 3 elements only, 3, 7, and 10. 6 we already deleted by this remove statement. So that's how you'll find the size. It's easy, right? So nothing to do. Now let's see how to search an element. So to search element in the linked list, there is a function or a method called as contain. Okay. So how to call that? That returns a Boolean data type. So we'll store into this b1 is equals to um, we'll call on L1 dot contains. So you can see here contains is a thing. Now in the bracket or in the parameter, you have to pass what value you are looking for. Suppose I'm looking for 7. Okay. And then I'm going to print this b1. So as it returns a Boolean data type, this contains method. So it will tell that if the element is found, it will return true. If not found, it will return false. So b1 will be true in this case because I'm looking for 7 and 7 is already in the list, right? So it should say true. Let's see that. So when we execute it, it says true. If suppose I'm looking for something which is not there, like 11, then it should say false. So that's how the contains works. So it returns true and false. It doesn't returns the index number or anything of that type. So for that, you have to write a separate code. But simply if you want to know that a particular element is there or not, just search it. Then this is how you can do it. Now, one very important thing which I'm going to talk here is related to linked list. That is, Java provides a very good method support that is called as add all. Suppose you have created one data type or data structure which is having certain elements, and you want to create another or shift that data structure to any other data structure. Like you have stack and you have elements over there. Now you want to shift all those elements to a linked list. There is just one method using which you can very easily do it. I'm going to show you that now. So let's see. So what I'm going to do here is that copy contents from, or I can say better, elements from stack to linked list, or from one data structure to any other data structure. I'm using stack and linked list here, but from any other data structure, you can copy it to linked list. Okay. So let's see how it is done. So first we'll create a stack, right? Let me create a stack. So that is how to create a stack using stack class. Okay. I'm going to use it of string type. The elements in the stack are of string type. So it is stack s1 equals to new stack and then semicolon. Done. Yeah, it will ask me to again import java.util.stack. So yeah, we'll do that. Now let me also create one empty linked list. Okay. So linked list L2 this time. Okay, this linked list should also be of type string. Okay. Let it be L2 equals to new and linked list. Right. Now let me insert the elements in the stack first, and that all the elements I'll copy it to linked list directly. Okay. So to copy the elements from stack to linked list, I should insert some elements. So I'm doing that. How to do that? Using push operation. And then as it is a string data type, so I have to push, suppose, hello. Okay, wrong spelling of hello. This is how it is. Then suppose I want to push the next element to be uh, hello everyone. Sorry. So right. So two elements I have pushed hello and everyone to stack. So a stack contains these two elements. Now I want to copy all these elements to a linked list L2. How to do that? So you can call L2 dot add all. So you can see here there are no, so many options coming up. So you can take anyone, add all, and you have to add from where? Stack to this linked list. So everything from the stack, all the elements from stack will be copied to L2. Make sure these two data structure stores the element of same type, because type conversion will be a problem there. So only this is the check which you have to do. And apart from that, you can copy all the elements from stack to linked list successfully here. Let's see, let me iterate over it. So to iterate, we have already written a code over here, right? I'm just copy pasting the same code. to save time, guys. So this let it be IT1 this time because it will give an error if I'm using the same variable. Okay, this will be over L2 because L2 is a linked list here. So let's see what's the output. So you can see here, I'm iterating over L2, right? And L2 is the linked list. But I have copied the elements to this linked list from stack, that is S1. And S1 had hello and everyone, but I'm printing L2 where it's printing hello and everyone. It means what? That the elements have been copied from stack S1 to linked list L2. So this is all in the implementation of linked list, guys. So we have studied, or we saw how we can add elements to the linked list, then how we can remove the elements from the linked list, how you can remove from the first and from the last, then how you can make the linked list iterable, that is you can iterate over it one by one and access each element individually. Then we also saw how you can implement searching, that is contains method can be used to look for any given element, is it present in the linked list or not. Then you can copy the content of any given data structure to any other. You can use array list also here. There are other data structures in Java, right? Array list can be used. I have used stack over here to demonstrate the example to you. So from stack, I have copied everything to the linked list. So this can be done. Then to do the size of the linked list also, you have a method, predefined method called as size. So link using dot operator on the particular linked list, you can call all these methods and you can successfully implement it. Now let's talk about the implementation of linked list with a different problem statement. That is, we are going to talk about the circular linked list now. That is, its implementation in Java programming will be discussed. So the problem statement states that you have to create a circular linked list and implement it using the concept of classes and objects in Java. Then certain functions we will create it over that linked list. That is how to insert the elements into the circular linked list, how to delete the elements from the circular linked list, as well as how to iterate over it to display the contents of the linked list. So let's go to the IDE and try to write down the code. So we have come to the Eclipse IDE here. So I'm using Eclipse, or you can use any other IDE whichever suits you. The program remains the same, guys. So here I've already created a class list, and which is having a main method, public static void main string args already over here. Now to create a circular linked list, I'm not going to use the inbuilt linked list method here or inbuilt linked list classes, neither the associated methods of the linked list class. I'm going to create a linked list by the basic concepts of classes and objects which is there in Java. So for that, I should create so in this outside the main method, I'm going to create another class over here. Okay, and this class is suppose node, because each element of a linked list is referred as node. Okay, so I'm creating the class also as node. You can give any other name here. So what this node will consist of? So every node of a linked list consists of what? Two things. Singly linked list if I talk. So circular linked list I'm talking about over here. Single circular linked list. So in that case, it will have a data, the value of the linked list. Every node will have a data and then a pointer to the next node. So two things will be there. So that's what I'm going to define over here. So in data, okay. And the next one is going to be your next node reference. That next will contain the another node. So it should be of type what? Node itself. The next variable which is pointing to the next node of the linked list will also be of type node itself because it is pointing to another node. So its type should be node, right? Now we'll initialize this using the constructor of the node class. And in this constructor, I'm going to pass the value for this data. That is, each node will have a data, right? So what value that data should be having, that will be passed from here, and let it be also data. You can give any name, doesn't matter. So this is how we create a constructor of a class. That is, the name of the class should be same, and you can use parameterized constructor, default constructor. I'm using parameterized constructor, meaning I'm passing one parameter to this constructor. So it is parameterized. If I'm not passing any constructor, it is default constructor. So here, what I should do here is I'll initialize this data. So for this, I'll be using this keyword. This dot data is equal to data. Okay. You can initialize next also over here, but next, no, already it will be pointing to null. So you need not also, you can skip that as of now. So this is the node creation part is done. So I created one node, which is having data and the address to the next node, which is in the next variable. Okay. Now let's create certain functions in the class. So outside this node class now, node class ends over here. So, okay. Outside this node class, I'm going to create different methods. So first method is to insert the element into the linked list, circular linked list. Okay. So, okay, one more thing here. As we are talking about circular linked list, the difference between normal linked list and circular linked list is only that the last node of the linked list will be pointing to the first in case of circular linked list, right? So we should have a pointer that should connect this, right? That is, the last node should be pointed out somewhere. So what you can do is, here itself we can have another variable that is of type node itself, which is your tail. Okay, that is, this tail will tell that it is the end of the node or beginning. Initially, when there is no element in the linked list, it will be pointing to the first itself. Okay, now let's go ahead and try to implement the other methods. So we'll implement the next method, that is inserting the elements to the linked list. So it will be of return type void and maybe insert elements. You can give E capital element. Okay, the element which you have to insert. Okay, so let that be maybe insert int ELE, or I can write data itself. So in this function, first what you have to do is create a object of the node class. Okay, because that is the node which you are going to insert finally, right? Which will have this data and also a pointer to the next node in the linked list. So this will be node, maybe let it be new node. Okay, this is equals to new, and then I'll be using the class name, that is the class constructor here, and the data which is passed while insertion, that is while calling this insert element, that is in data over here, that will be given to this node as its value. Okay, now once it is inserted, what are the condition check we have to do? So there is two conditions. First one is that if suppose the linked list is empty, the first data you are inserting here, then in that case your head and tail pointer both will be pointing to the beginning itself. Okay, we have to create head pointer also. This should not be here. Okay, one second. Inside this class, we'll have two pointers, head and tail. Okay, so this head and tail is nothing but these are the two reference variables which are pointing to some node, okay, in a linked list. So initially they are null, meaning they are not pointing anywhere. When you insert elements to the linked list, your head pointer will remain same. That is, the head pointer will point to this new node if there is no elements in the linked list. This is the first element being inserted. Then your head and tail pointer both should point to that particular new node, right? That's what I'm going to do. So you'll check here first condition, that if uh, head is equal to null, then in that case, what you should do is, it means it is the first element to be inserted. Then in that case, your head of the linked list will also point to this new node, right? Your tail will also point to this new node, correct? And as it is a circular linked list, the tail of the new node, that is new node, should point to also the new node itself, because there is only one element and it is a circular linked list. So that one node should point to itself, because it's a circular linked list, right? Are you getting the picture? And there is only one node, so that node should point to itself to make it circular. So what will be there? Tail is now equal to this new node, so tail dot next will be equal to also this new node itself. Getting it? What is the else condition? Else condition is if it is not the first node to be inserted in the linked list. There are already some nodes inserted in the linked list. Then in that case, head will be pointing to the beginning of the linked list, tail will be pointing to the end of the linked list, right? And new node will be inserted at the end. In that case, your tail pointer will change only, correct? So what will happen? Now this tail will become the new node which is inserted. So your tail will become the new node, okay? And tail dot next will be your new node first, and then tail itself will also be pointing to new node. Now the next of the tail now. Earlier tail was the end. Now new node is added there. So tail next is the new node. Now tail is shifted to this new node because now new node is the last one. To make it circular, this new node should point to head. So new node and tail is the same thing now. So tail dot next will be the head node. So that's what I'm going to write here. X is equal to head node. Okay. So this is your insert element or insert function in the insert method in the linked list. I hope it is clear to all of you. Now let's create another function, that is your display. Void display elements. This will also not take anything as an input, as a parameter. So in this display elements, what you have to do? So okay, there is again a condition check. If there is nothing to display, linked list is empty, then definitely it will not display anything. But if there are elements, then it should display. So for that, you'll have a condition check. If what should be the condition check? If your tail is equal to null, then in that case, your linked list is empty. So in that case, it should print a statement saying that uh, circular linked list is empty. Okay, and nothing to display. Nothing to display. Let it be more informative, right? Okay. So else condition. What will be the else condition? It means else meaning there are elements. Tail is not null. There are some elements into it. So in that case, it should display that. And in that case, what you do? You have to iterate over it again, right? So to iterate over it, you'll use do while loop over here. So what we have to do basically is, I'll write the while condition also, but while there are next elements into it. I mean, while the tail is equal to, or you can say not equal to, head, right? When tail will point to head, it means you have to stop. You will start from the beginning, go till the end, and as it is a circular linked list, end will point to the beginning again. So once you started from beginning and you reach to the beginning again, you have to stop the accessing. You have to stop the iteration, right? So that's what I have written. So you do the iteration or you do the process of accessing the elements until unless you reach to the end of the linked list. That is when tail points to the head. That's the end of the circular linked list. That you came back to the initial position, that is the head. And what you have to do here? Access the elements. So to access the elements, I'll just print it out here. So what you have to print over here is that the node data value, right? So let the node be n1 dot data, but this n1 has to be defined over here as a type node. So node n1 equals to new node. Okay, or you can just skip this part. You can have node n1, that's it, will be enough. So you can use n1 dot data. So this will be pointing to your head node, so that we can start from head and go till the tail. So let n1 point to head itself. So we'll print this. And now as we have to go to the next element, and in linked list we can't use for loop or something or increment the pointer to 1 plus plus and it will go to the next. We have to go with the pointers. We have to go with the next variable. So in this, what you have to do, n1 will be equal to n1 dot next. So n1 will be pointing to the next of the n1 now, and every time it will keep on printing till where it should print, as it's already here, that is till when the n1 dot next is not equal to head. Till then you have to keep on, because it's starting from head, it should go till head only, and once it reaches there it should stop the accessing of the elements. So this is your display element function. Now let's call all these functions from the main method, then we'll talk about the delete. Okay, so in this you have to make a object of the class, that is the class name is your list. So list, let the linked list be list1 is equal to new l list. Okay, using this list1 we'll be calling the two functions which we have created over here, that is your insert element. So what we are going to insert here is suppose 2, and then again let's insert one more value into this list1 dot insert, and here we are going to insert this time is 7. I'll do one more list1 dot insert, and I'm going to insert 8. Okay, now let's call display function on it to see how it works. We'll save it and then run it. So you can see here 2 and 7 is being displayed. Okay, 8, 2, 7, 8 is there. Okay, something is missed out. Let's see what is that. It starts from the head tail and it will go till n1 dot next, it is not equal to head. Okay, so what went wrong is that let's try to figure out that. So okay, display elements, we have created a node n1 and tail is equal to null. Okay, here it should be also, and head should be equal to null, because not just tail equals to null, but also if head is equal to null, then this should be printed. Let's see, we'll see the output. So let's 2 and 7. So okay, let's explore it further. Till n1 is equal to n1 dot next, while n1, okay, so here is the problem. So while n1 is not equal to head, because n1 dot next is not equal to head, meaning it is skipping the last element. That's the reason 8 was not printed over here, right? Because it was checking with the next value. So the current last is being skipped. Now let's see, it should give us the output. Yeah, so you can see 2, 7, and 8 were the three elements which we have inserted here. So this is the logic of printing or displaying the elements, accessing each element of a linked list. Here I'm not using the inbuilt linked list class to create the circular linked list. Okay, not the inbuilt methods as well. You can create a simple linked list also using the same logic, but here I have created circular linked list to demonstrate you. Now let's create another method to delete. Okay, so this was the method ends over here. Let's have a void delete method, delete elements. Okay, it will not take any parameter. What should be the logic of deleting elements into it? So the logic will be here is that you have to just check that is there only one element in the linked list, in the circular linked list. If there that is the only one element left, then if you delete that, your head and tail both pointers will be pointing to null, because nothing is there to point to, right? And if there there is more than one elements or nodes in the linked list, in the circular linked list, then we can go ahead with a normal procedure. One more thing to keep in mind here is that when you delete node from linked list, it will be deleted, as it is a circular linked list I'm talking about, it will be deleted from the beginning, that is head node itself, because tail and head both is pointing to the same, that is the first node, right? The last node is pointing to the first one. So the head and tail pointer is basically at the first node itself, right? So deletion will be from there. So these two things you have to keep concepts in mind and then implement this function. To implement this function, as I said, you have to check if your tail is equal to null. Then in that case, if tail is equal to null, it means what? Okay, I'll check tail is not equal to null. Sorry. then you should implement something, otherwise else. So if tail is not equal to null, meaning there are certain elements into it. So that code will go over here. Okay. Else part will be if there is only one element. Tail is okay. One more thing. Tail is not equal to head, right? Meaning the next of tail is pointing to head, not the tail and head are equal, right? Next of tail will be pointing to head in a circular linked list, but tail will be the last one and head will be the first one. But if they are not equal, then it means there are certain elements into it. If they are equal, they're pointing to the same thing. I mean, they are the same node, not pointing. They are the same node. It means there is only one that particular node. So in that case, head will be equal to tail will be equal to null, right? But if there are certain elements into it, then in that case, what will happen is that your head will point to head dot next and tail dot next will point to head again. Head dot next, that is the next, the head will be deleted now. So head dot next will be the next node that will become your head, and tail dot next will be now this new head because the first head was deleted. I hope this is clear. So this is your delete elements. Now let's call this over here. So if I call it list1 dot delete elements, let's see if it successfully deletes. 2, 7 and 8 is there. So it should delete one of the element and it should print. Okay, I should call display elements again after this to print the correct value. Display elements. So let's see what it prints. So you can see 2, 7 and 8 was there first, and then there is just 7 and 8, right? You can see the output. I will just expand it a little bit for you. 1 second. So you can see here 2, 7, 8 was the first display element output, and then 7 and 8 only because 2 is deleted, which is deleted from the head node. Although head and tail, next of tail is pointing to head because it is circular linked list. So always the deletion will happen from the head node. So head node will be deleted. So next of head node will become now new head node. Okay, and tail dot next will point to this new head node. That's what the logic we implemented here in delete elements. So this is how the working of the circular linked list is, or you can implement circular linked list. That is, to insert element, you have to keep a check that if it is a first node to be inserted, then the logic will be a little different, which we have seen over here. And then to if it is not the first node, then there will be little change in the logic that is over here. Then to display elements, we saw if there's empty list, there is nothing to display, then what will happen? And in the other case, when there are certain elements already, then you can just iterate over it and display it. We have used do while loop over here in that case. To delete the elements, you have to just check that uh, it should not be just one node which also gets deleted, and that is a different case. In that case, if that gets deleted, head and tail both will point to null. Else there will be a different condition which we already saw. So this is all about the implementation of your circular linked list using the different concepts of classes and methods in Java programming.
Now let's talk about the advantages and disadvantages of linked list. First, let's talk about the advantages. So obviously, as compared to array, right? When we talked about arrays, they were fixed in size, right? We need to specify the size in the subscript. So fixed in size, which is not in the case of arrays. It is dynamic in nature and you can add as many nodes as you want depending upon your requirement, right? So obviously when you have that uh, independency over the size, you will never, there's no chance of wasting any memory, right? So if you require 4 nodes, you will use 4 nodes. If you require 3 nodes, you will add 3 nodes only. So in this way, the size of the linked list is entirely dependent upon your application. What are the things that you require, you make them, that's it. So you will not be wasting your memory and you will be utilizing your memory very efficiently. So this is the reason why this is written over here, the efficient memory allocation. How you are doing efficient memory allocation? Let's suppose you have chunks of memory available here and there. You can link them together and allocate the memory and use those memory location for storing the data, right? So memory can be used efficiently. Memory is not wasted. It is dynamic in size, and it is very easy to insert and delete a node in a linked list just by manipulating a single link, as we have seen earlier. Just if you want to delete this, you just manipulate this link and just point this link to the next node, which is after this node. That's it. You are done with the deletion operation just by manipulating a single link. Similarly, when you're talking about insertion, at that point, you just if you want to insert at this location, you remove this link, point it to this, and then remove and point this new node to this node that is there, that was already there. Again, we are manipulating a single link. Okay, just the manipulation of single link here, that is required for insertion, and a single link here that is required for deletion. Now, when we talk about disadvantages, one of the major disadvantage is that you cannot lose your head, right? The head node that is pointing always to the first node, either in a singly linked list or a doubly linked list or a circular linked list. This head node cannot be lost. If this head node is lost, or if it is manipulated, right? If the head node is lost or manipulated, the whole linked list will be lost, right? Let's suppose this is your linked list, and somehow, right, if this is the head node and somehow you made it traverse to this particular point, right? Now head node is pointing to this in a singly linked list. Now there is no way you can access these nodes, and you will get undesired results. Another disadvantage is that you cannot access randomly. So random access is not possible, because if you want to go at this particular node, you have to traverse through the first three nodes first. Why? Because this node knows the address of this node. This node knows the address of this node. This node knows the address of this node. There is no way you can directly go to this particular node. Random access that was there in the arrays, with the help of indexing, you can randomly access the elements. That is not possible in terms of linked list. And the address of the first node is known to the head of the linked list or the root of the linked list. Okay. So that head is pointing to this first node. Okay. So you cannot change or manipulate or lose, or you cannot lose your head, because the whole linked list will be lost. Okay. And the random access is not possible in linked list. Binary tree. Now let's talk about what is binary tree. So it is a hierarchical data structure. As we have seen in earlier data structures like arrays, linked lists, stacks, and queues. All of these data structures were linear data structures. But when you talk about tree, is a hierarchical data structure. That means it can have one or more than one children. Doesn't have to be explicitly two children. But when you talk about binary tree, therein you can have at most two children. That means if this is the node, and then it can have at most two children, or if this is a node, it can have either left child or the right child, or it can have no children at all. Okay. So this is a binary tree. And now this is known as the root of the tree. That means the first node is known as the root of the tree. And you cannot access elements or these nodes directly. Okay. So now this is the whole structure of a binary tree. Now there are some common traversals, right? How we can traverse through all these nodes. So one of the common traversal is pre-order, wherein you always, whenever you are on this node, you always print this node first. What is the value of this node? Then you go on to the left side and do the same. Then again you go on to the left side, then do the same. Print, go on the left side, print, go on the left side, and so on. Unless and until there is no left, then what you do is print that thing. Okay. Then after that, you will go on the right side. So pre-order follows print first, then go on to the left, then go on to the right. Similarly, post is saying that whatever is you have, print it at the last. So go on the left, go on the right, print at last. And in order says left, print, and write. So these are all traversals. We will also see one by one how we can implement it, and how we will also see examples based on these traversals. Now let's talk about the applications. If you have seen the file hierarchy system, wherein we have the root folder, and inside that root folder we have subfolders like music, and we have bin, we have files, we have program files, and all those things, right? So it is a kind of a hierarchical data structures, right? And explicitly here we are not talking about binary tree but generalized tree. Now, if you have binary tree, it has multiple variations, right? If you talk about this binary tree, so here you always have either the left child or the right child. When you talk about BST, the childs are inserted in the tree in such a way that on the left side it will be always less than the root, and on the right side it will be always greater than the root. So this is a variation. It is known as BST. So you have aerial tree wherein you don't exceed the height more than 2. So that is one more variation. Then we have red black trees. So these are all variations of binary tree.
So now let's talk about the implementation of binary tree in Java programming. Before going to the coding, let us see what is the problem statement which we have to code for. So the program which we are going to write is about creating a binary tree, and creation of the binary tree will be done with the help of classes and objects and methods, the basic concepts basically of Java programming. And then we are going to implement a order in which the tree traversal will be done. Now, what is tree traversal? That is accessing each and every node in a tree. So a tree will be having nodes and edges, vertex and edges. So how do we access each vertex or each node in a tree? There is a order or a way to do that. The way in which we access each node is called as your traversal. Now there are three ways in which we can traverse each node of a binary tree. That is your in-order traversal, pre-order traversal, and post-order traversal. Before going to the actual implementation of it, let us see first what are these concepts all about. Like what exactly is in-order traversal, then what is post-order, and then what is pre-order. So let's take an example here and talk about first in-order traversal. So suppose this is the binary tree, okay? A simple binary tree. I'll name these nodes so that it's easy for us to refer them so that it's clear which node we are talking about. Okay, so this is your binary tree. Now, to traverse this binary tree, we have to use the concept of in-order traversal. In in-order traversal, what we should do is, first we should traverse the left child node or left node of a given node or in a tree. Then we should traverse the root node and then traverse the right child of a node. So for any tree, suppose this is your small tree with just one root node and then the left and the right node. So in in-order traversal, first you have to traverse the left one, then the root node, and then the right one. Okay, so let's see if I traverse this in an in-order traversal way, what is the sequence of vertices we get. So starting from the top, that is the root. So this is the root node, so we'll start always from this. So first we have to traverse the left child. So we'll go to the left first of this. Left of this is B, and this is also a subtree, right? So we'll go to the left of this also. Left of this is D. So first we'll traverse D because after D there is nothing. This is pointing to null. This is also further pointing to null. So there is nothing after this, right? So we'll end it here, where whichever is the leaf node, that is the last node in the tree. So D will be traversed. Okay. Next, coming back, we have to traverse what? The root node. So if I talk about this particular subtree, in this particular subtree, this is the left child, this is the right child, and this is the root node. So next, after left child, we have to traverse root node. So we have to traverse now B. After root node, what we have to traverse? The right child of it. And right child is nothing but E, this particular node, right? So we'll traverse E. Now this subtree is done. We'll trace back, that is we'll do backtracking and come to the previous one. Now all the left part of this particular node A is done. So now what should you traverse? The root node, that is A itself. Then we have to go to the right part of A. And coming to the right part of A also there is a subtree. In this now, which is a root node, this is a root node, this is left child, and on the right side there is nothing. So in this subtree, we have to again traverse first left. So left is F. So we'll traverse F. Now after F there is nothing, so we will not go further in the depth. Here itself it will end. So F is the left child of the C, right? So we'll traverse first the left one. Then coming back to the root node. Root node is what? C over here. So we'll traverse C. Then we'll go to the right side. Right side there is nothing, right? So we'll not be traversing anything. So this part is done. Now we'll go back to A, and already A is traversed. So the sequence was left, root and right. So this is the sequence you will get when you traverse it in order. Let me talk about pre-order traversal. Okay. In pre-order traversal, I'll talk about the same tree A, B, C, D and E. Okay. And this is suppose one more F. Fine. To traverse this now in pre-order. Pre-order is first you have to traverse the root itself. Then you have to traverse the left child and then the right child. Okay. So to traverse root first, we'll start always from the root node of the complete tree. A is the root node of complete tree, so we'll start from A. So first you have to traverse the root here. That is A will be traversed first. Then we'll go to the left of it. Left of it is this part, right? Now this is also a subtree. So again for this we'll implement this logic root left and right. So which is the root in the subtree? B. So B will be traversed first. Then which is the left one? D. So D will be traversed. Now once D is done, there is nothing after D, so we'll not go ahead. Once D is done, what is the right of B? E. So E will be traversed. So in this subtree, we traversed it in the order root, that is B, then left, that is D, then right, that is E. Now we'll trace back to A again. So we have already visited A because root was the first one to visit, and left is also done. Now we'll go to the right part. Right part, this is the tree, right? In the right part, this is a subtree, and which again will traverse the subtree also in the order root, left and right. So which is the root node here? C is a root node. So C will be traversed. Then left of it. Left of it is F. So F will be traversed. After F there is nothing. So we'll not go again deeper there. Edit there. And then what is the right of C? Nothing. There is nothing on the right side of C or right child of C. So we'll not go to the right child. That's it. So right part of the root node A is also traversed. So this is the order of traversal we get when we traverse the given tree in a binary tree in a pre-order traversal. Talking about the post-order traversal. In the post-order traversal, again the same example I'm going to take here. So A, B, D, and this is your E, and then coming here C, and this is your F. Okay. In the post-order traversal, what we do is we traverse the root node at the last, post everything. So first is left child, then the right child, and then the root node. Okay. So starting from again the root node of the complete tree, that is A, we'll start from here, and we'll go to the left first. So coming to the left side, this is a subtree. Now in this subtree, which is the root, this is the root, and this is the left, and this is the right. So in this also we'll go to the left first. So left is what? D. And after D there is nothing, so okay, we'll traverse D first. Then go to the right of, in this subtree, which is the right child, E. So after left we'll go to the right, that is E. Then we'll go to the root node, that is B. Once the subtree is done, we'll trace back, and now we have to go to right side. Left part of A is done, so we'll go to the right part of A now. Right part of A. In right part of A, this is a subtree. Now in this subtree also we'll follow the same sequence, left, right and root. So left child is F. What is the right child? There is no right child of C, so we'll not traverse anything. Coming to the root now, so root is C. So right child is also done. Left child subtree is done. Right subtree is done. Then we'll traverse the root node, and root node was A. So this time A will be traversed at the last. Okay, so this is a sequence we get when we traverse a given binary tree in a post-order traversal or in a post-order way. Now let's go and write down the code for this, how to write down a binary tree, as well as how to write down the code for all these concepts which we studied right now. Okay, so here already I have created a class traversal. So there's a main method in this already, which is define public static void main. Now to create a binary tree, so creation part of a binary tree will be done inside the main method itself. But there has to be some logics which has to be defined outside this class, and for that I'm going to define a separate class over here. So let's define a class node. Okay, you can give any name of this class. I'm giving it a node because it is easier to identify that there is nodes in a tree. You can give it a vertex name as well, or any XYZ name. So node, and every node will have what? A value, that is, which I named it as ABCD. So that is the value, or that is the key. So let's see that as a key character, and that will be of type character because it was ABCD. Now next is your, then there will be left child of it and right child of it, right, for any given node. And each left child and right child is also a node itself, right? So it will be of type node. So node left and right will be there. Fine. Now let us define a constructor for this class so that we can initialize these values. Okay. The constructor is going to take character key. Okay. And this dot key will be assigned to whatever key is passed while calling this constructor. Okay. Uh, that's it. You don't need not define the left and right to be null, because automatically when an object is declared but not assigned any value, the automatic initialization to it happens with null. So this is what we'll be doing in the node class. That's it. Now coming ahead, we'll define one more class, maybe tree traversal. Okay. In this class, I'm going to write down the code for pre-order, in-order, and post-order traversal. So there should be a first node that is called as your root node, right? Now let us define a method which will not return anything, void maybe pre-order traversal, and what will pass to this? Will pass the root node of every tree. Every binary tree root node will be passed here. It is a recursive call because you have seen that first we go to the root node of the whole tree, and then we go to the left subtree, and then again implement the concept of pre-order or post-order traversal there. Then go to the right subtree. So it's a recursive call on each subtree, right? So, and every time when we do the recursive call, we pass the root node of that subtree in this function. So it will be node n. Let it be node n itself. Okay. Now in this method, what we have to do is that there is a one check which you have to perform. That is, till when you should keep traversing. Till when the node n becomes null. That is, you reach to the leaf node. You reach to the end of the tree. So that is a check or condition check which you should put. That is, n should not be equal to null. Till it is not equal to null, that is till we have not reached to the end of the tree, till we have not reached to the leaf node, keep on traversing. And in the traversal of pre-order, what is the concept? First we should traverse the root node, then the left, and then the right child, right? So I'll traverse the root node. It means we have to print it as well. So I'll do system.out.println, and in this I'm going to print n dot key. Let us have some formatting over here to demonstrate. So let it be print itself, not println, otherwise it will go to the next line. Okay, so first we'll fetch the root node. So root node is fetched and it will be displayed with using system.out.println. Now again recursive call on the left subtree and then recursive call on the right subtree. That is what pre-order traversal is. So what we have to do is pre-order traversal, the same function will be called, and the parameter to this will be node n dot left of it. Getting it? And then pre-order traversal n dot right of it. This is the logic. So this is a logic or a code written for pre-order traversal of the tree. Now we'll come to the main method or our main class here. And in this, we are going to define or create the tree first, and then we'll see, call the method pre-order traversal and see is it traversing in a good way or not. To create the key, what we should do is you have to create, first is you have to create the object of the class tree traversal, let it be t1 is equal to new traversal. Okay, it's tree traversal. And then the constructor of this. And the constructor of this to what we should pass. Is there any constructor defined? No, right? So it's a default constructor. So will be like this only. Now using this T1 object, we will call all the methods. Fine. So let us call the method in this, that is tree traversal, method called as pre-order traversal. But before that, first we should create the binary tree, right? Creation of binary tree is very easy. Using this left and right child or left and right variable itself, we'll be able to create the tree. So first we should create the root of it, right? So T1 dot root will be equal to new node, and let the root child be as A. Okay, as we have defined it to be of character type, let's have a character over here. Okay, now T1 dot left of root. So root dot left is how we will refer. New node, and in this we should pass suppose B. Okay, meaning the root node is A, left of it is B. Now we'll go to the right of A, right of root node. So how we can go? T1 dot root dot right, which is equal to new node, and that value is suppose C. Okay, similarly now we'll go to the left child left. To do that, T1 dot root dot left is equal to new node, and in the bracket you can write suppose D. Okay, it should be new, right? Similarly, if you have to go to again right, so T1 dot root dot left dot right is equal to new node, and let that be as E. So we have created the tree something like the root node A, the left child B, right child is C, B is having two children D and E. Okay, so this is your tree. To this, now let us call the pre-order traversal. So how to call? T1 dot pre, well, small letters, T1 dot pre-order traversal. And in this you should pass the node. So what will pass here? The T1 dot root, which is root, right? So let's see what's the output we get. Okay, it's not showing any output. Let's check what went wrong. Yeah, so here we can see that it is key, not the spelling was wrong. K-A-Y is what I have written. So let's save it and check if it gives the output. So yeah, so this is your pre-order traversal of the tree A, B, D, E, and C. So what exactly was the tree? To see that, let's see. So we'll come back here, and the tree which I have created programmatically was A, B, C, D, and then E. For this, if we do pre-order traversal, what we should get? Pre-order meaning first we should traverse root node. So A, then coming to the left side the first root node is B, then the left child and then the right child, right? So left child is D, then E, then going back to the right child, that is C. So A, B, D, E and C should be the output. A, B, D, E, C is the output, right? So this is the pre-order traversal. Similarly, to do the post-order traversal and in-order traversal of the given tree, we should write the same function but in little bit of a different way. So I will just copy paste from here to save time and paste it here 2 times. Okay, so let's change this to pre-order to post-order traversal, and this will be your in-order traversal. Okay, and in the post-order traversal, the root node is traversed at the last, first left and then right and then the root node. So this statement will come at the last, that is after left and right child. In order traversal, what will happen? First left child is done, then the root is traversed, and then the right child is traversed. So this statement of printing the root will be in between these two statements. Getting it? Now let's call here T1 dot pre-order traversal and T1 dot route will be passed as a parameter. Similarly, T1 dot post order traversal and T1 dot route will be passed as a parameter. So let's execute this and check. Okay, we should give a next line statement here so that it prints in the next line. Okay, so we'll save it. So you can see here, this is the pre-order traversal. Then there is, okay, this is again pre-order. This should be in order traversal, right? Let's call it. So pre-order, in order and post-order. So this is what we get in case of the pre-order, post-order and in order traversal, and this is the code for it. Let me zoom it once. So I think it is clear to all of you. So once I'll revise it, we'll have a node class which will have a key and the left and the right child node. Key will be of type character, integer, whatever you want to store here. But left and right will be of type node itself because left child is also a node and right child is also a node. Then we'll have a constructor of this which will initialize the key. Coming to the actual function of pre-order. So you can define it in the same class in the entirely in one class itself, like this main class itself. You can do all these, but I have to differentiate it properly to write a well-defined readable code. I've written it in a different class. So pre-order traversal and the node will be passed whichever root node is there, which you have to traverse in pre-order. And there is one condition check which you have to do every time. That is, you have to keep traversing until unless you reach to the last. That is, the node starts pointing to the null until you reach to the leaf node. So that's a check here every time under if condition. Then in the pre-order, first root node, then left child and right child. In post-order, first left child, right child, and then the key. In order traversal, first left child and then the root and then the right child of the node has to be traversed. And then creation of binary tree is easy. We can create it just using this left and right pointers itself. So T1 dot root will be your first node, and then left child of root, right child of root, then left of root, then left of right of root. Similarly, you can keep on defining the left and right of given node, and you can define a complete binary tree. Make sure you pass here the parameter that only which is the type of the key which you have defined. Here I have taken characters. So you have passed your characters. You can take integers 1, 2, 3, 4 you will be passing. So that's how it is. And then these functions are called by using an object of the class. So that's all about your binary tree and the different techniques of traversing over the binary tree.
Now let's talk about advantages and disadvantages of binary tree. If you talk about advantages, we can represent data with some relationship, right? So this is the root node or this is the parent node and this is the child node. So that relationship, parent-child relationship is always there. And while you are inserting or searching an element or a node in a binary tree, it is much more efficient as compared to other data structures which we have seen. Now, if you talk about disadvantage, if you want to sort this binary tree, it is much more difficult, right? Because we can either go on the left side. This can be a tree. That means this is a left skew tree, or this can be the scenario wherein we have all the elements on the right side of the node. So this can be another scenario wherein we have this right skewed binary tree. So sorting is difficult and it is not much flexible, right? If you talk about this binary tree, we always have either the two children or one children or no children. There is no flexibility in terms of how you want to store it. Can we store another node on the with this root node? No, that is not the case, right? And we don't follow any restrictions like, okay, we always find this node. That is, if this is in root node, we always find an element which is less than this node on the left side or on the right side. That is of the greater element. So that flexibility is not there. Binary search tree. Now, what is binary search tree? So binary tree is an additional restriction, right? This BST is nothing but the additional restriction on binary tree. Like we have already seen the binary tree wherein at most we can have two children, right? It can be on the left side or it can be on the right side. Now, what are the restrictions on this tree? So the restrictions are that data That is, let's suppose this is 5 and these are another two nodes. Now the restriction is that if this is a root node, then you always will have the element that is less than your root node. So you can have 4, 3, 2, 1 on these sides, but you cannot have 6 on the left side. Similarly, you can have 6, 7, 8, 9, and so on. On the right hand side, you cannot have 1, 2, 3 on the right hand side. So these are the two restrictions that are there in binary search tree. Now, if you talk about insertion, deletion, and while you are searching the element in the binary search tree, it is much more efficient as compared to binary tree, because we can obviously, when we are trying to search for an element, we can obviously, if let's suppose we are searching for 8, so will it make sense to go on the left hand side? No, we can easily neglect this part. Similarly, we can do it on the rest of the elements. This is one scenario wherein searching is much more efficient than binary tree, because in binary tree we cannot neglect any elements, or we cannot say, okay, now we cannot find an element on this portion, on that portion. Similarly, when we are inserting, now, if the element is greater than 8, so we can easily, in this scenario, right, we can easily go on the right hand side rather than searching where we want to insert it. And similarly, when we are deleting, a little bit of ordering is done in order to get the exact same situation, wherein your root is less than the right hand side elements and wherein your root is greater than the left hand side elements. So that scenario is there in the binary search tree. Now let's talk about the application. It is suitable for applications which require sorted hierarchical data. Let's suppose you have some data and you want to store them in such a way that always you want your elements that are greater than the root on the left, on the right hand side, right? You want them on the right hand side, and for the elements which are less than this root, you want them on the right hand side. Okay, so that you can easily neglect. Okay, you can now, let's suppose, not, if you don't want this scenario wherein you are just dealing with the greater than or the less than, you can have a similar kind of a situation wherein you are saying that, okay, on this side I will always have some files that are related to coding. Okay, let's say an example, and in this I will always have files which are related to entertainment. So you can do that, so that you can easily neglect these files, because these are always going to be your coding files, and these are always going to be your your entertainment files. So wherever you require sorting, right, or you want you want your data to be in such a manner that it is easy for you to find, insert, and delete. So therein your binary search tree comes into picture.
Now let's see the implementation of binary search tree in Java. So before going to the coding, I'll tell you what the problem statement is all about. So we are going to write a program that is implementing the following points. We have to create a binary search tree using the concept of classes and objects in Java, and then create a function to insert the elements into a binary search tree, and then create a function to delete the elements from the binary search tree. So let's go to Eclipse IDE and try to write down the code. So here is the Eclipse IDE. Here I have already created a file, a package, and inside that there is a class file already with the name of BST, and which is having a public static void main method, which is a mandatory method to be there for execution of any Java code. Now, let us create a binary search tree. For that, in a tree, every vertex will be referred as a node. Okay, so we'll have a class node here, which will have a key, and it will have a left child and right child. Okay, then we'll go to the implementation of insert method, and then we'll see how we can call the insert method on the given binary search tree. So let us create a class here. So class node. You can give any name for the node again here. I'll have a character type for the key, and then the left child and right child will be the of type node itself, because they are also actually the nodes of any given node. Left child is also a node, so it should be of type node itself. Now inside this, let's have a constructor for this so that we can initialize this key value. Okay, so the key is of character type, so we'll have char itself here also. And in this dot key, this refers to the current instance or current object, okay, or current reference is made using this keyword. That's the reason I'm using this here. And that's it. Coming out of this, Again, we'll have another class here. You can write in the same class also. I'm just improving the readability of the code a little bit. So I'm creating a different class. So in this class, let's have suppose binary solution. Okay. And as the class name always starts with the capital letter in Java, let's have that as well. So a binary solution is a class. Now inside this, we'll have a root node first. Okay. Now let's have a insert function to insert the elements into this binary search tree. So void insert key is a function. And what we should pass here as a parameter. There won't be any return type because once the key is inserted, that's it. What should be the parameter here to be passed? It will be the key itself, which is of character type. Okay. Now inside this function, what we have to do is that we'll create another function here that will create the binary search tree, because it's not a normal tree, it's a binary search tree which is having certain property. So that property should be checked and verified, and then only the nodes should be inserted into it, right? So this function insert key is will take the key and it will create the root of it. Okay, first if there is no tree or no node present in the tree, but if there are already some nodes there, then that should check that where that particular new node should be inserted, right? So to check that, I'll create a separate function here. Let that function be named that maybe insert in tree. Okay, and here you will pass root dot key. Okay, now we'll create that function as well. Void insert in tree. Okay, and here you will be passing node, that is your root node. Okay, and also the key. Yeah. Okay, sorry, this will be comma, not the root, and the key will be passed. Okay, now let's have the implementation of this. The return type here will be node, because it will insert the element and it will return the root node, so that with the root node help we can refer the entire tree. Okay, so now in this, what has to be there is we have to write a logic or keep a check here that if your root node is equal to null, meaning there is no element or no node as of now in the tree, this is the first node to be inserted. In that case, what will happen? If that is the first node, then that becomes your root node as well, and that's what you will return. But if it is not the first node to be inserted, then you have to keep a check or do a condition check that if it is less than the root node, then it will go on the left side. If it is greater than the root node, it will go on the right side. Right? So that's a check here. So we'll write down a code for it. If root is equal to null, it means that is the first to be inserted. In that case, root will be equal to new node, and you'll pass here the key. Okay. Otherwise, and also will return root from here. It will be if again. Now if condition here is that if the key is less than the root node. So we'll compare if key is less than root dot key value. If it is less than that, then it should go on the left child, right? So it should go on the root dot left should be, and we'll call here insert in key, and we'll pass from here root dot left and also the key to it. Else, if again key is greater than root dot key, then in that case, what we should do is that we should go on the right side of the tree. So root dot right is equal to, insert in key, we'll go on the root dot right of it and also pass key over here. Okay. And then once this condition checks are done, we have to return the root from here so that the complete reference to this is made. Insert in, okay, insert in tree is a function name. Sorry, guys. So it should be insert in tree, not insert in key. Okay, so now it won't throw any error. So this is your insertion function in the binary search tree. Now to see that have we inserted it correctly or not, we'll come to the main method. And here, okay, before this, let's write a traversal method, because once you insert to access those nodes of a tree, we need to have a traversal here, right? So uh, let's see the sense here. So after this, we'll write a function void maybe pre-order traversal again. Okay, we'll pass node dot root, and then this again, that condition check will be there. If until root is not equal to null, we should do the traversal, and that traversal is in the pre-order. First we should traverse the root node, right? So it should display first, it will be root dot key. Then we'll go to the pre-order, meaning left child then and the right child. So it will be pre-order traversal of root dot left, and then pre-order traversal of root dot right. Pre-order traversal of root dot right. So we have written a function to traverse as well. Now let's come to the main function and write down the code here for inserting the elements in the binary search tree. So we'll call the function. Okay, before that we need to make a object for the class. Which class will make object? Binary solution. So binary solution, maybe T1 is a tree, new binary solution. Using this tree, we'll call the function insert key, and we'll provide the key here as it is a character type. So we'll provide the characters. So let's take any character in that manner. So insert key, then I'll take suppose some random characters I'm taking. T1 dot insert key again, and then here I'm inserting B, then T1 dot insert key, and here I'm going to insert maybe any character you can insert here, suppose G. Then again T1 dot, let's insert an ample amount of keys so that it's easy for us to understand. Let's have M T1 dot insert again. Okay, this will be the last, no more. Let's go to the checking part. Is the function working fine? Then we'll call T1 dot pre-traversal. What is the name of the pre-order traversal? So T1 dot pre-order traversal, and we'll pass T1 dot root. Okay, let's save it and run this file. So yeah, we'll remove the println from here, guys. So you can see here, like C will be inserted first, and then in C, I, B, G, M, and A, what will be the binary search tree? How to verify that this given answer is correct? Let's go to the slide. So here, what we inserted was, okay, if I am not very wrong, we inserted B, then, okay, we'll go to that and check again. What was the insertion order? C, I, B, G, M, A. So it was the not C, C, I, B, G, M, N, A. This was the order. Okay. So first we'll insert C. Next we have to insert I. I is greater than C. So it will come on this side. Next is B. B is smaller than this. So it will come here. G. G is greater than C, greater than I. G, H, I. Okay. No, smaller than I. So G will be here. Then M. M is greater than C, greater than I. So it will come on this side. A is smaller than C and smaller than B also. So it will come on the left side. Now what will be the pre-order traversal for this? Pre-order traversal meaning first you have to traverse the root node. So C will be traversed first. Then you have to traverse the left B. In this also root will be first traversed. So B. Then A. Then right side of this nothing is there. Then come on the right side of this. Right side of this first you have to traverse the root node. So I. Then left side G and then M. So CBA IGM. CBA IGM. You can see this is the output. So we have verified that the output which we got was correct. So this is how you will create the insert function in a given binary search tree.
Now let's talk about advantages and disadvantages of binary tree. If you talk about advantages, we can represent data with some relationship, right? So this is the root node, or this is the parent node, and this is the child node. So that relationship, parent-child relationship, is always there. And while you are inserting or searching an element or a node in a binary tree, it is much more efficient as compared to other data structures which we have seen. Now, if you talk about disadvantages, if you want to sort this binary tree, it is much more difficult, right? Because we can either go on the left side. This can be a tree. That means this is a left skew tree, or this can be the scenario wherein we have all the elements on the right side of the node. So this can be another scenario wherein we have this right skewed binary tree. So sorting is difficult and it is not much flexible, right? If you talk about this binary tree, we always have either the two children or one children or no children. There is no flexibility in terms of how you want to store it. Can we store another node on the with this root node? No, that is not the case, right? And we don't follow any restrictions like, okay, we always find this node. That is, if this is a root node, we always find an element which is less than this node on the left side or on the right side. That is the greater element. So that flexibility is not there.
Now let's see the graph data structure. So first I'll talk about what are graphs, and then we'll talk about its implementation using two different applications of graph, that is breadth first search and depth first search. So what is graphs first? So graph is actually a concept which has been derived from the field of mathematics to computer science. Okay, and graph is used here as a data structure. Here meaning in the concept of computers and programming and computer science. In this field, graph is used as a data structure. That is, it is used to store a data, represent a data in a different way. Okay, a graph consists of vertices and edges. Vertex are also called as nodes in computer science terms, but graph is basically the combination of vertex and edges. Edges connects two vertices. That is, a edge is always drawn between the two given vertex. There are different types of graphs on the basis of the different properties of vertices and edges and different properties of the graph altogether as well. But let me tell you, before going to the types of graphs, let us talk what is the different use of graph data structure in computer science. So if I talk about the application of graphs in computer science, I'll give you a very simple example. I ask you a question that, represent whoever is your friends in, like, suppose in your area or in your colony, and tell me in a pictorial way that who is a friend of whom and who is not a friend of whom, and how is that complete friendship structure in your colony or in your lane where you live. What will you do? You'll start drawing something of this type, like maybe, this is one person A, this person A is friend with person B, B is a friend with person C, and D is a person who is only friend with B. So this is how you'll represent. So this is nothing but what? A graph, where these are called as your vertices or vertex, and this is called as your edge, the line drawn between the two vertices. This is telling what exactly? The relationship between the two vertex, that is B and D. This, what kind of relationship in this example is it representing? That is a friendship relationship. So B and D are friends in the example of what right now I discussed. So in general terms also, edge between the two vertex tells some kind of a relationship between the two vertices. Okay. Another example I would give you, like suppose I ask you to, there are five different cities, suppose Delhi, Mumbai, Bangalore, Kolkata, Patna. And all these five cities, you have to travel from one place to the other. And I ask you what are the different routes I can take to travel between these cities. So what you'll do, you'll first represent these two cities like this, suppose A, B, C, D, E, these are the five cities. And so, okay, you can go to B, you can go to E, and then you can go from here E to B. To go from A directly, there is a place to go. Then to go from D, you can go either directly to E or you can go directly to B. Getting it? To go to A, you have to go to C first, and then you can go to A. So this is the representation. This is nothing but a graph. Okay, so we have seen two different applications, real life example applications where a graph is used in computer science. And I hope what is graph is clear to you as of now or till now. Now let me tell you what are the different types of graphs. Although there are multiple types of graphs if I consider the field of mathematics, but I'll discuss few here which is relevant and important in the field of computer science. So first one is your directed and undirected graph, which is important for you to know. So directed and undirected graph. Okay, directed graph meaning suppose these are the vertices. There will be a edge between these. Okay, as it is a graph, there has to be edge between these vertices. Directed meaning there will be a arrow marked here. There will be a direction specified. Meaning if there is these four vertices, B is having a directed edge from B to A. Meaning there is a relationship from B to A, but the relationship whichever is between these two vertices does not exist when it is talking about A to B. It is only for B to A. Okay, so this is your directed graph where there will be some kind of direction mentioned on the edges using a arrow mark. Okay, undirected graph where there is no direction mentioned. Okay, suppose this is the three vertex and this is your graph. So there isn't any direction mentioned here. This is your undirected graph, meaning the relationship which exists between B to C is also between C to B, right? Now there is another group of graphs called as connected and disconnected graph. What is connected and disconnected graph? Suppose all the vertices, these are the four vertices, okay, in a graph. All these four vertices are at least connected to any one of the different vertex. Any one of the other vertex, if it is connected, then it is a connected graph. Disconnected, that out of a complete graph, suppose this is your complete graph, A, B, C, and D, and these two are connected, but D is not connected to any other vertex. It's also called as your isolated vertex. So if there exists any isolated vertex in a graph, that is your disconnected graph. Or there is no link between any two vertex of a graph, that is two different graphs exist. For example, suppose there is one more edge here, one more vertex here, and this is connected. Now this complete together is one graph, okay, graph G1. But this is a disconnected graph because there is no connection between this part of a graph and this part of a graph. There are these different set of vertices where there is no connection between them. So you can divide if the complete graph into two different group of vertices where there is no edge connecting between any of the two vertices of those groups, then it is your disconnected graph. Clear? Or if there is an isolated vertex in any graph, then that is also a disconnected graph. So these are the basic classifications of a given graph. Now coming to the another concept of adjacency matrix or adjacency list. This concept is important here because when it comes to programming, adjacency matrix or adjacency list is what we use to represent graph programmatically. Okay, now what is adjacency matrix and what is adjacency list? Let's see that. So first I'll tell you what is adjacency matrix. Adjacency matrix is nothing but it will tell you that which two vertices are connected in a given graph. So this kind of a matrix it is two-dimensional. There will be rows and there will be columns. And this represents suppose A, B, C, D, E, and F. Okay. Similarly, on the row side also A, B, C, D, E, and F. Now, see, there is no self loops here. Self loop meaning if there is an edge from the vertex to the same vertex. So there is no self loop over here. So there is no self loop meaning there is no path to go from A to A. To go to A itself, there should be something like that. But there is nothing of this sort, right? So to go from A to A, there will be no path, so we'll mark it as 0. To go from B to B also no path, mark it 0. To go from C to C, similarly all this diagonal part will become 0. Now let's see from A where all you can go. You can go to B directly where you can go. Like, okay, indirectly after going to C, you can go to D also, but directly I'm talking. So from A directly you can go to B, directly to C, and directly to F, only three of these, right? So B, C, and F. So B, C, and F will have the value as 1. Rest values will be 0. Okay. From B where all you can go either to A or to C. So A or C, rest other values will be 0. From C where all you can go. You can go to every place like A, B, D, and E directly, not indirectly. Indirectly you can go to F also, but directly there is no edge between C and F. So you can't go to F. So F will be alone 0. Rest everywhere we can traverse from C. Coming to D. From D you can go directly only to C. Rest all other places direct edge is not there between D and other edges. So D to C is only will be 1. Rest all will be 0. Similarly, from E, you can go only to F and C. So F and C value will be 1, rest all will be 0. From F, where you can go either A or E. So A and E will be 1, rest all values will be 0. So this is your adjacency matrix. Now, adjacency list, how is to create that? And that's what I'm going to use in programming also right now when we'll write a code for the different applications of graphs in Java. So there we'll be using adjacency list itself. Now, what is that? So it is created in this way. So all the vertices will be marked A, B, C, D, E, and F. Okay. This is column representation. And in the row, like this will contain a list alone. This will contain another list. This will consist of another list. This will consist of another list. This will also consist of another list. This will also consist of another list. This itself is also one list. Okay. And each of it is pointing to another list. Programmatically, I'm talking about. Okay, to represent it, this is column and these are the values in those columns. Now, what are the values here in this list? So whichever vertices we can reach from A directly, those will be contained in this list. So from A we can reach to B, C, and F, right? So A will contain B, C, and F. From B where all you can go? A and C, so it will be A and C. From C where we can go? A, B, D, and E. So A, B, D, and E. From D we can go to C only, so only C. From E we can go to F and C, C and F. From F where we can go? We can go to either A and E directly, meaning there is a direct edge connecting between F and A, F and E. So A and E. So this is your adjacency list. Okay, that is from one given vertex, which all are the other vertices we can go. So this comprises of one list. So this is your adjacency list and this is your adjacency matrix. Now let us discuss the implementation of breadth first search algorithm. But before implementing it or writing down the code in Java, let us see what is exactly this breadth first search algorithm or how it works. So it is one of the application of graphs in which we are going to traverse the nodes of a graph in a certain order. Okay, so as the name itself says, breadth first search, that is along the breadth of a graph, along the horizontal level of a graph, we are going to search the nodes one by one in each level. So BFS is your or breadth first search is your algorithm to trace the nodes of a graph in a breadth first order. Okay, that is in a single level. First, all the nodes will be traversed, then we'll go to the next level and then next level. Now, you must be wondering whether how is the levels defined in a graph, because graph is not like a tree that you can define levels, right? So yeah, I'll tell you, if you try to visualize it like closely, you will be able to figure out that there are levels in the graph as well. So let us talk about this example itself, which is there right now here, the screen you can see. So in this, if I talk about the levels, can I consider this to be one level, this to be the another level, if I talk in this order, and then this will be another level, and this will be another level? Yeah. If I talk in this order, we can talk that this is these two A and B belongs to the same level, then F and C belongs to one level, then E and D belongs to one level, isn't it? So you can see here that the levels, if you closely observe a graph, you can find there are different levels as well. Now, to implement breadth first search algorithm, the concept used is of queue data structure. Okay. Why I'm saying queue data structure? Before implementation, let's see how it works actually. So in that, we'll start from any one vertex. Suppose A is the source vertex to start with. So we'll start from here and go on searching along the breadth of the graph one by one. So let this be a queue. Okay. The very first vertex which you will refer or visit, that is your source vertex. So once you visit this, we have to insert that into a queue. Okay. Now there will be one more, maybe a array which will be maintained, and let that array be called as your visited array. And this will have how many indexes or how many fields to store, equal to the number of vertices. So 1, 2, 3, 4, 5, 6 vertex are there. So 0, 1, 2, 3, 4, and 5. So 6 is there. 0 to 5 is 6. So 6 nodes will be there. Whenever you will visit or traverse any given node, that will be marked here as a true. Initially, all will be false. Okay. If the particular vertex is visited, that will be marked as true. So A is inserted first and it is visited first, right? So A is visited first. Okay, this 0 represents maybe A, this represents B, C, D, E, and F. Okay, we can have these numberings also like 0, 1, 2, 3. That will be more no, connected, I guess, or you can relate it in this way also. So this will be marked as true. Okay, it means A is visited. Now, Q follows FIFO order, that is first in, first out. So now you have to do is remove the very first element of a queue. So remove the first element, which is the first element right now, A. So A will be removed from the queue. Okay. Now, so what will be inserted? Once you remove any given vertex, we have to insert all those vertices which are in the adjacency list of A. That is, which all are connected to A. So connected to A is F, C, and B, directly connected. That's what is in the adjacency list, right? So F, C, and B. So we will insert here F, C, and then B, right? And in this, FCB is inserted. Now next, again we will perform the same operation. We'll remove or delete the very first element of the queue. Right now the first element is F because A is already deleted. So F will be deleted. And as F is visited, so it will be marked over here. And in this also, F will be marked as true because now it is traversed or visited. Which are the other nodes which are connected to F now? E and A, right? A is already traversed because this is made as true. So we'll not go with A. But connected to F is the E also. So we'll insert E again. Insertion is always from this end of a queue and deletion is always from this end of a queue, right? Okay. Next, again, same process. We'll remove the topmost element. Whichever are connected to that, we'll insert it into the queue. So C is the topmost element right now. So C will be deleted. And here the C will be marked as visited. That is true. And here also this will be your traversal list. So C will be marked here as well. And which are connected to C? A, B, D, and E. So you can see A is already visited. So we'll not consider A. So E and B is also already in this queue. So that also we should not insert again. Only left is D. So D will be inserted here. Fine. Next to be visited is B. Right. So B will be deleted from here. B is the next visited and B will be marked as true over here. Right. Now which are connected to B? C and A. And already A is visited, C is also visited. So nothing is there to insert right now. Now again we'll remove the topmost element. Topmost element right now is E. So we'll remove E and E will be visited now and this will be changed to true. And as connected to E, the vertices are C and F, and C and F both are already visited because it has been converted here as a true. So we will not perform any insertion for C and F. Okay. Now next is the element to be removed is D. That's the only element left. So D will be visited now, and this will be changed to true. And as now the queue is empty, will not perform this operation anymore on the graph. Okay, so this is the sequence which we get A, F, C, B, E, and D in the breadth first search. Let's see, is it following any level by level searching? So you see, first it searches A. Okay, A is this. Next it searches F, C, and B. So F, C, and B. Then it searches E and D. Now observe it closely. The first level comes as A, then the next level is B, C, and F, then the next level is D and E. So this is your breadth first search, where level wise, horizontal level wise searching is done for any given key. Okay, and this is the order we obtain. I hope the concept is clear. Now let us see the implementation of this in Java, and for that we'll come to the IDE now and try to write the code. So yeah, here I'm using Eclipse IDE, and I've already created a class here that is graph search. This is the file which is having a main method as well, public static void main. In this itself, I'm going to write down the code for a breadth first search, that is BFS algorithm. Logic is clear to you, so I'll go directly to the implementation. So first, what we have to do is, here we should have, so guys, how many things are required here? One is vertices, next is edges, or edges also I won't consider. The input will be vertex, that is how many vertices are there, and then the adjacency list. So we'll create an adjacency list that will tell us that related to, like for a given vertex, which all vertices are directly related. So these two will be our input, and our output will be the order in which the breadth first search is performed. So let's write the program. So what we need first is number of vertices. Let that be denoted as V, or we can use number of vertices also as to denote. Anything is fine here. After that, we'll go here. Now, in this, I'm going to use a data structure which is already predefined in the collection framework of Java, and that is your array list. Okay, array list helps us to store or create an array dynamically. Like it grows and shrinks as the size increases and decreases. Like if you delete element, the size will decrease. So dynamically the storage, the space allocation is done. So it is more effective. Space complexity will be less. That's the reason I'm using this. You can use any other linked list or array or to implement as well. So array list, this will be of type integer. Then let it have a name that is maybe adjacency list. So let it be adjacency. Sorry. Okay. You have to import this actually. In the java.util.star you can import, or java.util.arraylist will be have to be imported to use array list in the program. Now let me have the constructor for this class graph search, because this constructor, using this constructor, we are going to initialize this adjacency list as well as the number of vertices and all those parameters. So I'm going to create graph search. Input to this will be number of vertices, number of vertex. Okay. So it will be initialized. So we'll initialize first v itself with number of vertex. Okay. Now we will also initialize this adjacency list which we created. Fine. So adjacency, this is equal to new array list. As we know that new keyword is used for allocating space to any object, and then this will be number of vertex. Okay, so adjacency list will have number of vertex as a column. the spelling correct? Let's check once. Edges. Okay. Let's have a small naming convention. So let it be ADJ itself. Okay. That will be easy to spell out. So yeah. Now the adjacency list is in the allocated space and the size and all is declared. Now let's have the elements for it. So we'll need a for loop for this. For I is equal to 0, it will go till I less than number of vertices, number of vertex and I plus plus. And in this we will allocate, okay, let it be ADJ itself. Then I, this will be equal to new of array list. If you remember, I have told you that array adjacency list in itself is a list again. So there's one list which will have all the vertices, and then every you know uh, element there is another list which consists of the list of those vertices which are directly related to that particular vertex. So that's why it's a array list over here. Fine. So these are the initializations which we have to do under this constructor graph search. So as this is done now, we'll come out of this. And now we have to insert those elements which are the part of adjacency list. Right? This is what I have created or initialized the adjacency list. Now let us actually insert. So for that we need a method. So void, let it be edge. So I'm going to add those. Why I'm giving edge here? Because between two vertex, there is an edge, right? So that edge defines that there is a relation between these two vertices. That's why the function name I've given edge. You can give anything else as well over here. It will have two vertices, int x and int y. I'm taking integer vertices, not ABCD. It will be 0, 1, 2, 3, 4 as a numbering. It is easy to work with. That's the reason. You can have character numberings as well. And then this will be ADJ of x dot add y. So add is a function, inbuilt function, which I'm using here that is defined inside this array list class, and which will help to add the elements, add those vertices which are related to the vertex x. Okay, so this is your function for adding edges, or you can say creating adjacency list. Now let's have a function for breadth first search. Breadth first search. Okay, this will take input as your the source vertex. The first vertex you have to give as a input to this function. So let it be source vertex. So in this, now the logic will be that we have to take that vertex, insert it into a queue or any list data structure. Okay, you can use queue, array list, arrays, anything. And there should be one visited array also, which will keep mark that which all nodes are already visited, so that we should not revisit them. Right? So let's have that written over here. So first I will create that visited vertex. It should be of Boolean type because true and false is the value we have to store here. The size will be again equal to number of vertex. Right? Or okay, we can give here as v. Both should work fine. Okay, yeah, I have missed the square brackets. Fine. Now, once this is created, we'll have another list. So I'm not using queue here. I'm using list itself. You can use queue data structure as well, which will be of type integer itself. Let it be named as A1. Short names I'm going to use now. So array list again. And in this, we'll have of type integer. So these two requirements are over. Now, what we have to do is, first you have to mark the visited for the source vertex as true. because initially by default it is false. So first thing I'll do is visited for source vertex to be marked as true. Okay. Now next will be we have to add the source vertex to this list A1. Add source vertex. This is what we have done, right? In the even in the logic, this was there. Now, until the complete queue became empty. So here I'm using list. So until the complete list becomes empty, you have to keep doing this task, deleting the topmost one and inserting the values which are, the vertices which are related to it. We'll keep on doing this until and unless the complete list is empty, the complete queue is empty. So here it is list. So while we'll be using while loop for putting that condition. While uh, let's have not even dot till when there is an element. So is empty is an inbuilt function which I'm going to use here to say that we have to perform this operation till there is some elements in the list. So is empty will tell you true or false, is it empty or not. So until unless it's not empty, we have to keep doing this. When it's empty, it will come out of the loop. So what we have to do is source vertex will be removed. So I mean, not source vertex will be removed. We'll remove the topmost element, that is the 0th index every time, and that will be stored. That becomes our new source vertex. And so again, the whole process will be repeated. That is first thing. And then we have to also print this. So we'll be printing source vertex. Let's have little formatting here. I'll do here print itself. After printing it, now we have to iterate over it to check that is there some more elements or not, right? Or we have to iterate over even the adjacency list to find out which are the other vertices related to this. So we need a iterator for that. And so I'm going to use the concept of iterator over here. Iterator I maybe is equal to adj source vertex every time will be made iterable dot iterator method will be called. So it is made iterable. Then we have to import this. That's the reason it's showing error here. So yeah. Now we'll have again to iterate over what we need is while loop, right? And has next method. So while I dot has next, yeah, till when there is more elements into it, what we should do, int n is equal to I dot next. Okay, we have to convert it to this integer here. Now we have to also check that if the particular vertex is already visited, that is, we have to check that visited array. If it is already marked as true, then we should not revisit that. That condition I'm going to write now. If not equal to visited uh, for that particular n, then we should, if it is not visited, then in the visited of n, we should mark it as true, else it will remain false. Okay, and then add that to the list. That is a1 dot add that particular node to the a1 list. That is the array list, right? So this is what the logic was earlier as well. We have seen. So this is the complete program for breadth first search. Okay. Now let us come to the main method and just write up for calling this. So in the main method, we are going to just create an object for the class. Now what is that class? Graph search itself. So yeah, graph search. Maybe G1 is equal to new graph search, and there was a constructor right over here, if you could see. Where is it? Here, where you have to pass number of vertices. So let's have a some graph which is having 6 vertices, and then we'll be calling all the method. We'll have first adjacency list, guys, right? So edge will call, and we'll define the edges now. Okay, so let us take one example of the same graph we'll take which was there in our slide. So let's go to the slide. So yeah, this was the slide, right? This was the graph in the example here. So in this, the adjacency list will be, if I mark this as integers, because integer is what we are taking. So 0, 1, 2, 3, 4, and 5. Okay. So adjacency list will be 0 and 1. We have to insert this edge. 0 is connected to 1, 0 is connected to 2, and 0 is connected to 5. So let's insert this 0, 2, 0, 1, 0, 2, 0, 5. 0, 1, 0, 2, 0, 5. Okay. So similarly, I'll first write this, then we'll insert the values. G1 dot again edge, then again edge, G1 dot edge, then again G1 dot edge, and again G1 dot edge. Okay, now let's see. We'll go back to the graph again. Next is your from one vertex, which all are connected. 0 is connected, and then from 1, 2 is connected. Right? So 1, 0 and 1, 2. Then similarly from 2, which all are connected? All of these except 5. Right? So 2, 1, 2, 0, 2, 4, 2, 3, and that's it. 5 is not directly connected. Then from 3, only 2 is connected. From 4, 5 and 2 is connected. So similarly, we'll insert all the pairs. Let's see. So we'll go back here. So 0, 1, 0, 2 is done. Then there was 1. 1 was connected to only 2 of them, that is 0 and 2. Right? Now next, 2 was connected to all the others except 5. So we'll insert that. 2, 0, 2, 1, 2, 3, 2, 4. It's not connected to 5. Now 3 was connected to 2 and that's it, I guess. 3 was connected to only 1. Then we'll have again some few more edges. Okay, and one more, I guess. Okay, so let's have 4 now. So 4 was connected to 2 of them, 4, 2 and 4, 5. Lastly, 5. So 5 was connected to 0 and 5 was also connected to edge. 5 was connected also to 4. So this was the graph. So this is how you will insert all the edges. Okay, so this will prepare the adjacency list. Now after once this is done, we have to call the breadth first search algorithm. So breadth first search, and have to pass the source. So let the source vertex be 0 itself. So it'll start from 0. Okay, and we'll now execute this and see what's the output. So the output is 0, 1, 2, 3, 4, 5. Yeah, so let's see what should be the exact output. 0, 1, 2, 3, 4, 5. So the output is 4, 5. Okay, so the output here is first 0, then 1, 2, 3, and then 4 and 5. So the output is wrong actually. The output should be somewhat similar to this, right? Level by level it should traverse. Okay, so let's check what went wrong, that we are not getting the correct output. So if we traverse over the function, it was right. Let's just check once the calling part. So have we entered all the edges or not? So 0, 1, 0, 2. Let's go to the our graph. So 0, 1, 0, 2. Okay, 0, 5 is also there. Have we entered that? No, right? So let's see that thing that was the issue. So 0 and 5 will be entered. Let's execute this and check if there is something else. So now we got a different output, that is 0, 1, 2, 5, 3, 4. Okay, 0, 1, 2, 5, 3, 4. Let's see if this is a correct output. 0, 1, 2, 5, 3, 4. So yes, you can see here that 0 was visited first. This was the first level. Second level was this. Now in the second level, the order can be anything. This level, either there can be 1, 2, 5 you can visit, or 5, 2, 1, or 2, 5, 1, 2, 1, 5. All is correct answer, because it just has to traverse level by level. So this is first level. So next was this the output. Then 4 and 3 was the output. So our output is correct now, right? So 0, 1, 2, 5, 3, 4. So this is the implementation of your breadth first search. So let's revisit the code once. So what we did was had a class named as graph search, where the constructor of it was used to initialize the number of vertices and also the adjacency list. And we are using the concept of array list here, which is a dynamic array, which is the concept of a dynamic array actually. And using the for loop here, we have initialized it to so the number of vertices becomes the size of the array list. Then the adjacency list is created, and that is done using this function edge. That is, you have to insert the edges which are directly connected between two vertices, which will be added to this adjacency list. Then the breadth first search algorithm itself, this function method itself, which will take input as a source vertex, and from this source vertex, it will traverse down alongside the breadth of the graph. Okay, so for that we need a visited uh, Boolean array, which will keep track of which node is visited, which is not, and one array list, which will keep track of which all vertices are being visited one by one, or which will help us in implementing the whole concept of breadth first search. And there is only one condition check, that till we are completely emptying it out the elements of the list or a queue, till then we should keep repeating the process of deleting the topmost one and then inserting all those nodes which are related to or directly connected to that particular vertex or node. And that's what is done. Then lastly, we need one more condition check with the help of while loop. That is, until unless there is the node is visited, we should not, if the node is visited, then we should not enter it into the list again to revisit it. So no revisiting should be there. That's the reason this while loop is needed. And that's it. In the main method, we'll just create an object of the particular a particular class, and then call the edge function, edge method, to create the agency list. And then lastly, call the breadth first search method. So that's all about the implementation of breadth first search algorithm. Now let's see the implementation of another application of a graph, that is depth first search algorithm. So what is depth first search algorithm? First, let's try to understand that. Okay, what is the data structures that are used here to implement? Although graph itself is a data structure, but implementation of these concepts of the graph will take some other data structures that are there in the collection framework of Java while implementing it. So let's see how it is, it works and how is it implemented. So let's see the concept first. So what is depth first search algorithm? So depth first search is a searching methodology that scans through a graph depth wise, like vertically. First it scans all the nodes in a single depth, and then it backtraces to the previous one, the first vertex, and then it again traverses through the depth of the second line, and then again it backtracks itself, then again the next depth is traversed. So depth by depth, or in a vertical line, you can say, the searching methodology continues. That is, the nodes are traversed in a depth first order. Now what is the exactly meaning of this depth first order? Let's try to see with the help of this example here and understand. So A, B, C, D, E, and F, this is the graph. Okay, when I say depth first, so suppose this starts from here. Okay, this is your source vertex. I'll tell you the data structure which is used to implement this, and that is your stack. Okay, so we need a stack here. to implement this. And then there will be again a Boolean, you can say array, which will store true or false. Initially, all the values will be false, starting from A, B, C, D, E, and F. So all the values will be false. Once we visit that particular vertex, we'll make it as true. Now, this is your how the depth first search algorithm works. That will be explained with the help of these two data structures. But first, logically, what it is like. Okay. So depth first meaning, suppose I start from the source vertex. Okay. And I go to, so three vertices are connected to it. I can go to any depth first. I can go to F, I can go to C or B, any one. Suppose I go to F first. So I'll visit this first. Then F to F, what is connected? E is connected, A is connected. A already visited, so we'll not go back. We'll go to E now. So E is connected to C and A, B and D. So we'll go to C. Now C is connected to B and D both. So suppose I go to D now. So that's it. It ends here. Now D is no more connected further anywhere. Now it will backtrack itself till A and then it will go to the next depth. That is, it will go to, so C it is already traversed, so it won't go to C. So it will go to B. That is your next depth. So this is one depth. I mean one line vertically down till the end of the graph, and then backtracking it to the first vertex and then again going to the next depth. So this is what depth first search is about. If suppose I would have gone to B first, then it would have gone to this depth first till wherever it goes till the end. And then it will backtrack itself to the source vertex until then it will go to the next one. Got it? Now it's easy to understand like this when a graph is in front of you, but we have to write a program for it, right? So to write a code for it, you need to understand it in a different way. And that is, we'll be using stack over here. So what we do is that we pick up the source vertex first and insert the first vertex, that is source vertex, into it. Okay. This also what we'll do is we'll remove the topmost element in the stack. Okay. And then insert all those which are connected to that particular topmost vertex. Fine. As we know that stack, we can insert also from here and we have to delete also from the top itself. So this is what will be following the pattern. So first A is there. Now first we'll delete the topmost element. Right now only one is there, that is A. We'll delete this. Okay. And we'll mark this A to be visited, that is true. And A will be our first element to be traversed or searched. Now connected to A are which all? F, C and B. So you can insert this in any order. That is not important. So B, C and F, suppose I inserted. Now next element to be deleted will be F, because we delete from the topmost. So okay, F will be deleted. F will be marked as true over here and F will be placed over here as well. Okay. Now which are connected to F? E and A. A is already visited, so we'll not insert A again. Next is E. So we'll insert E into the stack. So our stack is going to look like something like this. B, C and E. E will be inserted. Right. Now we'll delete again the topmost element. Topmost element is E. So E will be deleted and E will be marked here as true. It will be deleted from here. Now which all are connected to E? Which all vertices are connected to E? C is connected. F already is visited, so no need to go there. C is connected. C is already there in the stack. So this also one condition check is that you have to check the stack also. If it is already there, then no need to insert it again. So C is already there, so we will not insert it again. Let it be like this. Now again we'll delete the first topmost element in the stack, that is C. So C will be deleted. C will be marked as true and it will be the next element to be searched. Now which are connected to C? D is connected to C. B is also connected to C. B is already inserted there. So D we will insert it again in the stack. So we'll insert D. Okay. Now we'll delete again the first topmost element, that is D. So D will be deleted and D will be marked here also as a true, that is it is visited now. Which all are connected to D? Nothing is left to be connected to to be inserted to stack because D is connected to C and C is already visited, so no need to insert it again. So will not perform any insertion here. Now next element to be deleted from stack is B. So B will be deleted. B will be marked true here, that it is visited, and B will be the next element to be searched. So this is the sequence we got. And as you can see, now the stack is empty. So until unless the stack is empty, you have to perform this operation. Once it is empty, no need to perform this operation again. We can stop there. So that will be our stopping criteria of the algorithm. Now this is what we got. So you can see here, A is traversed first, then F, then E, then C, then D, and then lastly B. So this is one depth, traverse first or searched first, then the next depth. So this is your depth first search algorithm, and this is how it works. So we are going to now write the code for it, and we'll be using these three concepts itself, guys: stack and a boolean array which will store true and false, and maybe a list which will store the adjacency list, that is called as, that is which vertex is connected to which all other vertices. To maintain that, we need one array list, and then we need one stack and one boolean array. So using these three data structures, we are going to implement the concept of depth first search. So let's go to that. So we have come to the Eclipse IDE here, and I'm using Eclipse IDE to write out the code. You can use any other. Where the already I've created a class, graph search, where there is the main method of the class. So we'll be writing down the code in this itself for depth first search. So let the main method go down. Okay. So as I've told you that we need three different things here. One is here the concept of stack. Then one, we need a Boolean array to keep track of which all nodes are visited, which are not. And then one more list, that is your adjacency list. So let's create all these. So first will be the number of vertices, which will be denoted in the with the help of variable v. Then we'll have a array list, which is of type integer. This is will be maintaining the adjacency list. Okay, you can give any name to this, which is an array. So if we can give maybe adj. Okay, I think we have to import the class. So yeah, let's import it. And this should be the wrapper class. We cannot use primitive data type over here because all these classes which are defined in the collection framework takes wrapper class to be the data type for it, not the primitive data types. Now we have to create the constructor for the class graph search so that we can initialize how many vertices are there. Also, we can initialize the adjacency list. So let's have the constructor here for the class graph search, which will take input as number of vertex, which will take as a parameter. So it is a parameterized constructor, which is taking one parameter, that is number of vertices. So we'll initialize v with this number of vertex. Then we are also going to add, initialize the adjacency list, new array list, number of vertex will be its size. Okay, this will be a square bracket here. So yeah, this is done. Now let's create the structure for the adjacency list. Like we created an array list where all the vertices are there, but each vertex should be connected to a list that is called an adjacency list, to which that will represent that that particular vertex is connected to which all other vertices. So that's what I'm going to do here. That is int I is equal to 0, and then I should be less than here a number of vertices, and it will go till I plus plus. And then here I am going to initialize this I, this is equal to new array list. Okay, so this is done. The constructor for the graph search class is created. Closing, this is also closing. Now we have to create the elements inside this adjacency list, that is the edges which are there that should be inserted. So for that I'm going to create a method void edge, which will take two parameters, int x and int y, and which will be inserted into this adjacency list. So adjacency of x will be having, you have to add y here. So add is an inbuilt function which is being used. It is inside the collection framework, or you can say it is inside array list class. So that's it for adding the values or edges to the adjacency list. Now we'll write down our main function of depth first search. Okay, it will take input the first source vertex. Okay, let it be source vertex as a name. Now, in this, the logic is we have to use stack, we have to use Boolean array. So let's define first all those whichever is needed. So Boolean array, maybe the name will be suppose visited. Okay, the size will be equal to your number of vertices. We need a stack now. So how to create a stack? We have to use inbuilt stack class and create an object for this. Okay, let it be S1, which is equal to new stack. Then we have to import this, I guess. So let's import it. In the java.util package, it is there. So we have to import that. So now stack and this visited array is created. Now we have to come to the logic. So every time we should peek into the stack and see which is the topmost element, then pop it out, delete it out, and then go to the adjacency list, and whichever is connected to that, we should insert into the stack again, and then perform the whole operation. So let's write the logic for that part. So S1 dot, first we have to push the source vertex, okay, and also change its value in the visited to true, because initially it will be false. Okay, let this be represented also as a node. Now the condition check will be there. So while there is some element in the stack, we have to keep doing this. Okay, it should be S1 dot empty. Yeah, so empty is a function which we are going to use. So till the stack is not empty, we should keep continuing and doing the process of deleting. So that will be S1 dot pop. Okay. But before this, what we should pop? So for that, you have to peek into the stack, right? So your source vertex will become now whatever you peek into the stack, right? And then you should pop out the topmost element. Okay. So while loop is completed here, now we have to do what? Check the adjacency list, whichever are there that has to be inserted, and also we have to keep a check that the visited vertex, visited node should be marked as true, or it should be false first, then only we can insert it. So let's write the code for that. So for int I is equal to 0, uh, adj of source vertex should be uh, its size. So yeah, size is the function there. We can have that till the size of it, like complete list you should scan. Okay, should be I less than. Now here your node will become adj of source vertex, adj of source vertex dot get function is will be used, get of I. Okay, so get of I will tell you that particular at that particular index, whatever is the value it gets you, like it fetches that value, because that's what we'll be comparing, right? Is it inserted first or not? Now here we have to also keep a check that in the visited uh, array, it should not be true. It should be false. If it is true, it means it is already visited. So that check should also be done. So S1 dot push. If it is not, then only we should perform push. And what we should push? Node, whichever node we are referring that time with. Okay. Now, okay, this is closing here for loop. Okay. Now we will do the changing of true to false. So if visited source vertex uh, is equal to false, then we should change it to true, right? Visited source vertex should be changed to true, and also it should print. Nowhere we are printing, so let's print it here. So we should print what here? Source vertex, because that is the vertex being visited that time. Okay, and we'll change it to true. So that's it, I guess. This is the ending part of it. This is end of the function. So yeah, this is our depth first search algorithm. Let's call this in the main function now. So to call it, we have to make an object of class graph search. So let's make it quickly. Graph search G1 equals to new graph search. So to pass the source vertex should be passed over here, right? Okay, no, the size of it. So size, let's take the same example which we have to take in for the explanation. So in the explanation, if we go, you can see this is the graph. So it is connected to A to B, A to C, A to F. So we'll insert all these values here. So let's call G1 dot edge, G1 dot edge. Okay, I'll copy paste it. Let's save some time. So how many edges are there? 1, 2, 3, 4, 5, 6, 7. 7 edges are there, right? Okay, let's go back. We have inserted so many. Okay, let's insert the values of it and see. So 0 is connected to 1, 0 was connected to 2. Then 1 was connected to all except 5, we remember, right? So 1 is connected to 0, 1 is connected to 2, 1 is connected to 3, 1 is connected to 4. So yeah, let's see. I think 2 was connected here. So yeah, if I represent this with numbers like 0, 1, 2, 3, so it will be something like this. This will be 0, 1, 2, 3, 4, 5. So 2 is connected to all except 5. 1 is connected only to 0 and 2. 1 is connected only to 0 and 2. Okay, let's, my mistake. 2, 2, then 3, and then 4, uh, again 4, then 5, and again 5. So yeah, these are the number of, so 1 is connected to 1, 0 and 2. 2 is connected to 1, 0, 3, 4. 3 is connected to, I think, only 1, which was 2. 4 is connected to, let's check, guys. 4 is connected to 5 and 2, and 5 is connected to 0 and 4. Okay. So 4 is connected to 2 and 5. 5 is connected to 0 and 4. I hope this is right. Okay. Let's call the function g1 dot depth first search and pass 0th index there. Let's have one print statement as well here, stating that result of depth first search. Okay. Okay, so it is not printing correct. Again, there is something which we have missed, so let's check it out. Okay, so as we are checking where what went wrong. So we'll see here depth first search, it's correct. Source vertex, stack, then we have to push it to it. Then this node will refer the current no vertex being visited. S1 dot empty source vertex. Then we'll pop it out. Size, okay, till the size of the edges list, we have to traverse it all and then push it into it. It's false. Okay, it's looking correct. Let's figure it out. So I think, okay, we will, okay, this while should loop should not end here. It should end over here. Let's see if it works. Okay, yeah, so that was the problem. We have closed the while loop over here itself. So it should be closed at the end. So this is the output of the depth first search 0, 5, 4, 2, 3, and 1. So you can see this is also the output. We can match it with what output we got. So it is 0, 5, 4, 2, 3, 1. 0, 5, 4, 2, 3, and then 1. So it's correct, right? This was one depth, and then this was the next depth. So 0, 5, 4, 2, 3, and 1. So yeah, our output is correct for this program. So you can see, just I'll go through the code once again. So what we did was we created a depth for search function here. Before that, adjacency list was created, and the edges which were connected were added to that adjacency list. And then while searching, while performing depth for search, we have to keep no we have to use these two data structures, the stack and one boolean array, which will keep track of whether the node is visited or not. And that's what is done. We have to peek into the stack, whichever is the first element, we have to delete that, and whichever is connected to that particular deleted vertex, insert all that to the stack, that is push all that to the stack, and then also check if it is the visited vertex value is false or not. If it is false in the visited array, then should make it true, and that will be printed also as an output. And then in the main function, we have created the edges, that is the adjacency list is created, and then the depth first search method is called, and that will give us the desired result. So this was all about the implementation of your depth first search algorithm. Now let's talk about the concept of hash tables. So what is hash table? How is this hash table implemented in Java? Now, before understanding all that concept, we have to understand what is hashing. So because hashing is a concept which is being utilized when we talk about implementation or no, coding of hash tables or hash map and so on. So what is hashing? So hashing is a black box technique in which if you pass a key, the key can be anything, a number or a string. If you pass a key to that black box function, the output will be a code that is called as your hash code. Okay. Now, why this input and why this output? What is the whole concept? Why is it required first of all? Okay. So let me explain you. So suppose I'm talking about a function. Okay. Let this be represented as h of x. Fine. Now, this will pass a key. Okay, this key can be a string, it can be an integer, it can be anything, any number or a sequence of characters, anything. Okay, output will be a code, also called as your hash code. Okay, now what does this hash code is used for? So hash code tells the position where that particular key is going to be stored at the backend in the computer system. Okay, for example, suppose there are these many, this is your array you can assume, or this is a space which is there where your data will be stored. Fine. Suppose the data example I'll take is of a student. Okay, so a student will have its name, will have its roll number. Okay, now this data has to be stored somewhere. When we talk about the storage in RAM, that is a temporary storage, right? So when we talk about storage in RAM, this is how the storage is structured. So suppose this data about a student who has a name and a roll number has to be stored somewhere. Okay. Now that data or that name of a student, suppose, is a key. Okay. That key will be passed to this hashing function or hash function. And the output will be a code. That code will be nothing but that position in this storage area where that particular data of a student will be stored, that name or roll number of a student will be stored. Okay, suppose the key or the name of a student is something called as maybe ABC. Let the student name be ABC. So ABC will be the key which will be given to this hash function, and output will be a code. This code is suppose for ABC key is your 4. Okay, so starting from 0, 1, 2, 3, 4, and suppose there are more numbers, more storage space here, 4, 5, 6, and so on. So at fourth location, we'll store the data of the student ABC. Getting it? Next, suppose there is some other another student or whose name is maybe Priya. Okay, so Priya name will be this key. It is a key here. It will be passed to this hash function, and the code or the output which we get out of this hash function is suppose 2. Now at second location, the information or the data related to Priya student will be stored. So this is how hashing works. Okay, this whole concept of finding a code out of a given key. That key can be anything, either a string or either an integer value. Like in this example, it was a name. So for the Priya name, the code was or the output of this hash function was 2, and we stored there. So this is the complete concept of hashing. Okay, so you can say it is a one-way function, meaning if you provide a key, it produces a code or a hash value. Okay, but if you provide a hash value, it won't produce a key, right? Now, what is this function? So this function is designed in various ways. This function can be like as simple as picking the last character of a string and converting it to its ASCII value, and that ASCII value becomes the index or the hash code. Okay, or it can be as complex as some mathematical calculation over the ASCII values of a given string. So we are not no bothered about what this hash function is going to be, although the complete hashing concept depends on this hash function itself. The more better and well structured your hash function is, that good the complete hashing technique will be. Why I'm saying that? Because a good hashing technique is only that where there is minimal collision. Now, what is this collision? So we'll take this example again and see. So the same hashing function, I'm going to take another example. Okay. Now, let's see here. Suppose there is a student called by the name of Priya. Okay. Then another student is there by the name of maybe Pooja. Then there is another student maybe by the name of, you can say, what, Rohit. Fine. Now, we have to store these three data or three names of a given student into the storage space. Now, Priya will be passed to this hash function as a key. Okay, it will produce a hash code. Suppose it produces the hash code as 2. So this Priya will be stored at location 2. Then there is another student named as Pooja. It will be passed as a in the hash function, and it will produce the hash code to be suppose 4. Okay, at the fourth location we'll store this Pooja. Now next is your Rohit again. So Rohit is passed in this hash function, and the hash code which it produced was again 2. But at the second location already there is another information about a student named Priya is stored. So where will this Rohit be stored? Now this complete situation is called as your collision. And a good hashing function should avoid this collision situation. Okay, so when we talk about its implementation in Java and where it uses hash map and hash table kind of a concept, there this collision is resolved. Now, how is this resolved there? It is resolved by using the concept of linked list. It means what? Like, suppose the second student here, Rohit, also had a hash code of 2, but 2 was already occupied by another student information, that is Priya. So what will happen? There will be a pointer to from this place, that is second index, to another node. Okay, and this node will be having the information. This is a node of a linked list. Okay, and this node will be having the information of a student Rohit. This will also be like one node of a linked list. Okay, which will have the value, that is Priya, the name of the student, and the address to the location where this node is. Like how in linked list it is. Every node of a linked list stores a data and a pointer to the next node, right? Similarly here, the data will be the student name Priya, and then address to the next node, that is this node where the Rohit information is stored. Getting it? So this is how collision is resolved. So there are multiple techniques to design this hashing function. Then there are multiple techniques also to resolve the collision whenever it happens. So one of the way I told you is by using the concept of linked list. So all those keys which are mapped to the same location are linked with the concept of linked list or linked as a nodes. Okay, but we always try to have a hashing function which has minimalistic collision, and that's a good hashing concept or a good hashing technique. Now we'll talk about what are those ways in using which we can implement these concepts of hashing and how it works when it comes to Java programming language. Now let's talk about the implementation of the concept of hashing in Java programming. So for this, what will be the problem statement is that we are going to write a program using which I'm going to tell you how this hashing concept works or what is hash code and then what are different hashing functions which we can use in Java programming. So guys, there are so many hashing functions which already exist like MD5, SHA. All these hashing functions produces 16-bit hash codes. So you can do the direct implementation of these hashing functions also, but even if you don't do, like, how in a most simplest way you can use the concept of, or is Java using the concept of hashing? So for that we will talk about two of the concepts of collection framework in Java. One is your hash map and the next one is your hash table. Okay, so hash table is an interface which is defined in the collection framework of Java, which we'll be making use of directly here to write down the code and understand the whole concept of hashing. So what happens basically is, so let's try to understand that first and then I'll come to the coding part. Suppose I'm using the concept of hash map. Okay. Now hash map is kind of a associative array where there are two fields. Okay. One is your key, another is your its value. Okay, so this pair is always stored in hash map as well as in hash table. Both is same, just with a few minor differences, which I'll tell you what is the difference between them. So key and value pair will be there in both hash map and hash table. Taking example of a student data. Okay, so every student will have a name, and suppose that student name will have a roll number as well. Okay, so every name of a student is associated with roll number. Let's take few examples. For example, Priya is a name and the roll number of student Priya is 3. Pooja is another name of a student. Roll number of the student Pooja is 2. Then Rohit is another student whose roll number is suppose 6. Okay. Now, how hashing works here? So what happens is when we create a hash map and store these values there, backend what happens is that this particular key, that is Priya is a key here, Pooja is a key here, Rohit is a key here, and these are the associated values with that. Okay, so for the key Priya, this Priya will be passed to the hashing function, which is an inbuilt hashing function when we use the concept of hash map and hash table. In fact, for every other objects which we create of the wrapper class in Java, there is a hash code. I'll show you the implementation or whatever I said right now in the IDE also. But try to understand first here the concept, the logic. That is, the student Priya is passed in the hashing function and it generates a hash code. Okay, and suppose this hash code is generally a very lengthier one, like it will have 10 digits or 11 digits or something like that. So which is you can do modulus operator on this and reduce it to a smaller number also, like suppose mod 10 I do, then I'll get one single value, right, of as a hash code. So you can do that, but normally, like by default, a longer 10 digit or 9 digits or 11 digits, some this kind of a hash value is generated. Okay, and depending on that hash value, suppose the hash value, and after doing mod operator or reducing it to a smaller size, I get a value of maybe 20. Excuse me. Okay, maybe 20. So in that case, this what will happen that at the backend at location starting from 0 somewhere at location 20, this information Priya and its roll number, the other value also, that is 3, both of these will be stored, Priya and 3. Getting it? Similarly, for the key Pooja, only as key will be Pooja here, the name of the student, which will be passed to the hashing function, and hash code, one hash code will be generated. And that hash code, suppose generated is maybe 25. So at 25th location, okay, the information about the key puja and its associated value, that is your roll number, both will be stored there. So puja and associated roll number, that is 2, will be stored there. Getting it? So this is how the hashing concept or hash code concept is being used by these two um, collection frameworks or the concepts of collections of Java. Now let's see the implementation or coding part of it, and let's go to the IDE now. Okay, so here you can see I have already created a class named as hash, and there is a main method public static void main here. So now let's go to directly seeing how the concept of hash code actually works in a real scenario. So for that, I'm going to create a hash map. Okay, so hash map, as I said, it takes two value, the key and the value of the other element. That is the example we saw, name and the roll number, right? So two values will be there. So similarly, you have to provide the data type also for those two values. So if I take name and roll number, the same example, continuing further as implementation, then name will be a string value and the roll number will be an integer. So let's take a string and then integer. Okay. After that, we should give a name to this hash map. Let that name be student. Okay. Then new keyword, which is equal to new keyword, which is used for allocation or creation of an object or allocation of space basically for the student hash map. So okay, new keyword, and then again hash map, and then again you have to provide the data types which we have already provided, that is string and integer, and then round brackets and colon. That's it. Okay, it's showing some error. Let's see. I think you have to import it. So yeah, let's import this hash map. Okay, so hash map is declared here now, or created here basically. Now let's add the student information, that is its name and roll number. So to do that, we use a concept of, or we use a method that is called as put method. And how it is called? So let's see, student dot put, and in the bracket you have to provide two values. First will be your name, that is maybe your, let's take Priya as a name, and let its roll number be, this will be a integer value, so 3. Okay, so I'll just copy paste this again and again just to save time, guys. So if you put here 3 students, suppose I'm going to put, so Priya, Pooja, okay, Rohit, okay, these are not my friends, just simply I have taken the names, and suppose 7. Okay, now to get the information, like okay, I have stored it, now let's check has it been stored correctly. So if you'll give a key here, it will give you the value, that is the roll number of that person, the student, as an output. To do that, how can you use, just see here, student dot uh, get. Okay, okay, we'll do one thing, let's put it under the for loop so that we can use it for all. Now, again, for before putting it in the for loop, there are two ways by which you can iterate over a given hash map. Let me tell you both of that. So two ways are there by which you can iterate over a hash map. Okay, one is by simply using the concept of set, and other is by using the concept of entry concept. And that, what is that, I'll tell you. So first, let's see the concept of set. Okay, so what you will do is we'll create a set here which is of type string. So all these data of the hash set will be converted as a type of set. So let's create a set first here. Okay, and to do that, we use set class and then string, the data type for that, and then any name you can give. I've given data as a name of the variable of that set variable. So data on, and then we can call student dot key set. Okay, so I'm going to make the student hash map as a set of data or a set of keys. Okay, think we have to import this also. Okay, let's import that. Now we can use for loop on this. Okay, so I'm using for each loop concept where string I for data. What I'm going to do is I'm going to print. Now here I'll use the get method. So get method, put method was used for storing the data. Similarly, get method is used for fetching the data. So get of I. So we can see here. Now let's run this code. So you can see that with respect to all these names, all these keys, we got 3, 2, and 7 as here values for them. They're all numbers. Now suppose you want both to be printed, the key as well as its value, that is the name as well as they're all numbers. So for that you can use another concept is there, which is your entry set concept. Let's see what happens there. Okay. Okay. So after this. So in this, what we'll do is we are going to create a entry set. Okay. And this takes map dot entry, and the data type will be a string and integer, because this time we are creating in pairs. This entry set. Okay. So it will be in pairs, a string and then integer, the name and the roll number. Okay. And then let it be data 1. I just change the name of student dot entry set will be called as a function, then semicolon. Okay. This is how we create a entry set. Okay. Now using this again for each loop on this entry set, we are going to iterate over the given hash map. So for again, but here there you see that data type was string, right? But here the data type will remain same, that is map dot entry. This will be the data type, and here you should write string, and then you should write integer I colon over data 1. Okay. So in this we are going to iterate, and then I'm going to write the same thing, that is I dot. Okay, the here function is get key. So this will tell you the complete key, that I mean that is your name of the student as well as its roll number together, because you've created the entry set. Okay, so get key will give you the key, and then you can have again I dot get. So you can see here the get key, get value, get class, 3 methods are there. Get key we used, which will tell you the string part of it. When get value you do, it will tell you that integer part of it. So we'll use get value. So both we can get the key and the value, that is the name and the roll number of the given student. Okay, so that's it. We'll save the file and then just let's run and check. So you can see here, this is the output of the earlier for loop. And then this is the output of the second one, that is entry set we used. So this is how we iterate over it. Now, let me here tell you where is the concept of hashing here used. Okay, although I have told you that when this particular set, that is the hash map, that is the name of the student and roll number is stored somewhere, first the hash code is generated for it, and then it decides the position of that particular data to be stored at the backend. Let's print here I dot hash code. So you can see here the hash code is an inbuilt function already in Java, which helps you to get to know what is the hash code generated for each of this data. So I here is nothing but the key, that is the string part here. That is the name of the student in this example. That is Priya, Pooja, and Rohit. Okay, so let's see what is the hash code generated. So guys, you can see here, okay, I will just comment out some of the lines. Okay, so that it's easy to understand the output. So you can see the output here. So it has generated the hash code. First one is for Priya, the second one is for Pooja, and the third one is for Rohit. Right? So this is the hash code generated. Okay, one more thing. Okay, it's not necessary always that this is how the order will be. So let's print this for that matter and check what is exact hash code. So 3 is the roll number. So 3 is Priya itself. So its hash code is this one. Then 2, its hash code is this. And then 7, its hash code is this. So you can see how longer hash codes are generated by default. So most of the time what we do is we get mod of n, and this mod of n we do. N is nothing but the total space that is there. Suppose initially we use a number of Suppose we are using arrays to decide the position. So suppose the array size is 10. So we'll do mod of 10. What is the total complete size where these data are going to be stored? That becomes your n. That is used as a mod here to bring the complete hash code to that range. So if you do mod of 10, it will come to the range of 10 storage space. Okay, 10 indexes. If you do 12, it will come to 12 indexes. Okay, so in that range it will come. So let's see what's the output after that. So you can see here for 3, the 3 roll number, that is Priya, the hash code is 9. For 2, the hash code is 2. For 7, hash code is 0. So you can see it is stored at that particular location ranging from 0 to 9. When you do mod of 10, it is 0 to 9. Okay. So these at the backend, what would have happened at is that these particular data would have been stored at this particular indexes. So that's how the concept of hashing works inbuilt or by default in Java programming. If you can see this by the whole help of the concept of hash map, or even if you don't create hash map, like suppose directly I create a string here, a is equal to and hello suppose. And if I try to print, okay, this will be capital S. And if I try to print a dot hash code, then also you can print the hash code value. So it's always that there is a hash code generated. So this is the hash code for string A. Okay. So that's all about the concept and implementation of hash map and hash table. So hash table, guys, it's similar in implementation, just that here you have to use hash table in class. And then you have to import this as well. And that's it. It will work in the same way without any error. Okay, but there is a difference between hash map and hash table. Okay, one is your hash table is your synchronized and hash map is not synchronized. I mean hash tables are thread safe, so and hash maps are not. So that's a different concept here altogether, but that's how hashing is implemented using Java programming.
Let's try to understand what is an algorithm. It is a step by step approach to solve a particular problem. If there is a problem, what is the things that you are going to take care of? So the solution that you give should be crisp, right? It should be exactly what is required, right? If a problem is about swapping two numbers, you should be able to swap two numbers and with the most efficient approach. And when you define an algorithm or when you're writing an algorithm, it should be understood by a non-technical person, right? There should be no such language dependency in your algorithm, right? So this is what an algorithm is, a step by step approach to solve a particular problem. Your problem can be complex or it can be an easy problem. It is free from programming language. There are multiple possible algorithms to solve a given problem. Let's suppose I told you to swap two numbers, right? Now, one algorithm is wherein you can go ahead and create one temporary variable and then swap them. The another approach is that you're going to use addition and subtraction operators to solve the same. You're going to use these operators and you can solve this problem of swapping two numbers, right? Which one do you think is the efficient approach? Obviously, here you're using an extra variable and here you're not using any extra variable. So this seems to be a better approach. And obviously, it should be understood by a non-technical person. You should not be using language dependency code, like you should not use any language agnostic code, right? So it should be language independent. So let's see what is an algorithm analysis. This is again a step by step approach to solve a particular problem. It helps us identify which algorithm is optimal. Okay, this is the analysis part of algorithm, right? Herein, let's suppose I told you to swap. It helps us to understand the trade-off between time and space complexity, right? So there should be always, you should be able to understand the difference between time complexity and space complexity. And depending on that, you should be able to do a trade-off as well. Now, when I mean trade-off, you should be able to depict that are you going to keep your time complexity efficient, or are you going to use your time efficiently, or are you going to save your space? So let's suppose you are given an example, right? Let me give you an example. So you are given an example, you are given an array, and in that array you want to search an element. Now the first approach is that you will go and search one by one, right? You will go here, you will iterate through here and here and here. You try to search an element, right? Let's suppose you are searching for 4. In the worst case, you are traversing a big O of n time, right? And in the best case, you are traversing big O of 1 time. This is the best case and this is the worst case, right? So these are the two cases. But this code in itself, whenever you are traversing in a linear fashion, is inefficient, right? And if you're trying to search for an element using different approach, let's suppose you are using a binary search and then you are trying to search an element, obviously your time complexity will reduce. The best case will again remain big O of 1, but it will reduce to big O of log n. Now there are certain parameters, or depending on these parameters, you can define the best, worst, and average case of a given problem. So now there are different types of algorithmic analysis, that those are best case, average case, and worst case. Okay, so the best case is obviously when you are searching for an element in an array of, let's suppose, 100 size, right, or 1000 size. The best case is that the first element that you look, if you're talking about what, linear search, okay, best case scenario is that the element that you're trying to search is the first element, right? Done. This is your best case and it requires constant amount of time. Now if you talk about average case, it will be somewhere around the middle, right? About 1000 divided by 2, or you can say big O of n divided by 2. Since we are neglecting, we do not take care of these constant terms, or we can negotiate or we can neglect these constant terms, because as soon as our input is increased, right, let's suppose right now we are talking about million, thousand elements, we are talking about 10 billion elements. At that time, dividing it by 2 still is same, okay, not same, but it is, it can be ignored, because as soon as we are increasing our n, let's suppose, to 10 crore or more than 10 billion, okay, 10 100 billion is the input size, right? At that time, dividing by 2, still it is greater than what we can do if we have something around log n, okay. So obviously the average case is still big O of n. Now when you talk about worst case, the element is found at the end, or it is not even found in the array. You're traversing each and every element in the array and still you were not able to find the element. So this is the worst case, okay. Now the worst case is always taken into consideration because this is the maximum resource that you require, okay. When you talk about time complexity or space complexity, right, so time and space, right, so you always talk about worst case scenario, right? And you always deduce your time and space complexities based on worst case. It is computed because the analysis, as it dictates the maximum resource requirements. So worst case helps us to find what are the maximum resources that this is going to take, okay. So we keep track of those things and we allocate resources in such manner. So we always talk about worst case. Now let me give you an example of linear and binary search. So in linear search, right, we always talk about it, and in binary search, the space complexity of both these algorithms is constant in worst case, right? And if you talk about the best cases of linear and binary search, it is again constant, right? And it is again same, okay. Now when you talk about, we go off on, now when you talk about the worst case scenario, right, and this is what helps us to differentiate between binary and linear search. The worst case scenario. The worst case scenario for linear search is big O of n, wherein for binary search it is big O of log n. Now let's suppose there are 8 inputs. You're going to traverse 8 times in it in this linear search. But if you have this log 8 to the base 2 value, it reduces, or you can reduce it to 3 into log 2 to the base 2, which is 3 times. So in this, you are only iterating 3 times. In this, you are iterating 8 times. Now, as you can see, that input is very low or very less. That means there are only 8 elements. As soon as what our input or n or the number of elements in the array grows, this size of these iterations become substantial, and that is for the same reason we always talk about worst case scenario. Okay, now let's talk about time complexity. It determines the total number of unit operations to be undertaken to solve a particular problem. Right? Let's suppose, let me take an example of number of iterations. Like, so if you are able to search an element in a single unit of operation, then it is termed to be a constant operation. And if you're doing same for number of inputs, that let's suppose there are n elements and you're traversing to find a particular element, you're traversing n times, so it's termed to be a big O of n. So to solve a particular problem, you determine the number of unit operations. Now, unit operation is an operation that is independent and it can be broken down into simpler operations. It is independent of architecture. It is computed on the basis of algorithm itself. You have an algorithm in place, and based on that, you compute the time complexity of each and every step. Right? If there is a loop, what will happen? If there's a if condition, what will happen? If there's a while loop, what will happen? It's high priority critical in optimal algorithm selection. Now, depending on this time complexity, you can determine whether you want to go with a particular algorithm or not. Because let's suppose you're trying to search an algorithm, right? You can have two options, right? You can use a binary search or you can use a linear search. Now, depending upon the time complexity, binary search works much more faster as compared to linear search. It works in order n and it works in big O of n. So time complexity plays a major role, and there is always a trade-off between the time and space. And in this session, we will be covering both of these things. Okay. So now let's take an example and let's try to determine the time complexity of that particular example. Now let's suppose you are given a for loop, and in that for loop, you are iterating from 0 to n, right? Where n is I is less than n, and then you're doing the plus plus. Now you're doing some work in it, okay? Now since you're traversing from 0 to n, now this is a scenario wherein this will be operated or this will work. The number of unit operations that are present in this for loop is big O of n. Now similarly, there is another for loop in the same program which is operating from 0 to n, okay? And then the same thing, there's a nested for loop in it, and therein what you are doing, you are traversing from 0 to what, let's suppose this is traversed, n is 8, right? N is equal to 8, and in this for loop you are traversing 8 times, and in this while loop you are traversing 3 times, right? Let's suppose you are multiplying every time by 2, okay? So now in this for loop, the nested for loop, the time complexity of the same is n log n. Now, why it is n log n? Because if you observe carefully, number of operations that I told you is 8. So outer loop is working 8 times and the inner loop is working log 2 to the base 8, that is 3 times. So now what is the scenario? What will be the total time complexity? It will be big O of n plus big O of n log n. Okay, this will be the time complexity. Now, what is happening over here? This is a scenario wherein what is happening? It is happening m into n. That means you are multiplying big O of n, that is the nest for the nested one, okay, into big O of log n. So you are multiplying it. Whenever you have a situation wherein you have a for loop inside a for loop, therein you will multiply the time complexities. Now you have a for loop outside and then you have this nested for loop. For this nested for loop, you have n into log n, right? And for this, you have what? Big O of n. Now this is a scenario wherein what happens? M plus n. And in this, you will always take into the consideration the maximum number of resources that are there. so that one for loop will take. So in this, you're taking only n resources, or this is the time complexity of this is n, and in this you're taking n log n. So obviously this is greater, right? So you always say that the time complexity of that particular problem will be n log n, because you're neglecting these smaller terms. As soon as our input is increased, these terms will be neglected and they will not be that much significant while you're allocating resources. Now, what about the space complexity? It determines the total space to be allocated in order to solve a particular problem. Now, whenever you're using any extra space in the algorithm while you are implementing it, that is termed to be as space complexity. It can be in the form of arrays, that extra array that you have used to solve a problem, or an extra linked list that you have used to solve a problem, or a stack or a queue, right? It involves memory of the computer, right? You're involving memory, right? You're taking something extra, right, to solve a particular problem. Let's talk about merge sort. Therein you take extra memory, and in worst case you can take big of n extra memory. That means the number of elements that are present in the array, you're taking the same array as an auxiliary memory, that extra memory, right? It's low priority critical in optimal algorithm selection. When you talk about space complexity, we try to avoid any extra space. We try to solve it with minimal space, right? So that we don't use any of these auxiliary memories. Okay. Now let me take an example of a merge sort, wherein in that merge sort, every time you create a left array for the left side and the right side, every time you create these subarrays and then you calculate them, then you divide them into further and further unless there is no possible division, and then you start merging them. So again, this is a condition, or this is a scenario wherein you are using extra memory of big of n. Now if you talk about simpler examples, let's suppose you are trying to uh, change the positions of even and odd numbers, right? So let's suppose you have these indexes, right, in the array, and you have some values. Let's suppose 10, 20, 15, 20, 15, and 10. Let's suppose these are the values, right? Now you want to use, or you want to find out the frequency of these numbers. So you will be using another array, and in that array, what you will be doing, let's suppose you are picking up this 10 and you are storing it in this. Now you'll be checking, okay, if this is already present, pick up the counter and keep track of how many times this 10 occurred. Now, this will work only for when you're trying to search 10 throughout the array. I'm taking a naive example, right? So I'm taking this example and I'm trying to search 10 and I'm trying to calculate how many times it has occurred. So you place a 10 in this array, and then what you're doing, you will just iterate through the array and then keep a track of this, how many times this has occurred, and keep incrementing your counter, right? So now you're using an extra space, right? Now even if this example is not understood, let me take another example. Let's suppose you're using a recursion, right? Now you might be thinking, okay, internally, you are not using any extra space, but what happens in recursion? Every time a recursion is there, that means function calling itself, an activation record is created and a stack is used internally, wherein your main function will be there and the number of function calls, right? The function calling itself, function calling itself, function calling itself will be we will be pushing it on the stack, and once you have returned, then we will be popping it out, right? So internally you are using an extra memory, and it depends on from program to program. Are you using big O of n, or are you using log n space? But internally, recursion uses extra memory. So an auxiliary memory, or you can say that extra memory, is used while you are using recursion. So that is why we try to avoid recursive problems, and we try to solve our problems using iteration. So, which is obviously that we are not using any auxiliary memory, although it is internally, but still recursion uses extra memory, and that thing is taken into consideration. Now, you might be thinking, okay, now should we use, or should we save space, or should we use less time? Should we go for time efficient algorithm or space efficient algorithm? Now, there is always a trade off between space and time. So, in some problems, they might ask you to save or to write an efficient algorithm keeping the time into consideration, that you don't have to use extra time. But in some, they might say, okay, you can use extra space, but time should be efficient. Or in some cases, they say you use as much time as you want, but space should be less. So that is also there. So there's always a trade-off between both of these things.
Now let's see how we can find the time and space complexity of any given code or algorithm. So basically here I'm going to give you some tips and tricks when it comes to finding the time complexity of any given code, or for that matter even space complexity for any given code. So what happens in any programming language? There are certain constructs or certain programming concepts which we use. Like for example, conditional loops, conditional statements, then no looping constructs. So nested loops. So how does time complexity is found or in these cases? And also the space complexity, like what is the total space being taken while executing that particular code. No space, when I talk about how many variable at a time resides in memory, that decides the space complexity. Okay, and time complexity is again the total time taken, maybe in terms of n we calculate. If suppose n is a number of input, so if n or 2 is a number of input, so for 2 input, what's the total time taken for each code to run or to execute. So we'll assume there are n inputs, and for n given input, how many times the particular code runs, that decides your time complexity. Okay, so I'm going to talk about few small tips and tricks about finding space and time complexity to you, starting from the first aspect, that is your looping constructs. Okay, so if I talk about loop, the very frequently used loop is your for loop. So let's see if int I is equal to 0, and it goes till I less than n and I plus plus, and then there is some statement here, maybe x is equal to y plus z. Let assume that all these variables were declared before in any programming language for that matter. Okay, so what will, if I tell you that okay, find out the time complexity, what time this complete code is going to take if n is the input. Okay, what you will do is, okay, if I assume there is no the number of input is only one. So the for loop will run only one time, and this complete statement will run only one time. So time taken is only 1 unit of time, right? And what will be the space taken that time? Only this variable, these two variables will be stored at a time in the memory, right? So no matter what is the input, every time you need only two variables at a time to be stored there in memory. And when the sum is done, that is discarded, and then only there is only one variable then after that, right? So space complexity is constant here, right? Only 1 unit of space is taken, because every time, no matter how much is the input, every time that same two variables occupies the space. So space here complexity will be O of 1, but time complexity will be, for one element, this for loop will run only one time. So time complexity will be also 1 unit of time it is going to take. For two no elements, this for loop will run two times. Similarly, for n elements, this for loop is going to run n times. So this statement will be executed how many times? N times. So we can say that it takes O of n unit of time. Okay, big O of n unit of time it takes to run the code. Okay, now coming to the another thing is your nested loops. Okay, so guys, whenever you find the smaller codes, you can fragment together and find out the overall time complexity for any larger code. So talking about nested loop. So nested loop, how it runs, for is int, suppose I is equal to 0, I less than n, I plus plus, and then inside this there is one more for loop. Okay, maybe int j of 0 to j less than n, j plus plus, and then this there is a statement, maybe same statement I'm writing, int x is equal to y plus z, and then this closes the bracket. Now how many times this code will run? Again, space complexity is going to be O of 1, guys, because you can see the actual operation being done is only this, and every time it requires 2 unit of space. So it's constant throughout the execution. It doesn't depend on the number of inputs. So it is O of 1, the constant time, the constant space. Talking about time complexity. So you see here, for each value of I, j runs from 0 to n. So if value of I is 1, Or you can say value of I is 0, then this runs from 0 to n, that is n times. If value of I is 1, then also this runs from 0 to n times. If value of I is 2, then also this runs from 0 to n for n times. Similarly, so on. Okay. It means if this goes from 0 to n, this will also go from, for each value of I, it is going to go from 0 to n, 1 to n, because it's less than, not less than equal to. Or you can say 0 to n minus 1, right? It means what? For I value as 0, this code runs n times. Then I value of 1, this code runs n times. I value of n, this code will run n into n times. Yes or no? Like, are you getting my point? So this is mathematical concept here. So n into n, that is the time complexity for this will be O of n square, right? Now, coming to the third type of a concept, if else loop, conditional statement. Okay. So if says if, and there is some statement over here. Okay. Then it says else, and then some statement over here. Suppose the time complexity of this is O of n, and time complexity of this is O of n square. Which will be the final time complexity out of this complete if else loop? Final time complexity will be whichever part of either if or else, whichever part has less time complexity, which is taking less time to execute. If this is taking n times to execute, this is taking n square times to execute, definitely n is smaller, n is lesser value than n square. So the overall time complexity for out of this if else loop will be O of n. Is it clear? Right. Okay. So this is your these are the three constructs. Now let's see if there are sequential statements. Like definitely in any given program, there's not only just for loop or just a nested for loop or if else loop. There are other statements also along with these loops. So in that case, how the time complexity or space complexity is taken care. Again, guys, here I'm not told about space complexity in this if else loop. So space complexity again depends on what statement is being over here. Like at a given point of time, how much is the space being occupied in memory to execute that statement. Does that space allotment depends on the number of input? Then how it depends on number of input will be your space complexity. Otherwise, it always remains constant. Fine. Let's see the fourth aspects where there are other statements also along with these looping constructs and conditional statements in a given program or a code. So now the fourth condition which I'm going to see here is that suppose there is a statement, x is equal to y plus z. Okay. Then there is a for loop over here. Then there is maybe do while loop, so it does something, and then while loop is there. Okay. Then there is again maybe some statement some statement here, maybe a is equal to a plus plus. Fine. Now let's see from, so what you'll do is you'll start from the beginning of the code. So first code here takes how much time? Is it dependent on the input? No, every time it's going to be y plus z only, no matter input is 1 2 3 or whatever. So it is constant time. Suppose this for loop, whatever is the for loop over here, this takes time complexity of O of n. Okay. Then there is this do while loop, which also takes the time complexity of O of n. Okay. Then there is this a is equal to a plus plus statement, which takes constant time. Okay. Then in this case, what will be the final time complexity? So the final time complexity is going to be the summation of all, that is 1 plus n plus n plus 1. Okay. And this will be your, so constants are always removed because it doesn't play much role, because constant is going to be always taking constant time. So that doesn't affect our performance, right, of the code. So we'll remove those. N and n. So n plus n will be 2 of n, right? Again, this is a constant which will be eliminated, and this will be just n, right? So the total time complexity will be O of n. Suppose out of this, one of the time complexity would have been O of n square, correct? So the time complexity here, suppose this is, so in that case it will be 0 1 plus n square plus 1, correct? So O constants will be again removed, it will be n square plus n, right? Again you see here, no, compared to n square, n is a smaller value, right? So our main focus should be on the bigger values because this becomes negligible in front of this one. So our total time complexity will be O of n square only. Getting it? So that's how the time and space complexity is calculated for any given code. Basically, time complexity, some tips and tricks I gave you here, which you can use to calculate. No, simply by just looking at the code, you can make out what is the no time complexity for that given code. There are other methods also like Master's theorem, which is properly used for finding the time and space complexity, but that's a time-taking procedure. It's for a full, process or steps which you have to follow. But these tips and tricks will help you quickly find out or verify the time and space complexity of your given code.
Now let's talk about searching algorithms. And the first searching algorithm that we are going to talk about is linear search algorithm. So what is linear search? It helps us to search an element in a linear data structure. Now let's talk about one example wherein we will be searching some element inside the array. So let's suppose this is an array and the elements are 10, 20, 30, 40 and 50. Now if we are trying to search an element that is 50 inside this array, how linear search works is that it checks each and every element that is to be searched, right? That is there in the element array, right? Let's talk about this example here, 50. Now 50 will be compared, right? We'll check, is this 10 equal to 50? No. Is this 20 equal to 50? No. Is this 50 equal to 30? Is this equal to 40? Is this equal to 50? Yes. So here we were able to do a linear search, right? We were searching for this element inside this array one by one. We compared first it with 10, then 20, then 30, and then 40, and finally then with 50. At the end, we were able to find this element in the array in a linear fashion. Now, this is what is termed as linear search. Now let's talk about linear search algorithm. Since it is a very straightforward, or you can say a brute force algorithm, right? It's a brute force algorithm of finding the element in the array. So this is how it works, right? We have one for loop wherein we will be what iterating through all the elements, that is from 0 to n, and inside that what are we doing? We are looking for the item, that is that element that we want to search, right? Let's suppose this is 50, right? This 50 will be, we were checking if this 50 is equal to the element that is ARR of I, right? And then if that is the case, if we find out the element in the entire array, we will return its index, right? That is index, right? That I, we will return this I. Now there might be the case as well if we are at the end of the array and we have exhausted the last element as well and we were not able to find this 50, right? Let's suppose this is 10, 20, 30 and 40. Now this 50 is not present in the entire array. At that time, what we are going to return is -1. So we will say that, okay, we were not able to find this element whenever we are returning this -1 in this array. And this -1 indicates that we were not able to find that element.
Now let's see the implementation of linear search algorithm. I'll go directly to the Eclipse IDE and will start writing the code. So here I have created the class search, and then there is a public static void main method. Now inside this we'll be writing the concept or the logic for search. So as you saw already, what is the logic behind the linear search, and that is that you have to linearly search each and every element in a given array one by one, starting from the 0th index. Okay, here I am using array. You can use any other data structure also to perform linear search on it. But linear search concept is always that you have to start from the beginning and one by one keep on searching till the end. Fine. So let's see its implementation. So for that, first I'll create a array, okay, which we are going to search. New int, and I'll define the array itself over here. Maybe 6, 4, 5, 8, 2, 1, 9. Okay, so this is the array defined. Now let's perform linear search on this. So we'll take the user input, that which element the user wants to search, or which the integer value among the given the user is looking for or searching for. So for that, to take the input, we use scanner class in Java. So scanner s1 is equals to new scanner, and in the bracket we pass as a parameter the input stream. So system.in represents that I'm going to provide input through keyboard. For this I have to, I think, import the class. Yeah, so scanner class has to be imported. Now we'll take the user input. So let's put a comment also here. Enter the element to be searched. Okay. Now we'll take the user input. So int maybe key is equal to s1 dot. So you can see here next int is a method which is used. So we'll use it directly here. Done. Now comes the main logic of the search, linear search. Okay. In that we'll run a for loop that will begin from the beginning of an array and will go till the end of the array. And at every index we have to compare that the value at that index, is it equal to the key that is being searched. If it is equal, then that index should be returned as an output. If it's not, then it should say that the number doesn't exist which you are looking for. Okay. So that's the whole logic. Let's write a code for it. So as I said, we'll be using for loop for int I equals to 0. I should be less than what? A1 dot length. So A1 dot length gives the total length of the array, whatever is its length. So in this case, it will give you 1, 2, 3, 4, 5, 6, 7. 7 as an output. And then I plus plus. This for loop, what you have to do? Compare. So again, for comparison, you have to use if loop A1 at ith index, is it that equal to the key which we are searching? If it's equal, then what should be done? If it's equal, then we should print first of all element is at index uh, I, right? That's it. Okay, what will happen if the element doesn't exist in the complete array? What has to be done for that? Okay, here there should be this. Okay, as it is a string, it should be in double quotes. So yeah, so what should be the case when there is no element, that element being searched is not there in the array? So in that case, let's use a logic here. What I'll do is I'll initialize one variable that is maybe count is equal to initially 0, and every time when it is, if it founds any number, it will increment itself. Okay, so count will be 1 now. And if suppose it doesn't find that particular element in the complete array and the complete for loop runs, so count will remain 0, because it will only increment if this if loop is true, and if loop will be true only if condition will be true. So if condition will be true only if any given element in the array is equal to the key which you are looking for, right? Until unless count will remain 0. So that's what the logic I'm going to use. So after this, I'll write that if count is equal to 0, then in that case, should print that element not found in the given array. Fine. That's it. So that is the simple logic behind your linear search. Now let's see. When we run this program, it asks the element to be searched. So these are the elements 6, 4, 5, 8, 2, 1, 9. So out of this, suppose I give as the 8 as an input. Okay. So it says, okay, one second. Element not found in the given array is also being printed, and the output is also being printed. So let's see, something is the mistake. I think this closing of the loops. Yeah. This should be outside the for loop. Okay. The for loop ends here. So outside this, it should be. Now let's run, check if it gives the correct output. So yeah, you can see 8 is the element entered. So it says element is at index 3, 0, 1, 2, 3. So yeah, at the third index, 8 is present there, right? If I enter some, look, like I'll run the program again. If I enter some value, suppose 78, 78 is not there in the array. It should say element not found in the given array. So that's the simple logic behind your linear search. So we saw the implementation of linear search in Java programming.
Now let's talk about the time complexity of linear search. Now, if you observe carefully, let's try to understand this best case, right? So now if you are looking for the element, and let's suppose these are the elements in the array. Now, let's suppose in best case, what can happen? You're looking for 10 and 10 is the first element in the array. Now, how many iteration did you require? Did it require to find you the 10? None, right? The constant time, right? Only one single unit operation was done and you were able to find this 10. So this is the best case time complexity where the element that you're trying to find is the first element that you search, right? In this case, you are looking for 10 and 10 is the first element. So this is your best case. Now, what about the average case and the worst case? Now, let's suppose average case is that you were looking for an element which is at the middle point, right? Let me just see. 0, 1, 2, 3, 4. Now, or you can put another and looking for 60. Now, in this case, or you can just skip it, okay? No need to add one more. Okay, so now you're looking for an element which is somewhere around in the middle. Okay, in this case, you're looking for 30. Okay, so now if you observe, you are only iterating half of the elements, that is 5 by 2, which is nothing by n by 2, since constants doesn't play in do not play any role when you're talking about time complexity. So that is why average case still boils down to big O of n. Now, what happens in worst case? You're looking for an element that is 50 and which is present at the end of the array. Or in the worst case, you're looking for something that is not present in the array, that is 60, let's suppose. And in that case, you will still iterate through the entire array. And that is why the worst case time complexity in that case will be big O of n, because you are iterating through the entire array and that element was not found. You're looking for 60 and that is not present there. So you're iterating through the entire array, that is n operations are done. So that is why it boils down to big O of n. Now let's talk about the space complexity of linear search. When we are trying to find the element in the array, that is 10, 20, 30, and 40 and 50, we were not using any extra memory, right? We were not using any auxiliary memory, that is what we mean by auxiliary memory or extra memory, in order to find that element. We were just looping around these elements one by one, and we were doing it on the same array that we were given, right? Since we are not using any auxiliary memory, that can be in the form of what? A stack, a linked list, or an array, or a string, or a queue. We are not using these auxiliary memories because they don't they are not required, right? We are searching for an element in this particular array that was given to us, right? So the space complexity of linear search is constant, right? We were able to find it in a constant amount of space. Okay, we are not using any extra space. Now let's try to understand binary search algorithm. What is binary search? So binary search is one of the searching techniques, right? Like we saw in linear search, wherein the time complexity of linear search was big O of n, right? We were iterating through all the elements, and now this is a much more efficient algorithm as compared to linear search. Now again, why do we need searching is the thing that, let's suppose if you have a given set of elements and you want to search if that element is present in your array or not, that time, right, we can use either linear search or binary search. Now binary search is much more efficient and it is used on a sorted array, or it can be used on an array wherein some order is maintained. because based on that order, we will divide our array, right? It is a searching algorithm which is or which follows the divide and conquer strategy, right? Let's suppose this is our array, and now since it will be divided in such a way that we can neglect one part of it, right? We will be dividing and then conquering. That means we will be then searching for our element. Now, let's suppose we are looking for something that is, now let's take an example wherein this array is written or the elements contained in this array are in such a way that we if we skip this part, or the left hand side will be skipped or the right hand sides can be skipped in such a way that they don't affect our output. So every time in linear search, our search space is reduced unless and until we find that element or the array is exhausted. Okay, so our search space is reduced to half in every iteration. So this is what a binary search is. We'll look for an element in such a way that every time we are neglecting half portion of the array. And let's take an example when we have this entire array. So first half, that means if four elements, eight, if there are eight elements, four on this side, four on this side, these four will be neglected. Then we have two on this side, two on this side, these two will be neglected. Then one on this side, one on this side, then this one will be neglected until unless and until we find that element or the entire array is exhausted, right? So this is how your binary search works. Now let's try to understand binary search algorithm. So first we are going to understand the iterative approach, and then we are going to understand the recursive approach. So iterative, as the name suggests, we are going to use for loops, right? We will start with a for loop and it will iterate, and we will iterate unless and until the beginning is less than the end, right? So because we will be updating our both beginning in some cases, and in some cases we'll update our end. Now, what happens? Now, since we know that in this iterative approach or in this binary search, it doesn't depend whether we are using iterative approach or recursive approach, the logic will remain same, right? So we will be having this array and it will be in some order so that we can neglect some part of it. It doesn't have to be sorted always. We can still apply binary search even if the array is not sorted, but still some order is there so that we can neglect some part of it, because again, keeping this thing in mind that it follows the paradigm of divide and conquer. So now we have this beginning and end at place, and we will always iterate when beginning is less than end, right? So now what happens after that? Now we have this array, and now what we will do, let me take new pointers. So this is your beginning and this is your end. So this is your beginning and this is your end. Now you will be taking a new middle index, right? M, let's call it M. And now let's name these things 0, 1, 2, 3, 4. So you will do what? Beginning plus end divided by 2, so that some part of it can be neglected, right? So it will be 2. So your mid is at this position. Now you will see, okay, the element that I'm looking for is, let's suppose, is 50, and the element that I am currently at is 30. So obviously it will be never from this side. There is no chance that we will be able to find 50 from this side, that is the left hand side, right? First we will check, okay, is this 30 equal to 50? No. So this will never be executed, right? Then we will check, is my item that is there, is this 30 less than or greater than 50? If it is greater than 50, right? If the element that is, if item that is 50 is greater than 30, right? Which is in this case, our 50, that is the element that we are looking for, the item is this point, is greater than 30. So there is no point that it will be on this side. So we will skip or we will neglect this half portion of the array. So that is why our new beginning is updated. It will be new, it will be middle index plus 1, that is middle index was 2 plus 1, that is this will be our new beginning. So we have smartly skipped the half portion of the array. So now let's rub all of these things, and now let's see what happens in the next iteration. Now we'll keep this thing in mind that we are not looping or we are not exceeding this limit. That is, beginning should be always less than, or it should be always less than or equal to end. Okay, so this condition should be maintained. And similarly, we'll again divide our array and then look for the same things, right? First we'll look for the element, then we'll skip some part of it. So this is the iterative approach for binary search, right? Now let's look at the recursive approach or recursive algorithm for the same. So again, beginning, the ground rule will remain same. We'll always iterate, or we will always recursively call binary search unless and until this beginning is less than end. Done. Now what happens? We'll again find middle index, that is beginning plus end divided by 2. Then we will look for the element. These three steps will remain same even if you're using recursive approaches. Now what happens in recursion, right? We again call the function again and again. That is what is recursion. So in this entire tutorial, we will be covering recursion as well, but in the later part of the course. Here you can get a good intuition, or let me give you a brief intuition about how recursion works. So let's suppose this is your activation record. Every time when a recursion is there, an activation record is called. So let's suppose you have these three statements. And let's suppose in your algorithm, you have statement P1, P2, and P3, right? And at P2, you are calling the function again, right? You're calling this function again. So now what happens? An activation record is called. He will check, okay, is this statement executed? Yes. So one will be executed. Is second executed? Yes. So second is executed. But at second, you're calling this function again. So at that time, again, a new activation record is created. Now this third step is left behind, right? Now this will be covered when we come back or return from this function call that we called here. So let's suppose this function was here. Now in here, you are returning, right? This function called, let's suppose this is not less than beginning. Beginning is not less than end. So this will be somewhat, this case is relatable, right? This is similar to what we are looking for, right? Let's suppose there is some similar situation wherein beginning is not less than end. At that time, you will be returning from this. Right now, once you have returned, you will be then calling this function again, but this time around for this. And let's suppose this time around you are calling this one is executed, step one is executed. Now again, this activation record is called, this activation record is one, and then again this is called, right? This is executed again, this two is called again, a new activation record will be created, and these three steps, the step third will be still left for execution. So now here you return, right? Then it will go back to this step, right? And then once you are done with this, now there are two positions or two possible scenarios where you can return. Either you are returning from this function just like we have executed this condition and we return, right? Another is that once you are done with this entire activation record, at that time you will also return. Okay, so these are two scenarios. Now you have executed this, there is no step to be executed, it will return. Now this was left behind, this will be executed. Now nothing is to be executed, it will go to the caller, which was this, and finally it will go to the main method wherein we call this at the first place, this function. Okay, so this is how an activation record is created. A stack is maintained. Okay, even if you might be thinking we are not using any extra space, but whenever recursion is there, an extra space that is in the form of stack, that stack is maintained. So you need to keep this thing in mind while you are playing around with space complexity at the time when you're using recursion. Okay, so now with that being said, let's clear our screen and let's see how recursion is called here. So again, now recursively what we will doing, if now we have this mid, right? And let's take an example of an array: 0, 1, 2, 3, and 4, 10, 20, 30, 40, and 50. So middle index will be 0 plus 4 divided by 2, that is 2. So this is our middle index, right? So this is 0, this is our beginning, and this is our end, right? So now we are hit here, right? So we again check the 50 that we are looking. This is our item that we are looking for. Okay. So is 50, and this is our middle index. Is 30 greater than 50? No, it is not in this case. So this will never be executed. This is not executed as well, right? Now, what about this condition, the else part? Now, what we will be doing, we'll be skipping, since this 30 is less than, we'll be skipping this part and we will focus on middle index plus 1, which is nothing but this. So, this will be our new beginning and our process will start moving, right? So, now again, then the same thing will happen unless and until this condition is false, okay? So, this is how your binary search works when you're using recursion. So now let's try to understand binary search and let's see its demonstration. Okay. So we are looking for 20 and this is our array, right? 10, 11, 16, 20 and 23. Now this array is sorted, right? So we can apply binary search, okay? Since we can neglect some part of the array based on some conditions, okay? So now our beginning in the first iteration, what is happening? Our beginning is 0, our end is 4, and our middle is this element. Now what we will be looking for is 16 equal to 20. No, it is not. But 16 is less than 20, so we will skip this part. In the next iteration, what happens, we'll be focusing on these three elements, right? That is 20, we will be focusing on this part rather, if we say, we'll focus on this part, right? Focus on this part. Okay, so now in the second iteration, what will be happening, our beginning is updated. Now our new beginning is this point, our end will remain at its own position. Now we'll find the middle index, so it will be 4 plus 3, that is 3, that is 7, right? And divided by 2, it is 3.5, right? So since this will be truncated, right, the truncation will happen and the integer that is there, the middle index will be 3. So this is our middle index, right? So you can see middle index is 3. Now, is this element that we're looking for? Yes. So we'll return the index. So we found our element at index 3 and hence we return 3. Because if you observe carefully, it is returning, if the element is found, it is returning the index. So this will be returned. Okay. So this is how binary search works.
Now let's see the implementation of binary search algorithm in Java programming. So I'll directly go to the Eclipse IDE and we'll type the code there. So yeah, I'm already here on Eclipse IDE and I've created a file with which is having a class name named as search, and then public static void main method is also created. Now let's create a function for binary search and we'll call that function of binary search from the main method on a given array. So to create a method, public static void, not void, it's going to return the index which is found wherever the element is found. So binary search is nothing but it's a searching algorithm, right? And we have to search for a given key in any given array. And if it is found, it returns the index. If it doesn't found, then it says that the element is not found. So it will return int, that is the integer, the value of an index where the particular value is found in the array. So int, let the name be binary search. And it takes what all it takes as a parameter. So it takes the array as a parameter. Okay. 1 second. Yeah, it will be A1. So first it takes array integer, in which you have to search for the given number. And then it takes the value which will be searched by us, right? So it may be an int value, as it is an integer array. So let's have that the user is searching for an integer number. So let it be a key. And then to implement binary search algorithm, we need the first starting index and the last, that is the ending index of a given array. So that has to be given as a parameter here in this function of binary search. So int first and int last. Okay. Okay, so it's giving an error saying that you have to add a return method. So need not worry, as when we'll add return method, that error will definitely not be highlighted over here. Now, what's the logic of binary search? So, binary search does what? As the name itself says, binary, meaning half. It divides into two halves. From the mid of the given array, it divides the array into two halves. Okay. The first, from starting from first index to the mid is one array, and from mid to the last is another array. And then it searches in the respective half. Like for example, the element which you're searching for is greater than the element in the mid. Then it will search the second half. If the number you're searching for is smaller than the middle element, then it searches the lower half. That's the logic behind binary search. Let's write that. So what will happen that, okay, if will come later, first we'll write int mid, we'll find the middle element. Then only we can divide into two halves, right? So middle element will be first plus last divided by 2, right? Let's put this in brackets. Okay, middle element found. Now let's divide it. So for that we have to put a condition first. First condition is that always the search should be between the given range of an array. That is between first and last. Correct? You should not go on like searching, like suppose the arrays are stored from index 0 to 10. And there's no point searching after the index 10, right? Or before like 0, that minus 1, minus 2. Correct? So which the first condition is that is first should be less than equal to last. Okay. Now inside this condition, all other conditions will come. Now that what is that condition? If suppose the given key is found at the mid of the value, like it is dividing from mid, like the numbers, if the number is lesser than the mid value, then it will search the lower half, greater then it will search the upper half. But what if it is equal to the mid value itself? That also has to be checked. So if key is equal to mid, then in that case it will just return that particular index, that is mid. Okay, it will be a closing here. Okay, now if it is not at the mid, then what has to be done? Then if the key is less than the mid value, then in that case what has to be done is go to the or implement the binary search again on the lower half of the complete array. So you have to return from here what? Binary search. That is, you have to call the method again. It's a recursive call to the same function. And here you will pass the array itself, A1, and then you will pass the key. Now what will be the first element? First will remain first, but end will become the one value lesser than the mid minus 1, right? Then it comes as else. You have to return what? Binary search and implement on the given array A1. Input will be the key. In this case, your last will remain the same, but your first will change one value more than mid because the second half is being searched now. So mid plus 1 will be your first and last will remain your last. Getting it? Semicolon. Okay, we'll see what's the error here. Unreachable code. Okay, let's fix this. So mid is here. Okay, this is opening here, closing over here. This is closing, correct. This is closing over here, correct. Okay, let's close this over here. Okay, so okay, so it is closing over here. Now, what if the element is not found at all? It gets searched everywhere and still it's not found. Then in that case, it should return -1. Fine. Now let's go to the main method and call this function. So for that, first we'll create an array itself. A1 equal to new int I'll define the values also over here. Let's take some random values: 4, 6, 2, 9, 1, 7. Okay. And let's call the binary search as a function, right? So let's call this. It will store the value in the index, binary search, and I'll call over A1. The key I'm searching for, I'm giving it manually here. Suppose I'm looking for 6. The first will be your 0. First index is 0 in the array, and the last index is array length minus 1, because length starts counting from 1. So 1, 2, 3, 4, 5, 6 will be the value. But actually the index starts from 0. So it will be 1 less than 6, right? 0, 1, 2, 3, 4, 5. So it will be A1 dot length minus 1. Okay. Then we can put a statement here saying that if your index value is equal to minus 1, then in that case, it should print that element not found in the given array. Okay. Else it should say element found at index plus index. Okay. Let's run the code. So I'm searching for 6. 6 is there in the array, right? So it would say the, okay, cancel it. There's some error is what it's showing. Okay. So there will be a semicolon. Right. Let's run the code. So it says the element not found in the given array. So I'm looking for 6, but it's not being found. So it's returning minus 1. Okay, what's the error? Let's try to fix it up. This is A1 dot 0. This is A1 dot length minus 1. 2. Okay, we'll see here. Some issue with this, I guess. Yeah, so I looked at the error, and what I could see here is that if we change the numbers here, that is the elements of the array, to be in ascending order or in sorted order basically, because the first requirement of implementing binary search is that the element given should be in a sorted order. Okay, because then only you can compare that from the middle element. If the key is greater, then it should be in the later half, that is second half. And from the center element, if the key being searched is smaller in value, then it should be in first half. And that comparison is only possible if it is in a sorted order. So that's the only change I did here, is that change the values of the array, that is the elements in the array. And then let's try to execute it with, suppose I'm searching for 3. Okay, here I'm hard coding it with the key which was being searched. There is 3 over here. So let's run this code and check. So you can see here it says that the element 3 is found at index 1, starting from 0. So 0, 1. You can check for any other. So maybe 6. Also, if we check, so we'll get that it is at index 3. So 0, 1, 2, 3. So that's how the binary search works. If suppose I'm checking for something which is not there, then it should say that the element not found in the given array. Okay, so that's all about your binary search and the implementation of binary search in Java programming.
Now let's talk about the time complexity of binary search. Now, in the best case, now what is the best case? Now let's take an array, and in that array, 1, 2, 3, 4, and 5. These are the elements. Now, the best case is that not that if the element, like we saw in linear search, that this element, when we are looking to search for this same element, at that time that was the best case scenario for linear search, right? But in this binary search, the best case scenario is when your middle index is at this location, and you're searching 3 in the entire array. So at that time, this will take a constant amount of time, and this is the best case time complexity in that case. Okay. Now, in average case, what happens, right? If you talk about this algorithm, let me just clear out my screen. So it follows a paradigm of divide and conquer. So let's suppose you have 8 elements first in the array. it will be divided into four, because these four, or either it can be on the left side or on the right side, will be neglected. And then we deal about these, then we focus on these things. Okay, these four elements, again it will be divided into two and two. Then we will neglect two elements, then one and one. Then again there will be one of the element can be neglected, so there are one and one, so we focus on this element. So the entire operation will be done, or entire searching will be done in three steps, right? Now if you I take an example, and if I do a log 8 to the base 2, what should be the value of this? Obviously when I do this, this can be written as 2 raised power 3, right? And this can be written as 3 into log 2 to the base 2. Now this is 1, and now you get the answer as 3. So this 3 and this 3 are equal. That means if I talk about the worst case time complexity of binary search, it will be somewhere around log n. As it also, as we saw in three steps, we were able to find the element, and the log n, that means log 8, the answer of that is also 3. So you get the point, right? So the worst case time complexity of binary search is log n, and same goes for the average case, wherein it will be somewhere around log n divided by 2, neglecting log n divided by 2, neglecting the constant terms. It will be again, or it boils down to big O of log n. Okay. Now let's talk about space complexity of binary search. Now, when you talk about space complexity, right, we only think of auxiliary memories, or you can say that, what any extra memory that you guys have used. Since we did not use any extra memory, that can be in the form of array, or it can be in the form of stack, or it can be in the form of queue, or linked list, or even strings, right? Since we never use these extra memories in our implementation, so the space complexity of binary search is big O of 1. That is, it takes a constant amount of space. So the question is that what is sorting? So you might be thinking, why do we need these sorting algorithms? So if I told you that you have a bunch of students, right? You have a bunch of students and they each have their roll number. They are not present in what, in a numerical order, or you can say they are not present in some order. I want that order to be maintained. Let's suppose you have 1 to 10 students in those bunch of students, and each are having roll numbers from this range, from 1 to 10. Now some of them are absent, and some of the roll numbers have left the school, but the roll numbers are not changed yet. Now, what I told you, please sort them or arrange them in such a manner so that I can easily understand which roll number is after which, either in ascending or in descending order. Let's suppose 1 is there, 2 is there, then 6 is there, then 8 is there, then 10 is there. So rest of the roll numbers I can easily depict, okay, these are the ones which either are not there or are absent. So in order to do so, we have these sorting algorithms in picture. And one of those sorting algorithms is insertion sort. Now, it is the simplest, easiest, and a brute force sorting algorithm. Now, what do you mean by brute force? Brute force means straightforward, right? In a naive way, it means straightforward. That means you're not considering any efficiency, or you don't care about time complexity or space complexity. You just straight away sort it with the most simpler and naive approach. Okay, in this brute force algorithm, what happens that, let me give you an example, right? Obviously we can sort with the help of this insertion sort algorithm. You can obviously sort either in ascending or in descending order, right? Let's take one example. We all know about the card game, right? Wherein you have a bunch of cards, right? Suppose you have a single card that is in your hand, right? And you have a bunch of cards available on the table. Now you start picking those cards one by one. Obviously, the one that is in your hand is sorted, because if I told you to sort a number one, obviously there is only one element in the array or anything, right? In the linked list, I told you to sort it. But if you're having only one element, that is itself sorted, right? You don't need to sort that. Similarly, what happens now, this card is in your hand, right? It's just like playing cards, right? Now you have this one card in your hand and it is obviously sorted. Now what you will do in the next turn, you start picking up one by one from these set of cards that are available on the table. Now let's suppose this is 0. Okay, I'm considering these numerical values so that you can understand and you can just connect the dots, right? So what happens? You have the 0, and now you start comparing it. Now we are considering the scenario where you are trying to sort in ascending order. Okay, so now let's try to erase these things so that it's easier for you to understand things. Okay, so now you have these two elements, right? And now we are considering the case wherein you are trying to sort in ascending. So you check, okay, if 0 is less than 1, yes it is. Now you swap them. Okay, now you have 0 and 1. Now these are the two cards that are present and both of these are sorted. So now insertion sort works in such a manner that you will always have two parts, right? One is the sorted part, obviously, which is in your hand, and one is the unsorted part, which is on this deck, right? So similarly, you will start picking elements, or you can start picking these cards one by one and keep sorting them. Okay. Now this is one simple scenario wherein you can apply what insertion sort. Right. This is the most simpler way one can explain or one can understand this insertion sort algorithm. Now it is simple, right? Now you start picking these elements and you keep sorting them, and at the end, when all of these elements are exhausted, you will get your sorted array. Now let's try to understand insertion sort algorithm. So in this algorithm, what happens? Obviously, now we know that we will have two parts, right? One is the sorted part and another is the unsorted part, right? So obviously, the one element that is present in your hand, or the element or the card that is in your hand, and there's only one element there, right? The one element in your hand, obviously, that is sorted, right? So we will not consider that first element, and we will start our iteration from the second element, right? Now we understand why we are doing this, that we are starting from 2 to n minus 1 or 2 to n, depending upon the array that we are starting from. Either we can start from 0 index or we can start from 1 index, right? So we always start from element number 2, right? And then what we will do, we'll just store this value inside some temporary variable, and then we will check if that element is less than the element that we have in this sorted part. If that is the case, then we will shift their positions, right? And we will get both. Now we will have two elements into picture, that is 0 and 1, and both of these will be sorted in ascending order. And then what we will do, we'll consider the rest of the cases, that is starting from 3 to so on to n. Okay, now you might be thinking, okay, how does this thing happen? Let me take an example and let me show you how. Let's consider this array that we have over here, that is index 0. These are all the indexes that we have, and this is our array, that is 23, 10, 16, 11, and 20. So in the first step, we are making partitions. Now this is our sorted part, that is the first element, and this is our unsorted part. Now what we will do in the first iteration, this is our iteration number 1, because this is the case wherein we will start moving from second index, that is first index, if we consider from 0, right? So we consider from second element and so on to n, right? So now in the first iteration, what we will do, we'll compare these two values. Okay, let me just erase everything so that it's easier for you guys. So now we will compare these two. Now obviously 10 is less than 23. What we will do, we'll shift their positions. Now this is your sorted part and this is your unsorted part. Again we will do the same thing, right? So in second iteration, what we will do, here comes 16. Now what we will do, we'll compare it first with 23. Okay, we know now, okay, 16 is less than 23. So now what we will do, we'll swap their positions. So this is 16 and this is 23. Now what will happen? Now 16 will be compared with 10. Obviously it is not less than 10, so it will remain as at its own position, that is its new position at index 1, right? So this is the second iteration, and after second iteration, this will be your sorted part. As you can see that I have bolded this text, right? Bolded the borders of these two elements, and bolded the same for these three elements, because this is the sorted part that we have over here, and this is the unsorted part. Now what will happen in the third iteration, that it will check for this number that was there, it is 11. So for 11, what we will do, we'll compare it with what
read this thing. Now we'll take 11 into consideration, and now we'll check it. We'll swap them. Then 11 is here, 23 is here. We'll check them. We'll swap them. 16 is here, 11 is here. We check them. So since 10 is less than 11, so nothing will happen. So in the third iteration, what will happen? We will have 10, 11, 16, and 23. These are all sorted, and we are only left with one element which is unsorted, right? Now in the final iteration, what will happen? That 23, now this 20 will be at its original position, that is here, and rest of the elements will be sorted. Now since we have exhausted all the elements have been exhausted, and we at the final step, that is in iteration 4, we will have this array that is sorted.
Now let's see the implementation of insertion sort algorithm in Java programming. So I'll directly go to the IDE and we'll type the code and we'll see how the logic of insertion sort is implemented there. So yeah, I've come to the Eclipse IDE here. So already I've created a class by the name of sort, and then there is a main method, public static void main. Now here I'm going to write the logic for insertion sort. Okay, so as we know that insertion sort does what? That it compares a given element with all other previous elements in an array, and if it is smaller than the previous elements, it keep changing its indexes, and it fix itself to that index where it fits well. Like suppose it is the smallest of all the elements, so it will be at the very first index. So that's how it is. So let's see how we can write the logic of this insertion sort using Java programming. So what I'm going to do here is that in this class, I'm going to create a method, public static. I'm creating static method here because we will not need the object of the class sort to call this method. Directly without using the object itself, the method can be called. That's the reason static keyword I'm using for the methods over here. So it becomes little easy and convenient in programming. So public static, return type won't be there for this. We'll print in this itself after sorting it. So insertion sort, let that name be there. And we have to pass to this the array itself, that's it, as a parameter, the array which had to be sorted. Now, as the logic of the insertion sort itself says that there will be one pointer or one index variable which will start or traverse the complete array from beginning to the end, and there will be another variable which will keep track of the previous elements to that particular index. Okay, so we'll have that j which will always point to I minus 1. Okay, but all this should be for the complete for loop, that is int of I, which is equal to start from 0, and it should be less than your a1 dot length and I plus plus, it will increment. Yeah, so from the beginning, yeah, this should be this. Okay, so from the beginning of the array to the end, we will perform this operation. And what is that operation? Let's write down the code for that. So okay, it says that there is a missing block here, so let's put this. Okay, so int j I have taken a variable which will always point to the previous element, then the element being right now sorted, that is ith element. Okay, why that is required you will understand soon. Let there be a variable which also holds the value which is being sorted right now, that is at the ith location. So a1 of I, whatever is there, will store it separately in one variable. Okay, so that later on it is used. Now I'll tell you where it is used. Once I'll write the rest of the code, you will understand what exactly was the benefit of using this. Now we have to compare the given element with all other previous elements, right? Previous element, how will you know these are the previous elements? Starting from that particular index to the beginning index, that is 0th index, right? That all will be your previous elements. So that's the reason j greater than equal to 0 has been used. So everything from 0 to the current ith element is your previous elements for that particular index which is being sorted right now. And you have to also check here if the value is less than or equal to a1 of j. Then what we should do? If the value is less, then it should swap it, right? Meaning j plus 1 will be equal to a1 of j. Meaning whatever is j will go to, whatever is at j plus 1th element, that is actually your ith element right now, will become your jth element. So jth index element will now become j plus 1th index element. Okay, that's the point here. So now j will be equal to j minus 1, because we have to compare all of the previous ones. So we'll decrement one time each time for j, and then we'll go till the beginning to compare that is there any other number which is greater than the current element which we are sorting. If it is greater, then again the swapping will happen. That swapping meaning it will shift all other elements and make space for that smallest element to come there. Now after while loop, what we'll do is whatever is at the j plus 1th location, one second, j plus 1th location will become your new b, because with this we are going to again compare the complete thing, and this for loop will end here. So after the for loop, now it will sort it. That's what the complete logic was of insertion sort. Now let's print the element. I plus plus. In this we have to just give a print statement for a1 of I. Okay, let's give a space here so that it looks little neat. Okay, so closing of for loop and closing of the complete function. So that's it about insertion sort. Now let's call that in this. So for that we have to create an array first. To new int, let's put that in some order: 3 7 1 9 4 2 6. Okay, let's see if it gets sorted. We'll call insertion sort here. Sort for a1. That's it. That should serve our purpose. Let's see. Okay, it doesn't print. So one second, let's see why is the print not happening. This is the closing of for loop. This is the closing of this for loop. Okay. Okay, but since cross check from beginning, b is less than a1, j. So a1 of j plus 1 is equal to a1 of j, and j is equal to j plus. Okay, this is okay. Fine. J is equal to j minus 1. And a1 of j plus 1 will be equal to b. This is correct. Then for loop and then print. Okay, let's see. Yeah, so you can see here, this is the output 1, 2, 3, 4, 6, 7, and 9. So elements given here in the array are sorted. So I hope you understood the logic which is being implemented over here. That is, for the complete array starting from beginning to end, what it does is that it compares a given element with all the previous elements and find out the correct place to be inserted for that particular element. Okay, for example, 3 it will start, and 3 will be compared with, there is nothing before, so nothing it will compare with. It will come to 7. Now 7 will be compared with 3, so 7 is greater than 3, so 7 will remain there. Then 1 will be compared with 7. 1 is smaller than 7, so 7 will come at the location of 1, and 1 will go at the location of 7. Getting? So 7 will be here. Okay, 1 will not go at the location of 7. 1 will be stored in some temporary variable which was over here as b. Okay, so 1 will be stored somewhere in b. Now this 1 will be compared with 3. So 1 is still smaller than 3 also. So 3 will be now shifted to the location of right now where 7 is. Okay, so 3 will be here, 7 will be here, and 1 will be still in a temporary variable. Now as we reach to the beginning of the array, so 1 will be inserted there. So it will be 1, 3, and 7. So that's how it is. Now I will increment to 9. 9 will be compared with whatever previous elements are. So now here it will be 7, right? So 9 will be compared with 7. 9 is greater than 7, so nothing to change. So this was the logic of insertion sort, which is what we have written over here. Okay, this while loop is nothing but it compares a given element with all the previous elements. And that element which is being compared right now is stored in a temporary variable every time. It is over here in B. Okay, and this complete thing goes till the end of the array starting from 0th index. So that's all about the implementation of insertion sort algorithm, guys.
Now let's talk about insertion sort time complexity. So in the worst case, when all the elements are in haphazard manner and we need to sort them one by one. So obviously we are talking about first the outer loop which runs from 1 to n, and then the inner loop which runs backwards, and in the last, first we consider, in the first iteration we only consider the 0th element. Then as we move along, it will be running from n to 0th element, right? We will be considering the whole n elements. So in that case, the time complexity in the worst case will be order of n squares, because we have two nested loops. That is, one is for loop, and inside that for loop we have that while loop, right? So this is the in the worst case, and it happens also in the average case, where some part or the sorted part is already there, and it is, let's suppose we have 5 4 5 6 7 8, and then we have the unsorted part. So half of the elements are sorted and half of the elements are not sorted. So it will be n square by 2. So we are not considering the case where we talk about constants and we are negotiating the constants. And in that case, the average time complexity will be n square, right? But the most important thing that is there in this time complexity is the best case. That means when your elements, that is 5, 6, 7, 8, 9, and 10, when the elements in the array are already sorted, what happens in this case? If you observe, the for loop that runs from 1 to n will be always there. So n is always there. The time complexity, the big O notation, big O of n will be always there. But in this while loop, wherein we were checking for if j is greater than or equal to 0 and if AR of j is less than 10, right? In that case, this will never be executed, because this AR of j will always be less than, will always be greater than 10. Why? Because we are talking about this element and we are checking if this 6 is less than 5. No, it is not. If this 7 is less than 6. No, it is not. So this condition will always be false for all the elements. So in nutshell, we are just checking these steps only once in every iteration. So that is for the reason that the whole time complexity in the best case will be big O of n and not big O of n square in the best case. Okay. Now let's talk about insertion sort space complexity. If you have observed in algorithms and in implementation, we never talked about any auxiliary memory, right? We were not using any extra space, either in the form of array, linked list, stack, queue, or anything, right? So that is for the reason the space complexity of insertion sort is big O of 1, that is constant amount of space. Now let's talk about insertion sort analysis, wherein we will be analyzing comparisons, number of swaps, stable or unstable, in place or out place. So first let's talk about number of comparisons required. In this we will talk about two scenarios, wherein we will talk about worst case and average case. In worst case, the number of comparisons required is n square by 2. Now, if you talk about average case scenario, it is n square by 4, which is twice as much as this, right? It is 2 times. If you talk about number of swaps that are required in insertion sort, in again we will talk about two scenarios, average and worst case. In average case, it is n square by 8, and in worst case it is n square by 4. These are the number of swaps required. And if you want to check those, if these statements hold or not, if these equations hold or not, you can always take an example wherein you will be considering both the cases, even as well as odd.
So take an example and run through it. Now, if you talk about stability of insertion sort, it is a stable algorithm. What do you mean by stable? So if you have an array which contains 1, 3, 1 dash, and 5, in this array, the relative position of these two ones, that is this one and this one, let me change the color and let me show you. The relative positions of this one and this one will remain intact. What do you mean by this thing? That whenever you are sorting it, you can sort it in two different ways, right? This is also sorted and this is also sorted. That means you can either have 1, 1 dash, 3 and 5, or you can have 1 dash, 1 and 3 and 5. This is obviously that this number is repeated, but this is the first number. This is this occurred here the first time, and here it is the second occurrence. Now you want to keep their relative positions intact, right? So both of these are sorted, right? But if you talk about stability, this is known as stable and this is unstable. Okay. Now, insertion sort, whenever you are trying to implement insertion sort, it is stable. That means the relative positions of both these ones will be intact. Okay. So if someone asks you if insertion sort is stable or not, you will say yes. Why? Because the relative positions of the numbers that are repeated remains intact. Now, what about this in place or out place? Since we are not using any auxiliary memory, right? We didn't use any stack, queue, linked list, or array. That is the reason that whenever you are not using any extra memory, it is supposed to be in place algorithm. So if an algorithm is sorted within the array that was there earlier, that means you're not using any extra space, that algorithm is known as in place algorithm, which is evident now in insertion sort as we are not using any extra memory. So insertion sort is an in place algorithm. Now let's look at the example wherein we will implement insertion sort. If you can see, we have this example over here wherein we have 6, 5, 3, 2, 8, 10, 9, and 11. And we have been given this key. What this key signifies that the maximum swaps or comparisons needed for this 3, either on the left side or on the right side, right? The number of positions that this 3 needs to get to its original position is 3. So this is a question that is known as nearly sorted array or k-sorted array. We do not need to sort all the elements in the array, but we are specifically looking for those elements which are not at its original position. And if we want to get them to their original position, the maximum comparisons or swaps that we require is 3. So if you see this 3, the original position of this 3 is this 5. That means in the sorted array, it will be here. Similarly, if you talk about this 2, the number of swaps that it should do is 1, 2, and then it will be at its original position. Or you can say that 1, 2, and 3. So max it can go to 3 positions. Okay. So similarly, it will be the same for all the elements. So at most 3. Okay. And at least it can be that it doesn't need to move at any location, that it will have its own original position. Just like in 11, you see 11 is at its own position in the original array as well as in the swapped array. So at most you have 3 positions.
Selection sort algorithm. Now let's talk about what is selection sort. Now before we move to this sorting algorithm, let's try to understand what is sorting. So if you have a bunch of students, and out of those bunch of students, let's suppose some of them have either left the college or school, or they are absent. Right now you want to arrange the remaining students either in ascending order or in descending order. So for that reason, you might require sorting. So this is one of such sorting algorithm which helps us to sort elements or number of students. It can be any object, right? So it is a simple sort algorithm that revolves around the comparison. So now this is different from if you talk about bubble sort, insertion sort, and selection sort. this sorting algorithm is predominantly based on comparison, right? The comparisons are done more as compared to swapping. In each iteration, one element gets placed, right? If you think about bubble, how it worked like a bubble, and at the end you had your element fixed at its original position, which was at the end when we are trying to sort our array in the ascending order. Now, in the same fashion, right, in this sorting algorithm, one element that can be either the largest element or the smallest element. So we are going to put in the case wherein we will be dealing with the smallest element. In each iteration, the smallest element get its placed fixed in the original array. That means when we sort the array wherein this element belongs, that is the least element that is on the first index, right? So this element will have its position after one iteration. We will be choosing a minimum index in this sorting algorithm. We have one minimum index, and that can be named as minimum, right? Since we are dealing with the smallest element. So now that minimum element in the array is placed at the beginning, right? Beginning of the array. And later on, we will compare it with all the elements and find out the minimum and then swap it with the first index. Okay. Similarly, we are going to do for all the rest of the elements. Okay. Now, this selection sort is basically selecting an element, that is the minimum element, in each iteration and placing it at the appropriate position. So that is the basic logic behind what selection sort. Now let's talk about selection sort algorithm. Now in this algorithm, our main objective is to find the minimum index, right? So let's suppose if we have one array. Now, in this array, there is one minimum index. Let's suppose that it is at the first index, right? Since we are keeping in mind, right? I told you at when we talked about what is selection sort, at that time I told you that we can have two cases. Either you can pick up the largest element and fix its position at the end, or you can pick the minimum element, that is the smallest element. Okay, so in this case we will be dealing it with the smallest element, right? Now this is our minimum index, right? This is the 0th index. Now this outer loop will work from 0 to n minus 1. Now why n minus 1? Okay, I will tell you why. Because then what we will do, the next step is that we will have this minimum index, right? And it is pointing to 0 in this case. And our iterator, that is I, will start from this position. Then in the nested for loop, that is, again, this is condition where we have one for loop and inside that we have another for loop. That is what you mean by nested for loop. Now, since it is a comparison algorithm, what we are going to do inside this sorted part, or inside this unsorted part that is there, what you can say, the rest of the elements. Okay, so we have this j iterator which is pointing to I plus 1. That means we will not compare. It doesn't make sense, right? If I and j are at the same position and we are comparing them, it doesn't make sense, right? So we have this j placed at this iterator at this index, right? 1. This j iterator is at index 1. Now what we will be doing, we'll be comparing it because it's a comparison algorithm and number of swaps are less. That means if there are n elements, there will be n or n minus 1 swaps. Okay, so the swapping is reduced as compared to bubble sort. Okay, so now what happens, we will be comparing them. Okay, and we will be trying to find the minimum index. Let's suppose this is 3 and this is 1. So since 3 is greater than 1, that means our minimum index will be updated. So our new minimum index is what? At index is the 1, right? This is the minimum index. Okay, done. Now once this comparison is done, right? So again we will check if 4 is less than 1, no. If 5 is less than 1, no. If 6 is less than 1, no. If 0 is less than 1, yes, 0 is less than 1. That means we are again comparing it, right? And we are not swapping them. We will wait once this entire iteration is done. So I will update my minimum index to what? 5, because that is the minimum index. Then we have, let's suppose we have 8. Okay, done. So now once this entire for loop is exhausted, right? Now what we will do, we will swap this minimum indexed element with the this with the minimum index that was earlier there, that is the zeroth index. Okay, now we'll swap it with the zeroth index. Okay, so now what happened, this we will get here 0 and we will get here 3, so only one swapping is done. So now after first iteration, all the elements will be at its own position, because since we didn't swap any elements, we swapped only a single element, that is these two indexes, that is 5th and 0. Okay, so now what we will have 0 1 4 5 6 and 3, and at the end we have 8. Okay, done. And then we will iterate through again. So now our iterator will be here and our j will be here, and this time around minimum index will be, right, earlier it was 0. Now since we will not take care of this, or we will not think about this index now, because this is already at its original position, the element is at its appropriate position. That means when we sort the array, 0 will be at 0th index, so we will not think about it, and it doesn't matter to us now because it is at its original position. So minimum index will be now 1. Okay, so now let's try to see an example wherein we get the better understanding of this algorithm. So if you observe carefully, this is our input array, right? So we have 23, 10, 16, 11, and 20. Now what happens, we'll make this our first step, and this is our iteration number 1. Okay, so now what happens in this, we have our minimum index that is at c. This is our I and this is our j. Now we'll compare, right? Is 10 greater than 23? No, it is not. So still we have minimum index as 0. Is 10 greater than 60? No. Is 10 greater than 11? No. Okay, now this is the first step. Okay, just a minute, guys. So let me erase this. So our I will be here and j will be here, and minimum index is at 0. Okay, because that is the first index. Okay, so since we are taking into consideration the smallest element, so now we'll compare. Is 23 greater than 10? Yes. What we will do, we'll update our minimum. That means this is now index 1. Now what we will do, we'll have our index updated as 1, and then what we will do, we'll compare 10 with 16, 10 with 11, and 10 with 20. Since this is our minimum index after first iteration, now what we will do, we'll swap it with the first index, that is this, and this element will be swapped. So that is why we have 10 here and 23. Rest of the elements are same. Done. So this is our first step, and our I was at 0. Now our I is at 1, so this is our minimum index, right? This is our minimum index in this case. Now 11, in this case, what is our minimum index? That is 21, right? So min is here, and 23. Now 23 will be compared. It is greater than 16, so this will be our min. Again 11 will be compared, so this is our min. Now 11 will be compared with 20, so this is not our minimum element. Now this is our minimum element, and it will be swapped with 23. So 23 and 11 will be swapped. So that is what you see here. So 10, 11, and 23 is swapped with this. So 23 here and 11 here, right? So 23 will be here, and rest of the elements will be as it is. So this is after iteration number 2. Now what happens in iteration number 3? So we have 0, 11 at its original position, right? Now let's swap back and let's erase this. So now what happens? So this is our minimum index, right? And now 16 will be compared with 23, nothing will happen. 23 will become 16 will be compared with 20, nothing will happen. So this is our minimum index, and this is the ith index wherein we will be swapping it. So 16 will be swapped with itself, and rest of the elements will be as it is. So you will see 16 and then 23 as it is and 20 as it is, considering this iteration number 1. Okay, so after iteration number 3, this is our input array. So similarly, after third iteration, this thing will happen. As 23 is greater than 20, so these elements will be swapped, and in the fourth iteration is required as last element is already sorted. Okay, so no fourth iteration is required as the last element that is there, which is already sorted. Okay, so this is the whole demonstration of this selection sort algorithm.
Now let's see the implementation of selection sort algorithm. I'll go directly to the Eclipse IDE and we'll write the code there and see how the implementation goes. So here I've already created a sort class. Okay, in this there is public static void main method also. Now I'll create a method or a function, you can say, for selection sort, and that method will be called from the main method. Now let's go ahead and write down the code. So public static. I use static keyword every time over here because we don't have to create an object for the class to call this method. Directly we can call the method without using any object for it from the main method. So that's why static here. You can avoid that. In that case, you have to create an object of this class sort and then call the method. Void, because I'm not going to return anything from this function. We'll print the sorted array in the function itself. So let it be void, or you can have return type int, then in array type of a return type. So in that case, you have to return the array. So okay, selection sort. Okay, the input will be here, nothing but an array which had to be sorted. Okay, so selection sort works in a way that it selects the smallest element among the complete elements of an array and places it at the required or the specified location, specified index. Now what is a specified index? Like suppose the array is given, okay, there are 6 elements in an array, so it will start from the first location. For the first location, it will search the entire array and find out the smallest one. Whichever is the smallest one, that will be placed over there. Then it will go to the next index and it will search for the smallest elements again, but in the remaining elements after first, like starting from second to the last index, whichever is the smallest element, that will be selected and will be placed at the first index. Then it will go to the second index. Now in second index also, it will place that smallest element which are there among the remaining element, that is starting from 3 to last. Okay, so that's how the selection sort works, and that exactly, this picture you can imagine and you can write it down, the code for that. So it will start with the for loop. So for int I equals to 0, okay, and I will be less than a1 dot length, okay, and I should be incremented every time. Now inside this, we'll have a temporary variable here also to store the current index being referred. Okay, so let have any uh, intermediate or let it be inter itself. Okay, I think just the name is clear, right? Intermediate variable is your inter I. Now we'll go to the for loop again because we have to find the smallest element among the remaining elements, right? So for loop int of j, which will start from I plus 1 remaining elements, right? And it will go till the end, that is a1 dot length, and we have to increment that also. Okay, now in this we have to check for this, find out the smallest element. So for that we have to do the comparison, and for comparison we know what is the loop use, that is if loop. So if a1 of j is less than a1 of intermediate variable, or let's keep a smaller name for this, that will make our things easy. So let be k. Okay, it will be confusing, I think. No. Um, uh, okay, k1, fine, let it be. So k1 is right now the intermediate variable which we are using, or it is keeping track of which index value right now is being referred. Okay. So if this is less than this, then in that case, what has to be done is that this k1 value will change. It will be now j, right? So that next comparison can start. So ultimately, what will end up with is that once this for loop will end, here, right? So once this for loop ends, we'll be having the smallest element at our k1 index. Okay, so k1 index will be pointing to the smallest number or smallest element in the complete array. So once we found the smallest element, we have to swap it from the ith location. Ith location nothing but the current location which is being referred, right? So once this for loop ends, we'll write the swapping code. So I'm using swap variable here. There is a third variable. Using third variable, I'm doing the swapping. You can do it using any other Boolean expression. I mean, arithmetic operators also. Anything is fine, guys. It's not mandatory here, anything. Both will work fine. Now a1 is given to a variable swap. So a1 will be populated with a1 dot k1, as k1 is having the current smallest value. And now k1 is empty. So k1 will be now populated with the swap variable which had a1 I. Okay, so swapping is done. Once the swapping is done, this code will end over here and this function ends here. So before the function ends, let's write the for loop to print this array, sorted array. So I less than a1 dot length I plus plus. Okay, so in this we have to just print the array. So a1 I. I'll just a little bit decorate this so that it looks neat. Meaning it will print the output in the same line, nothing else apart from that. Okay, now let's call this, selection sort method from the main method. So for that, I need an array first, a1, which is equal to new int, and then we'll define the elements here. Let's put it in a staggered way so that once it sorts, we get an idea. Okay. Let's call now the selection sort here. Selection sort for the array a1. Right? So yeah, that's it. Let's see if it works fine. So yeah, you can see here 1, 2, 3, 4, 7, 8, and 9. This is our output. So the logic has worked completely fine. And this is the logic, that is, this for loop is going to find out the smallest element among the remaining elements. Once we find it out, it is being pointed by a variable k1. So we'll swap that k1 with the current ith element which is being referred. And once that's the whole process, and we have to perform this whole process from beginning of the array to the end of the array. So for loop for I will go from 0 to end of the array, that is a1 dot length. Okay, and then lastly here I have just printed the sorted array, and from the main method nothing but we called the function directly from here. You can see here I have not used any object of a class because it is a static method and I can call directly without using the object of the class. Okay, so that's all about the Java implementation of selection sort algorithm.
Now let's see the time complexity of selection sort. Now, if you talk about worst case, that is if the array is unsorted or it is we are trying to sort an array which is reversed in nature. Okay, so let's suppose we are trying to sort the array in ascending order and we get the array in ascending order or descending order. Okay, so that is 10, 9, 8, 7, and 6. So this is the worst case, right? And now what happens in this case? Every index, the minimum index will be updated for every element. Okay, so 10 will be compared with the 9, so minimum index will change from 0 to 1, then 0 2 3 and so on. Okay, to find the minimum index, that is this element. So this is the worst case. Now what happens, we have the outer loop that is working from 0 to n minus 1 and the inner loop that is working from 0 from j plus 1 to the size. So in any case, whether we have this unsorted array that is here, we will still be traversing big O of n square times because we have these two for nested for loops which are working up to the size of the array. Done. And same thing happens in the average case as well, whether we have some elements in the sorted format. Let's suppose we have half of the array in this way and then the rest of the elements are unsorted. Still we will not update our minimum index, but rest of the elements will change for the not for these three, but for the rest our minimum index will keep on updating. Okay, so it doesn't matter. So average case type, if you talk about average time complexity, it will also be n square. But what happens if our array is still sorted, right? Or if our array, that is the array given, is already in sorted format, will there be, if we modify our bubble sort, we can get this down to big O of n. But this is not the case in selection sort. Still we will be comparing in the outer loop from 0 to n minus 1 or size minus 1, and in the loop will be again going from j plus 1 to less than size, without, even if we are not going in this for in this if condition, that is the comparison condition will not be executed and the minimum index will be as it is, still we are going through this for loop. Okay, whether we are not, even if we are not executing this if block, okay, it doesn't matter, still we are going, the n square time complexity will be there even in the best case as well. Okay, So this is all about the time complexity of selection sort. Now let's talk about the space complexity of selection sort. Since we are not using any auxiliary memory, so auxiliary memory can be in the form of arrays, linked list, stack, queues, or even strings. Since we are not using any of these extra memories in order to sort our array, so the reason for that is because we are doing this within the array that is provided to us, right? So the space complexity is constant. That means big of 1 as we are not using any auxiliary memory. Now let's talk about selection sort analysis. If you observe carefully in this array, let's take an example first: 10, 9, 8, 7, 6. Okay, let me put a 6 here. So this is our array, right? And in this array, what we are trying to do, we are trying to arrange it in an ascending order. So now, if you remember the algorithm, the outer loop worked from 0 to n minus 1, and then inner loop worked from, that means 0 plus 1. That is, let's suppose if this is an I iterator, if we use in outer loop, we used I, and then in inner loop, we use j, then j work from I plus 1 to size, that is n, right? Now and then inside this we used to compare. So now in worst case, every element was compared, right? J was compared with I plus 1, right? Or I was compared with j plus 1. So it was compared with this and this, and we were selecting the minimum element in the array, the minimum index rather. We were selecting the minimum index in the entire array. So this was working for n times, and this worked from big O of n times, right? And in worst case, the number of comparisons required will be big O of n square, because we are trying to find the minimum index in the entire array, right? And once we have that minimum index, and later on we'll swap them, right? In worst case, it will go from 0 to n, that means big O of n, and the inner loop will also go from big O of n, that means 0 to n. So in worst case, since these are nested for loops, so the worst case will be big O of n square. And for comparing them, well, I'll always compare all the elements, and it will be again, it will boil down to what? Big O of n square when we talk about number of comparisons. And what happens when we are trying to swap them? Since we have this minimum index that is there, only one swap was required, that was outside this inner for loop, right? So we have this inner for loop, and here we were doing the swapping. In worst case, the number of swaps that are required is big O of n. Okay, in worst case, that means we were swapping only single time, and it will be the case, right, that in worst case that all the elements right at the end will be swapped. So we will have at the end what? 5, 6, 7, 8, and 9, right? And we will swap them only once in the entire array, that is once for every element. So in worst case, it will be big of n square. Now, what about stability? If you talk about stable algorithm, it means that if you have this array, let's take an example, it is 10, 8, 9, and 10 again, and then 6. If you talk about this, the stability will boil down to two things: the relative position of these two elements, 10 and 10 dash. Now, if we sort this, it can be 6, it will be rather, it will be 6, 8, 9, 10, and 10 dash, right? So it will be 10 and 10, but just to separate these two tens, we are taking as an example, we are taking this, assuming this 10 to be 10 and this 10 to be 10 dash. And it can also be that it will be 8, 9, and then 10 and 10 dash and 10. So both of these are sorted, right? But if you talk about stability, this is a stable algorithm. Why? Because the relative position of this 10 and this 10 is intact, and this is an unstable algorithm. Now, when we compare or when we do the swapping in selection sort, it is not guaranteed that it will be stable, right? And the elements can be unstable. That means the resultant array will be in this format, that 10 dash maybe at first, and then we have 10. So it is not guaranteed that it will be always stable, but yes, we can make it stable by modifying our selection sort. But if you talk about traditional selection sort, it is an unstable algorithm, right? Now what about the in place? That means, are we using any extra memory or extra space? No, we are not using any extra space, right? Extra space can be a linked list, it can be an array, it can be a stack, it can be a queue, right? We are not using any of these extra spaces. So that is for the same reason this selection sort algorithm is an in place algorithm, right? Because we are swapping our elements and we are comparing them within the given array, right? We are not using any extra memory, right? So for that reason, this is an in place algorithm. Let's try to reiterate what we learned so far. So if we talk about number of comparisons, in the worst case, it can go to big O of n square. In terms of number of swaps, it is big O of n. It is an unstable algorithm and it is an in place algorithm. Now, before we understand what is quicksort, let's try to understand what is sorting and why do we require sorting. So sorting is a mechanism wherein we will be sorting or arranging our data either in ascending order or in descending order, right? So let's suppose you have a students, you have 10 students, and all those students have roll numbers allocated from 1 to 100, and you want to know which roll numbers are present and which are absent and which have left the college or school, right? So in that scenario you can easily implement sorting, right? And you can understand when you have that sorting arrangement in place, you can easily detect which elements or which students are absent or not, right? So herein you can use sorting. So in this tutorial we are going to understand quicksort algorithm. It is one of the most widely used algorithm. It follows a paradigm of divide and conquer. What do you mean by divide and conquer? Basically, we will be dividing our array in such a way that every time we will be dividing, let's suppose this is an array and now we will be dividing into two, then further we'll divide it into two, then further we will divide it into two, and so on, right? So we'll see in the algorithm part how we can implement this divide and conquer paradigm. And in this tutorial we will be implementing this quick sort using recursion. We'll see how we will recursively call those functions based on some pivot element. Now in this recursive call we'll choose a pivot element. Let's suppose you have this array and we were choosing this element as pivot. Obviously you can choose any element as pivot, right? So it can be first element, it can be last element, it can be any random element. But once we have chosen that pivot, now what we will do in each iteration, right? In quicksort, what happens in each iteration, this pivot will have its original position. That means this will be the position in the original array as well. Let's suppose this is our pivot. Now this pivot will have its original position after one iteration. After that iteration is over, and all the elements that are less than this pivot are on the left hand side, and all the elements that are greater than will be on the right hand side. Now then we will be choosing another pivot. Now what are those pivots? We'll see in the algorithm more extensively what are how we can choose that pivot. Now let's suppose we chose this pivot and this pivot is here, and after the second iteration what happens, this pivot, this will be our next pivot and this will be our next pivot. Now we will be having two pivots. So this is how we induce that we are implementing divide and conquer approach. Okay, with each step our problem gets reduced to two, which leads to quick sort, right? Or quick sorting algorithm. Okay, so now we'll be dealing with this subarray and we'll be dealing with this subarray, and now we'll be implementing the same procedure on this subarray. That means this is the pivot and this is the pivot, right? Now let's try to understand the algorithm of quicksort. So now we have this first the method that is there, that is known as quicksort, in which we will be calling this quicksort recursively again and again. But first time around, what happens, we will check, okay, now we have this array, always we will check beginning should be less than end, because that way we can keep the track of things, that okay, this is a part that is already sorted and this is the part that is unsorted, right? And now we will be checking, and after checking that, we will be calling this method. We will see what this method is, we will see the algorithm, and we will see how this partition happens, and we will get the index of the, let's suppose we pick this element as pivot, and after partition, what happens, this pivot has its original position at index 3, right? And that will be returned, and that will be contained in this pivot index, right? And now what happens, now we know that this is its original position in the original array wherein we will get the sorted array. This will be its original position, that means this element, let's suppose is 8 will be at index 3, and this will have its original position after each iteration. Now first time around, what happens, this partition is called. Next time around, what happens, this quick sort algorithm is called again recursively first time on the left hand side. That means this portion, now in this portion, this will be your pivot. Okay, you see, beginning is we are sending the arguments as beginning and pivot index -1. That means we are not including this element because this has been already sorted. We are not including this element, and we are calling this function on this subarray again, and this time around this will be our pivot, and same thing happens. Similarly, when we are done on the left with the left hand side, now we'll be moving to the right hand side. That is, we will be implementing it on pivot index +1. That means this element from this element that is there to the end of the array, and this time around this will be our pivot. Okay, now with that being said, this is what happens when we are implementing quicksort. But now what about this partition method? Let's see how that happens. So in partition, what happens, we will be setting up the pivot element, that is setting up the element which is our pivot. Obviously you can choose any element, but in this tutorial what I am going to use, and what you should try first, that we should try to pick pivot as the last element. Obviously you can pick any element, and its time complexity and depends on which pivot you will be choosing. We'll see that in the time complexity part. Okay, now we have set this pivot as the last element, and now what we are doing, we are saying that okay, the pivot index, this step refers to what, this is the index from, let's suppose this is the pivot index, and what happens, this will be our pivot. Okay, what happens, this pivot index maintains that order. Okay, from this index, everything on the left hand side is less than the pivot, and everything on the right hand side is greater than the pivot. So we'll see when we will see an example, and therein I will show you how this pivot index is very important. Okay, now what we will do, obviously at start it is at this position. That means we have no such scenario wherein we have some elements that are less than pivot and we have some elements that are greater than pivot. Okay, so now let's suppose this is our array and this is our pivot, right? And this is our p index, that is the index, pivot index, and it is -1 right now. Okay, now these two steps are done. Now what happens in the third step, now we will iterate from beginning, that is this point, and we will check if any element is less than pivot. If that is the case, then what we will do, we will increment this and swap those elements, that is the area, the first element and the index that is present at, that means now if you see this step, now we have incremented it first, right? Now let's suppose if any element that is less than pivot, we first increment the pivot index. That means that pivot index will be here, and we will be swapping it with ARR of I, and ARR of I is also at this location, so this element will be swapped with itself. Now you might be thinking, okay, so why we are doing this, right? Why we are swapping this with its own position? You won't get the intuition in this step, but in the next step you will definitely get the intuition. Now let's suppose this is the thing that happens in the for loop. Now let's try to reiterate this. Now if an element is not less than pivot, let's suppose there was, here we had 5 and here we had 3, so it was less than and we swapped it with itself. Now let's suppose we have this element 6 and it is not less than pivot, right? And what happens over here, so we will not execute this if block, right? And then we'll have this ARR of I. Now I will be here, now I will be incremented, and this time around we have 2. and P index is still here, right? Now this time around it is less than 2, right? And now what we will do, we'll increment first the P index, it will be pointing here, and then what we will do, we'll swap these two elements, right? These two elements will be swapped. So now you have 2 here and you have 6 over here, right? So you see, this is the reason why we have this pivot index in place and why we are swapping them. So in the first step, it was that it happened due to the fact that the element was less than pivot, and if the element wouldn't have been less than the pivot, then we have incremented the I pointer and P index would have remained on -1. Now finally what happens, now once the entire iteration is complete, and let's suppose we have 8 over here and we have then 10. Now once the iteration is completed, now what we will do, we'll swap these two elements. That means 5 and 6 will be swapped, and we have 5 here, we have 6 here, we have 8 here, we have 10 here, and we have 3 here, and we have 2 here. So you see, after one iteration, all the elements that are less than pivot will be on the left hand side, and all the elements that are greater than will be on the right hand side. And finally we will return pivot index, that is P index plus 1. That means we will be returning this index, so that this element is not considered or will not participate in any further iterations or any further recursive calls, because you see, if you observe carefully, that we were sending pivot index -1, that is without 5, all the elements on the left hand side, and +1, that means without this index, all the elements on the right hand side. Okay, this is how partition works. Now you might be confused a little bit. Now let's try to demonstrate this with the help of example. So you see, we have an example over here, right? We have 5, 10, 9, 6 and 7. These are the elements in the array, and we have this pivot here, the last element. We have chosen last element to be the pivot, and after that what we are doing, we have this end pointer and we have this beginning pointer. Also we have that pivot index, which will be somewhere around here, right? That pivot index, which will be -1. Now this 7 will be checked. Okay, is 5 less than 7? Yes, 5 is less than 7. So it will be swapped with itself, and pivot index will be incremented first and then swapped with itself. Now pivot index will be here. Next time around, our I pointer will be here. First it will be here, then what, it will be incremented. Now we will again check. Okay, is 7 less than 10? No, it is not. So our I will be incremented. I will be now here at this position, right? Now again it will be checked. No. Again it will be checked. Yes. So now what happens? 7 and 6. This 6 will be replaced with what? 10. So you have this 6 in here. Obviously pivot index will be incremented first, and then we have the 6 over here, and it will be swapped with 10. So 10 will be here, right? Done. And finally, when we are at the end, once the entire iteration, this is the step 1, once the entire iteration is completed, we have 5, 6, and then 7 will be the last swapping that we did, the last swap that we did. If you observe here carefully, this swap that we are doing, this is the one that is responsible for swapping this 7 with the pivot index, that is pivot index plus 1, that is this location, and we have this 7 over here, and it will be replaced with 9. So that is why we have 9 over here, and 10 was here, and this is the array after first iteration. Now you might be thinking, okay, now this element is fixed. Now we will not never talk about this element, because this has its original position in the sorted array as well. Now what we will be dealing with, we'll be dealing with this left part and dealing with this right part. So now what happens in this part, right? And what happens in this part? You see, now we have this is our beginning, and this is our pivot, because this is the last element that we will be picking, and this is our end. Similarly, this is our beginning, this will be our pivot, the last element in this subarray, and the end will be here. Now we'll be again doing the same step, and this time around we'll be checking, okay, pivot is less than, no, nothing will happen, and then we will be swapping this thing with itself, right? And now once this entire subarray is completed, we'll not go any further, because this time around beginning is not less than end. Both elements are at 0 and 0 is not less than 0. And now if you observe carefully, this is the condition that we were setting at the start of the function, that is the quicksort function. And we were checking if beginning is less than end, right? So this is the importance of that. Similarly, the same thing will happen over from this side, and again beginning will not be less than end part, and we will not go any further. So after two iterations, our entire array is sorted, right? So this is the step one. After step two, our entire array is sorted.
Now let's talk about the implementation of quicksort algorithm. So I'll directly go to the IDE, that is Eclipse IDE, and we'll start typing the code there. So let's go to the IDE. So here you can see I have created a class file already, that is sort class. And then there is a public static void main method here. And now here we are going to write the logic of or the code for quicksort. Okay. Uh, so as we know that, in quicksort, it's a recursive call, right? Over the same quicksort function is recursively called for each time, because it follows a divide and conquer approach where the complete given data is divided into two halves each time, and the same algorithm of quicksort is implemented on each half of the data set. So here the data is into a one-dimensional array. So we will divide the one-dimensional array into two halves. Okay. Uh, and it will be divided in such a way that the middle element, all the elements in an array which are smaller than the middle element should be before the middle element, and all the elements which are greater in an array then the middle element should be after the middle element. Now that middle element or mid element is nothing but your pivot element. So this is a term which we refer in quicksort, that is your pivot. So pivot element is nothing but that particular element when it is placed in the center of an array, all the elements on the left side should be smaller than the pivot, and all the elements which are greater than the pivot should be on the right side of the pivot in the one-dimensional array. Now the pivot element can be your either the first element in the array, that is at index 0, whatever element is there, that can be the pivot, or the element which is at the last, which is at the end of the array, can be your pivot element. Or you can randomly select any one number to be a pivot element also. Okay, there is no fixed rule for this. The only condition is that once you run over the algorithm or the code, after the first iteration, what it should be that when your pivot element is placed in center, all the elements on the left side. Now in center meaning it can be at the third index, fourth index, sixth index also. But all the elements before the pivot should be smaller in value, and all the elements on the right side of the pivot element should be greater in value. Okay, that's the whole logic and a point. Okay, then recursively we have to keep calling the quicksort function on the left side part of the array, and then again on the right side of the pivot element of the array. So let's write down the code for this logic. So first I'm going to write here, I'll be making a static function, and the reason behind making static function is that we don't have to create object for the given class that is sort over here, and directly without the object we can call the function or the method. That's the reason I make it static. If you don't make it static, you have to make an object of the class and then call using that object. So anything is fine there. So let's write a you know function by the name of partition itself, because we are partitioning it into two parts, or maybe dividing into two parts. You can write divide or whatever name you want according to your convenient. So partition, and then what will be the parameters to this function? The array which you have to partition into two parts, and then the beginning index and the last index, right? So it will be int first and int last, right? We should write this outside the main method. Obviously you can't have a method inside a method, right? So yeah, so here now we have to write a code for partitioning. So what the logic is that you have to compare each element with a pivot element, and if it is greater, then you should swap the values. If it is less than the pivot element, then you should swap the values. Otherwise, if it is greater, let it be like that only. Okay. At the end, the pivot element or the pivot will be swapped with that element which is at the neck of, you can say, the or which is at the place where from where all the elements on the left are smaller and all the elements on the right are greater. Okay, so that's the logic which we are going to write down over here. So I'm going to first initialize the pivot element. As I said, you can select any one as a pivot element. So here I'm selecting the last element to be that. You can select the first one. You can do some random selection as well. Then here, just to store the initial index, I'm going to store it into I so that while swapping it helps. Now for the all the elements we have to perform the operation, right? So we'll use for loop to run over or access all the elements of a given array. So int j equals to 0 and j should be less than uh, or better than 0, you can write first. Okay, and j should be less than last, because first will change, like initially the first will be 0 and last will be the last element of that. But when it will iteratively call this function, the first can be mid plus 1 also, right? So it is first, not 0 here. And then j plus plus. Okay, now in this, what condition check you have to do is that if a1 of j is less than or equal to pivot element, then the swapping is needed, right? If it's greater, we can leave it as it is. So in this case, we have to swap it. So swapping, I'm doing it using third variable. Okay. You can use any other logic to swap as well. That's not a problem. Okay. A of I is when to swap. Now, so A of J. Okay. So A of I, we should put first A1 of J, and then A1 of J is empty. So in A of J, we should put swap, right? Done. So this is the small simple code of a quick shot. I mean partitioning basically. Now once this all the comparisons are done and this swapping is done, at the end the pivot element is our last element, right? So that should be brought to its appropriate position. So that swapping will be done once this for loop completes. So after this we have to do one more swapping with the pivot element this time. Okay, with I plus 1, because I will be pointing to the current location, so it should be plus 1, and a1 of I plus 1 will be equal to your pivot, or you can say, like right now I've selected last element to be pivot element, so let it be a1 of last, but you can write pivot also here. And then a1 of last will be equal to swap, right? So the swapping is done. Then this will be the closing of your function. Now, so this is your partition function which we wrote, partitioning. Now, as I said, we have to recursively keep on calling on the once on each part of an array. Like we divided the array into two parts. Now each part, the same logic will be called, right? So let's write the code for that part now. So I'm going to create one more function here by the name of quickshot. Okay. We'll pass in this also an array and first and last. Now in this, what will happen is that, okay, this should return. Okay, let this return, guys. So this will be int actually, because that index, mid index from where partition has to be done, that has to be returned, right? Otherwise, it won't work fine. Here we should return. What should be returned? I plus 1. Because I will be pointing to current element, so I plus 1 will be returned. Okay. Now coming here back. So whatever is returned from there should be the middle element, right? So partition will be called here with same a1, first and last, this whatever is returned from your A1 first and last, I mean the partition function, that will be your mid element. That index will be stored in this variable mid. Okay. Now after this we got the mid element. What we have to do, divide into two parts and call recursively the quick sort. So let's do that. Quick sort will be called for A1, and here first will be first itself and last will be mid minus 1, isn't it? Because from mid we are partitioning it now. And again this will be called in the other half of the array. So quick sort A1, this will be mid plus 1 because the right side of the array we are going to take, and this will be last. Right? So I think this is complete here. Okay, now let's go to the main method and write a code to call these functions. So I'll define an array again here. A1 is equal to new int. Let's write some values which are not in sorted order. Okay. And then we should call the quick sort function here on A1, and initial index will be 0, starting index, and last index will be your A1 dot length minus 1, guys, because A1 dot length will give you the total number, but indexing starts from 0, so definitely the last element index will be 1 less than the length of the array. So this will be like this. Now let's write also a code to print, because how will we know what's the output finally? I is equal to 0, I less than A1 dot length, and then I plus plus, and then we should write the code for system.out.println through print, and this will print what? A1 I. Again, let's do some formatting here and remove ln from here. Closing of for loop, closing of the function, closing of the class. Okay, now I think this is complete. Let's run the code and see. Okay, it says error index out of bound. Let's fix that. First minus 1 and j is equal to first and j less than last. Okay, j plus plus. Okay, so what went wrong? I will scan it through once again. So we selected a pivot element over here and then initialized I so that it stores the current element. Then from first to last, we have to check that if the given element is less than the pivot element, then we should swap. Okay, we should increment I as well. Otherwise, how will it go to the next element? Always it will keep pointing to the first minus 1 itself. So this is fine. This is fine. Okay, let's run the code and check. Again, there is an error. Okay, we'll see what went wrong. Let's quick show. Okay, there is a condition check here, guys, which has to be there. Okay, all these process should be repeated till when? Like when will the quickshot keep on recursively calling itself? There should be some stopping criteria, right? And that stopping criteria is that till when there are no first and last is not pointing to the same. So till when first is less than the last element. And this will end up over here. Okay, now let's see. Yeah, so that was the problem here. We could find out the final solution, that is the element is in the sorted order 1, 2, 3, 5, 6 and 9. So I hope you understood this. So it's very easy, guys. Quick short, you have to write a function which calls recursively the partition method, which keeps on partitioning, and we keep on calling quick short again and again on the each half of the given array once it is partitioned into two parts. And this partitioning has a logic where for all the elements, what you have to do is you have to compare that with a pivot element. If it is greater, then nothing has to be done, but if it is less than equal to, then it should increment I as well, and then swap those two numbers at the end when all the elements are looked after or is scanned. Then after that you have to swap the I plus 1th element, because I will be pointing to the current element. So I plus 1th element will be swapped with the pivot element, and hence your final sorted array into two parts you will get. That is two parts meaning from pivot element less lesser elements, that is the value elements who are having lesser value than the pivot element, will be on the left side, and then other ones that is greater than the pivot will be on the right side. So the swapping, once after the no the swapping is complete, we will obtain that, the final thing, and then it should return the index of the middle element, okay, which is actually pointing to your pivot element right now, correct? And that's it. From the main method, we just have to call the given function on a given array. So we'll initialize an array here and then call the quicksort method on it. This for loop is just for printing the final sorted array. So that is all about the implementation of quicksort.
Now let's try to understand the time complexity of quicksort algorithm. In quicksort algorithm, we have now seen that partitioning of elements takes place, and we are partitioning all the elements. That means all the n elements. If there are 8 elements, all the 8 elements will be, we iterate through all the 8 elements, right? So partitioning them takes n time, that is order of n time, and then quicksort problem divides it into the factor by the factor of 2, right? Every time we are dividing it by 2. So the entire process or the time complexity of quicksort in best case and in average case takes order of n time, that is big O of log n. And same thing happens when we are talking about the average case as well. But why this is n square in worst case, that is the question, right? So let me clear it out. So the question is that why this thing happens if you are picking either the smallest element in the array or the largest element in the array as pivot. In that case, you are traversing through all the elements again. That means this n is already there for partitioning them. That means you will be iterating through the array. But the extra n, and that means inside that n, you're again traversing through all the elements and swapping them, because you have picked your pivot. In worst case, you can either pick it as smallest or the largest element in the array. In both these cases, you will be swapping all those elements with itself. That this element will be swapped, right? This is the largest element, right? This is, let's suppose this is 8, so nothing will happen, right? So this is smallest, then it will be swapped with itself. This is smallest, this will be swapped with itself, this will be swapped with itself, this will be swapped with itself. So all the elements will be swapped, and finally this element will have its original position at the end, right? So this thing will happen if you are picking your pivot as the smallest element or as the largest element in the array, okay? So in these two cases, this is not the case. You are picking your pivots as random. You are picking your pivots randomly, okay? In nutshell, when you are picking your element, that is your pivot element, as smallest or the largest element in the array, in that case, that will be your worst case time complexity, and it will be big O of n square. Now let's talk about the space complexity of quicksort. Now you might be thinking, okay, we are not using any extra space, right? We are not using any auxiliary memory like in the form of array, stack, queue, linked list, or anything, right? But for calling this function, that is the quicksort function, we are using recursion, right? We are calling this quicksort again and again, right? 2 quicksort calls are there. For maintaining the call stack, we require order of n space, that is the time complexity will be big O of n when we are using this approach. And in the worst case, this will be the scenario that all the elements will be on the call stack, okay? So in worst case, the space complexity will be big O of n. But if we modify this approach of storing the elements and calling the call stack and maintaining the call stack, we can reduce it to big O of log n. Now let's try to analyze quicksort algorithm. Let's first try to understand the stability. So let's suppose if you have this array 1, 3, 1 dash and 4. Now an algorithm is said to be stable if both these 1 and this one, both these in the sorted array will maintain their relative positions. Now you have this sorted array, right? And both this one and this one are maintaining their relative positions which were earlier in the unsorted array, right? So if that thing is maintained, right, if that thing is maintained, the algorithm is stable, else it is not stable. Obviously you can have another way with which this is also sorted, but this is not a stable, this is unstable algorithm. And if you are sorting in such a manner and you have these things placed, this algorithm is unstable. So if you talk about quicksort algorithm is an unstable algorithm. Although we can do some modifications and we can stabilize it, or we can make this algorithm as stable. But as of now, if you talk about quicksort algorithm, it is an unstable algorithm. What about in place and out place? Since we are not using any auxiliary memory, right? We are not using any extra space explicitly, right? In the form of array or linked list or stack, right? Or even queue. We're not using any extra memory, right? So this algorithm, quicksort algorithm, although we are maintaining a call stack wherein we are maintaining a call stack and we have a space complexity of big O of n, but since we are not explicitly mentioning these auxiliary memories, this algorithm is an in-place algorithm, and these are the two analyses that can be done on quicksort. So in nutshell, if you talk about quicksort, right, it is unstable algorithm and it is in place algorithm.
Now let's see what is the divide and conquer approach to programming. So divide and conquer approach is, as the name itself specifies or clears its meaning to a great extent. That is, we divide the complete given problem into subproblems and then solve that each individual subproblems to find out the final solution of the complete problem. Okay, so it works on the principle of divide and conquer, which Britishers also used to rule over Indians. So that same approach, right? So we'll divide the things and then try to solve it and find out the solution of the smaller units which we obtain after division. And then once the solution of the smaller units is found, it is combined together to find out the solution of the overall problem. The benefit of this divide and conquer approach is that any big or complex problem can be reduced to a very simple one, and that can be solved in a very easy way. But you have to see here that only those problems can be divided into sub problems where the task is repetitive. For example, merge sort, quick sort, binary search, right? Like in a binary search, what happens? We divide the complete given array, complete given data into two halves. And if the value which we are searching for is in lower than the middle element, we go to the first half. If it is greater, then we go to the next higher half, right? And then in that first half also we do the same thing. We find the middle element, and if it is smaller, the element which you are searching is smaller than the middle element, we go to the first half. Otherwise, we go to the second half, right? So it is a recursive call to the same procedure, or the same task is implemented again and again, right? So divide and conquer can be applied to those problems only where you can divide the complete problem into sub problems, and your actual the solution or the remains the same, right? For example, in merge sort, you have to perform sorting, right? If you divide it into two parts, then also the two individual parts you have to do sorting. If you divide further also, then you have to do sorting. Once that smaller parts are sorted, you combine together and get the final sorted array or final sorted elements, right? So this has to be kept in mind here. Otherwise, divide and conquer is a approach to programming that helps to solve the complex and a bigger difficult problems in a much more easy and convenient way. We'll see the example of the merge sort and its implementation also in Java. So among these applications like merge sort, quicksort, and binary search, now we'll see what is merge sort and how its implementation is done in Java programming.
What is merge sort? If we talk about merge sort, let's try to understand first sorting. So sorting is a mechanism of giving order to your values, right? So let's suppose you have some values, random values, 10, 30, and then you have 5, 2, 1, and so on, right? You have these values, and now you want to maintain some order. So in order to visualize this data, let's suppose you want to see the ascending order of it or the descending order of it. That is what you mean by sorting. So let's suppose you have a class, and in that class you have several roll numbers, and some of the roll numbers are not present, and then you want to sort those roll numbers in terms of ascending or descending order. That is when you require sorting. So this is the basic intuition behind sorting, trying to give order to some kind of values or some kind of a data set, right? So in this particular tutorial, we are going to talk about merge sort. So merge sort is a classical sorting algorithm. In this sorting, every time your problem is divided into sub problems so that your problem set is reduced, and then you will be focusing on that sub problem. Similarly, every time when you're dividing your sub problems, you will keep on dividing it unless and until there is only one element left, right? If you compare it with simpler sorting algorithms like bubble is there, insertion is there, selection is there, quick is there, when you talk about its time complexity as compared to these algorithms, this is very much efficient. Now, it follows a paradigm of divide and conquer. What does this mean? This means that first you keep on dividing your sub problems, and then you will conquer those problems, and then you will combine those things. Okay. So herein we will see when you are trying to divide your sub problems, and then when you have your problem set and those problem sets are conquered, that means those problems are further, when you talk about in this example, those sub problems are sorted in this case, and then you have conquered them, and then you will combine them. That is your merge phase, wherein you will be combining your problem again, and then for forming again a single sub problem. So every time you will be dividing that sub problem, you will be conquering it and combining it. So this is how this divide and conquer paradigm works. So basically, when you're dealing with merge sort, you are focusing on two functions, that is your merge function and your merge sort function. So now let's talk about this divide. That means you're dividing your subproblems, which continues unless and until there is only one element left, because one element in itself is sorted, right? Now this is your divide phase. What about conquer? Basically, you are conquering those individual sets and then merging those two subproblems into a single problem. And finally, you will be doing it on each step, and finally you have your original array, which is sorted. Now let's talk about merge sort algorithm. So first let's talk about merge sort method. So in this method, what we are doing, we are dividing our array into further sub arrays. How we are going to do that? We are basically, if we have this array, right? And this array, let's suppose this contains 8 elements, right? This is our array. And let's suppose this is our left pointer and this is our right pointer. And now what we are doing, we are dividing it. So we need some kind of in iterator wherein we will store the sum of, and we try to calculate the mid value. How would you do it? In simple words, we calculate left plus right divided by 2. That's it, right? So we have this division, and then we will divide this part because we are calling this function again, right, on the left hand side. So this is going to call on this side. That is, we will be talking about now only 3 elements. So this is let's suppose, or let's take 4 elements on this side and 4 elements on this side. So our mid will be 3.5. So we'll be talking about elements from 0 to 3. So we will be talking about 4 elements, and then further these two steps are remain. Why? Because we are implementing this in recursive fashion. So now let's suppose this is our first function call, and you have these 3 steps. One, let's name it 1, 2, and 3. Okay. So in the first function call, 1, 2, and 3. So this is the first function call, and in this we'll calling again. This is the second function call, and we are calling again these two remaining, right? And we are calling again 1, 2, and 3. Right? So in this case, again, we are calling it on these 4 elements, and it will be divided into further 2 elements, 0 and 1, right? And in this case, again, this will be called on these 2 elements, right? Here we are talking about only 2 elements. So this is the third function call, and again, we will be dividing it. These 2 and 3 steps are still remaining. So in the fourth step, what we are dealing with, only single element, right? And in this case, we are talking about only this element, right? And further, we will not be able to divide it. And in that case, our left is not greater than, our left will be greater than or equal to right. And in this case, it will be equal to. So we will return. So now it will be returned, right? And then whatever was the left over, right? Now we talk about this single element, the other element that was left behind. We'll talk about that. So again, that will be divided into 1, right? And again, this second option, I'll just erase it because it looks a little bit messy. So now what happens? let me just put it again in red. So here we call this fourth time, and this time it returned, right? So in this case, now we will be on the second step. Now again, it will be called on that single element, and again, left is not great, will be greater than or equal to. In this case, it will be equal to, and then we return. So again, we are returning. So we have these two elements, 1 and 1. That means not 1 and 1 element, but there is only a single element in both these arrays, right? Why I'm saying that in these two arrays, we will check when we talk about merge. Okay, we'll see how that is implemented. Okay, so now these two function calls are done, and then we deal with merge. Now before going into the merge, let me show you a demonstration of how things look. So you have these elements, and here you have how many elements? You have 5 elements, right? And now you're dividing it into 3 and 2. Now this is your first step. The second step will be this. So now will you go ahead and create this as your third step? That means you will move on to this? No, because we saw unless and until left is not, there is no left, right? We will not go to the right. So this is your second step. Then this will be your third step. This will be your fourth step. Now you will move on to your fifth step, right? And now once you don't have anything on the left, nothing on the right, then what happens? Will this be your sixth step? No, your sixth step will be merge. So let's move on to merge now. So in the merge function, if you see, the algorithm for that is simple, that you create two sub-arrays, that is, the one is your left array and another is your right sub-array. Now in this, you have obviously in the last case, if you have seen, we have a single element here and a single element here. Now once we have deduced out the length of these arrays, what should be the length of these sub-arrays, and we have declared the length or declared these arrays, and then we have initialized these arrays. Once these 3 steps are done, then what we are going to do, we are going to create 3 iterators, I, J and K, and those iterators deal with, I iterator will deal with the left array, J iterator deal with right array, and K with the original array, which helps us to insert the elements. So once we have everything in place, what we are going to do, the next step is comparing the values, right? If this element, that is the element in left array, is less than the element in the right array, we are going to insert that in the original array. So now let's suppose you have 10 here and 23 here. So 10 is less than, so we are going to insert this, and we increment the K pointer. And now also our I pointer will be incremented. It was earlier, it was 0, and it will go to 1, right? And now what happens? Now our I is pointing to 1 and our length is also 1. So now that in that case, when one of the array is exhausted, the next array, whichever is left, right? It can be either the left array or the right array. Those elements will be directly inserted in the original array, because we know for the fact that both of these left as well as right arrays will be sorted in itself. Okay, so let's see what is the next step in the demonstration. So here we had our steps, right? And this will be the 6th step wherein we are going to merge this thing. Now, will this be your 7th step? No, your 7th step will not be this. Your 7th step will be here. This will be your 7th step. Now 6th step is done. Now you will be dividing it and you will be creating all those arrays. Now once you have your right array, and there is no right because this left is already done, and now you had your right left. Now this is also done. Now your 8th step will be this, that you will be merging it. This will be your 8th step. Then you will be merging it. Now will this be your 9th step? No, you have your this array, that is your left array, in place. But what about the right array? Is this in place? No, it is not. So now let's try to calculate that. Now what will be your 9th step? This left is done. This is your 9th step. Then what will be your 10th step? This is your 10th step. Well, now there is no left, right? Now we'll move on to this right. So this is your 11th step, because this is the right side of it, right? And now when you don't have anything on the right, now you will be merging these 2 steps, and this will be your 12th step, which is over here. So this is your 12th step. That means you will be merging these 2, and the final sorted array is this array, and you will get this array in the 12th step. So you see 10, 11, 16, 20, and 30. Now if you observe carefully, you have these individual arrays 1 and 1. So now while you are merging them, you are also sorting them. So the left array is sorted, and same thing happens on the right hand side as well. If you see 3 and 4, these two elements are sorted in this left array. So this is the reason in the right array, right? Not the left array. So now when you are merging them, you will get again an array which is sorted in itself. You see 10, 16, and 23. So if one of the array is exhausted, the next array elements can be directly inserted in your original array. Let me erase this, and you see you have your left array which is sorted, and then you are merging it with the right array which is also sorted. Now if one of the arrays is exhausted, the next array, either it can be left array or the right array, the elements from that array can be directly inserted in the original array, because we know the elements itself in either of the arrays, either the left or the right, are sorted. Okay, so this is how you execute your merge function.
Now let's see the implementation of merge sort algorithm. But before we go to the IDE and start typing the code, let me tell you what is the logic behind this merge sort algorithm and how it works. To understand that, let's see how this sorting algorithm is implemented. What's the logic behind that first? So let's suppose there is this set of numbers which you have to sort it out. Suppose 2 and then 8 and then 6 and then 4, 3 and maybe 5. So these are numbers. Okay. So merge sort logic says that as it works on a divide and conquer approach. So divide and conquer is nothing but you to divide the given problem into subproblems, then further into subproblems, and then combine the solution of those subproblems to find the overall solution. That's how divide and conquer works. So similarly, merge sort also follows that same procedure. So what we'll do is to sort the complete array, merge sort divides the array into two halves. Okay, so this is your start and this is your end. So we'll find out the middle element of the complete thing. So middle element is suppose 6. Okay, so 1, 2, 3, 4, 5, 6. 6 by 2 is 3. So the third one. So 0, 1, 2, and 3. Maybe 4. Okay, let's take that. Okay, so this 3 will belong to one, sub array, and the other 3, 4, 3, and 5 will belong to other sub array. Okay. Next, what will happen? It will again divide this into two halves, this also into two halves. Suppose this is divided into two halves and this becomes 2 and 8, and this is one element only, that is 6. This is further divided into two halves, that is your 4 and 3, and this is divided as 5. Okay, this will be further divided into 2 and 8. This cannot be further divided because there's only one element now. There's no need of further dividing it. This will be further divided again, 4 and 3. This will remain same, 5, because there is only one element. So this is, you see, a recursive call over the same array to divide it into two halves. Now, as no more further division can happen, there is only single element in all. What has to be done is that we have to sort the individual arrays now. So this is one array, this is another, this is this, this is this, this is. Now these are individual arrays. So these are anyway in sorted order. There's no order. There's only one element. So what can be the order, right? So no need to sort that further. So we'll combine these two. So 2 and 8 combining together, this is in sorted order itself, so it will be 2 and 8. 6 will remain as it is because there's nothing to combine. 4 and 3 will be combined together because these are individually in a sorted order. So once you combine, this will be 3 and 4. Right? This will be 3 and 4. So this will be now 3 and 4. This is 5 alone. Now 3, 4, 5 will also be combined, but it should be combined in a sorted order. So it will be now 3, 4, and 5. 3, 4, and 5, and the other this side array will be 2 and 8 combined with 6, so it will be 2, 6, and 8. 2, 6, and 8. While combining it, we should combine in such a way that the resultant solution is in sorted order, because that's the whole point of dividing it, right? Now, how to now combine in such a way that the final result is always in a sorted order? Like I combined here 2, 8 as one array and this array. Okay, this one and this one is combined together and we obtain 2, 6, and 8, which is a sorted array. So how that happened? Like what's the logic there? So there is also one logic which I'll tell you now itself, so that when we write code, it's easy for you to understand. let's assume that these are the two arrays. Now this has to be also combined and the resultant will be in sorted order. Let's combine these two. So you will understand the smaller parts also. This two I am taking as an example. So let this be the left array L1 and let this be R1, right array. Okay. Or you can, this actually this is the left one and this is the right one, but doesn't matter. Take any one. Okay. Let take I as to point to the indexes and j here to point to the indexes. So logic says is that you have to have one empty array, okay, uh, maybe k, or you can use k to point to the indexes, and this array can you can call it as anyway maybe resultant array. Okay, so you'll need to have one empty array also. What logic should, and this the size of this array should be combination of the sizes of these two, because ultimately the elements of both of these array left and right is going to be in this array, right? So the size of this array will be 3 plus 3, that is 6. Okay, so 1, 2, 3, 4, 5 and 6. Fine. Now what logic you have to implement is that first I will be pointing to the first element, j will be pointing to the first element, k will be pointing to the 0th element index here. So now you have to compare I and j. Which one is smaller? J is smaller. So whichever is the smaller will be stored in the resultant array and that pointer will be incremented. Okay. Nothing you have to do with the other array. Only that which is smaller will be stored here and that will be incremented. Now we'll compare 6 and 3. So 3 and 6, which is smaller? 3 is smaller. So 3 will be written here. And every time k also has to be incremented, guys. So 3 will be stored here and I will be incremented this time because we stored from left array. Nothing to do with the j. Now I is at 4 and j is at 6. So compare 4 and 6. Which is smaller? 4 is smaller. So 4 will be stored over here. Okay. And as 4 is stored from the left side array, I will be incremented to this. Getting it? Now I and j will be compared 5 and 6, which is smaller? 5 is smaller. So 5 will be stored over here and k will be incremented to next. And now I reach to the end, right? I reach to the end. So no more comparison has to be done now. Once you reach to the end of any one of the array, no more comparison has to be done. So now what will be the next step? So one more condition is that if you reach to the end of any one of the array, comparison should not be done now. You should come out of that loop and check that is there more elements left in the other array. If there are more elements left in the other array, like for example in the right array there is more elements left, right? 8 is there still pending. So we'll store all these elements into, sorry, 6 and 8 both is pending as of now, right? So you'll store both of these elements into the whatever remaining elements are there, you'll directly store it into the resultant array without comparing them, right? So when you reach to the end of one of the array, in the other array whatever elements are remaining, that will be directly copied to the resultant array, because this will automatically be in the sorted order, right? So you'll copy it directly to the resultant array. So this is the logic of merging the two sub arrays so that the resultant array obtained is always in sorted order. Getting it? Similarly, 2 and 8 as one array and this 6 as one different array. This is will be L1, this will be R1, and the same logic which I implemented for these two arrays will be implemented here, and these two will be combined to obtain 2, 6 and 8 as a resultant sorted array. Okay, so this is your complete logic behind no merge sort. Now let's go and write down the code for the exactly same thing which I told you right now. First thing is you have to do the recursive call to the divide part. Like merge sort you have to call again and again, and then there will be one merge function which will require these three arrays, and we'll using this logic we'll merge them. So let's go to the IDE and write down the code. So here I am. I've created a class already, sort, and then there's a main method also inside this. Now let's write the code for merge sort. So first I'll write the function void merge sort. Okay, this will take three parameters. One will be your array, the array which had to be sorted, and then the start and end of the array. Okay, so whatever is the start value and the end value. In this, what you have to do is you have to do recursively call the divide part, right? So recursively merge sort you have to call on the complete array again and again until unless you're left with single array. Or how to check that single array? Until unless start and end starts pointing to the same value or same element. that means that there is only one element left, right? So that's what we'll do. So we'll check or we'll run this loop only if the start is less than end. It should not be equal, right? If the start is always less than end, till then you recursively call it. Once it becomes same or equal, then it will automatically stop, right? It will come out of this loop because the check is start should be less than end. First step is you have to find the middle value because partition has to be done from the middle element. So mid will be always first plus last, divide by 2. Let's put this in bracket. Okay. Now we have to recursively call it again. Okay. Let it be start and end. Sorry guys. Start and end itself. Okay. Now we have to recursively call the merge sort two times, right? Because one for the one half and the left side and the right half. So merge sort will be called on A1 and start and mid till mid only, right? Because first half is till mid. And then again merge sort will be called for A1 and it will be this time mid plus 1 until end, right? Now you have to merge. This is for dividing it. Finally, you have to merge also. So for merge also you have to call, let's create one function called as maybe merge. We'll write the function, implementation later on. I'm calling it right now. So you have to merge what? Left array and right array. So A1 and then while merging we need the array and then the start, mid and end, all three is required. Okay, yeah, mid and end. And so we'll call this, right? So this is your actual merge sort function. Now let's write the merge function also, guys. So it is going to be void, let's have static void merge, and in this it will take array as a first input, then int start, int mid, and int end. Okay. As I said, we need I, j, and k, three different variables to point to the indexes of the three different array, left array, right array, and the resultant array. So let's right now itself, as we know we are going to use these variables, let's define them also, declare them also. Now, what will be the size of the left array and the right array? Let's define that. So L size will be mid minus start plus 1, isn't it? And similarly, the size for right array will be our size will be equal to end minus mid. Let's define these, no, the two left and the right arrays. Okay, and define them, and then we'll populate the values also, which should be on the left array and which should be on the right array, and then we'll implement the logic of merge. Okay, let's quickly do that. So int L1 equal to new int, what will be the size of it? End minus mid, right? Similarly, int R1 equals to new int, what will be the size of this? End minus mid. Fine. Why is it giving error? Second. Okay, equal to sign is missing. Okay, fine. So we declared these two array left and right. Now we'll populate the data into it as well, right? So let's do that. So for loop will be used for inserting data. So I is equal to 0. I should be less than, okay, I should be less than what here? L size. And then I plus plus, definitely. And in this we'll populate the value of L size. So L1. L1 of I is equal to A1 of A1 will start from start plus I, right? Similarly, we'll do it for the right array also. So J equals to 0. j will be less than r size and j plus plus. In this, R1 will be populated with A1, A1 mid plus 1, and then also J. Because J starting from J, right? So obviously you have to do that. So mid plus 1 till the end, and that will start from start to the mid, like that is the L size, whatever. Getting it? So this is what we populated data into both the left and the right array. Now comes your the actual implementation part. Let's initialize this I and j again, guys, because we have changed its value. Maybe we can get error later on. So let's reinitialize all just to be on the safer side. Okay, this will not be 0. This has to be start. Although start is going to be 0 initially, so but let's reinitialize it for the safer side. Now what you do is compare that in both of these arrays, whichever is the smaller should go into the resultant array, right? So while loop, while I is less than L size, okay, and j is less than also the R size. It should not be that we go out of the complete loop. In this we'll write if else conditional comparison, that is L1 of I should be less than or equal to R1 of j. If no left hand side array is value is less than the right hand side, then we have to do what? Store the left hand side value into the resultant array. So this will be A1 of k, okay, is equal to L1 of I, and then increment I, right? Otherwise, else, I'll copy paste this. It will be R here, R1 of j, right? And this will increment j this time. Otherwise, j right hand side array will be value will be greater. So we have to store that into the resultant array and we have to increment j. That's what was the logic, right? So we'll do that. And also finally, you have to always do k plus plus. This will complete this loop. Now, coming out of this, as I said, if we reach to the end of any one array, the remaining elements of the other array should be directly populated to the resultant array. So that's what I'm going to do here. Let's compare that if if I is less than L size, okay, then A1 of k should be equal to L1 of I, right? And then also I plus plus and also k plus plus. Right? Similarly, we'll do for j also. So j is less than our size. Then in that case, I'll copy paste this from here itself, as it is the same thing. Ai of k will be equal to R1 of j, and this will increment j this time and then k also this time. Okay. I think that is the conditional checks. Now, what's the error showing? Let's see once. Okay, to miss this here. Now let's call this functions over here. So for that, I'm going to define an array A1, which is equal to new int. Let's insert the values 3, 5, 1, 7, 4, 9. Okay. And then call a merge sort for this array A1. And also we should pass the parameters beginning and end, right? Start and end. So we'll pass 0 as a start and end may be the length, A1 dot length, but -1. Be careful with this part because length gives the total value, but gets merge sort. I think the spelling is correct. merge merge sort. Yeah. Is it static? No, right. So that was the issue. Static. Okay, now it won't mind. So yeah, that's the thing. Let's see it works fine or not. Okay, no, there is index out of mount. Okay, let us see here what happened. Okay, so this is L1, this is our size, n minus mid. Okay, both see the size is same as we defined, which should not be the case. This is left array, so it should go till mid plus 1. Okay, now let's see. Okay, nothing to this. Okay, sorry, we have not written the code to display, guys. So let's write a for loop. So for int I is equal to 0, I less than a1 dot length, and then I plus plus. Okay, and then we have to just display it. That is a1 of I. I will again do this here. Okay, let's see now. So yeah, you can see 1, 3, 4, 5, 7, and 9. So it was that easy, guys. You just have to understand the logic behind it. And this is how the merge sort implementation is done in Java programming. We have to recursively call the merge sort to divide it further. And then once the division is done, lastly merge is called to merge the divided arrays, no, divided set of data. And merge has certain logic behind it, where there is left array, right array, and there is resultant array. Many times a different resultant array is taken. Many times you can take the same A1, no, same array like how we have taken here to store the resultant one as well. Uh, because anyway, we have populated all the data from A1 to left and right arrays. So A1 can be overwritten, doesn't matter, right? So that's there. Or you can use a third array also to store as a resultant array where the final value will be stored and you can display that. Any logic is fine. So that's the logic. Whichever is the smallest in the left and the right array, that has to be populated to the resultant array, and that pointer has to be incremented to the next element. And if one array you reach to the end of the elements or end of the array, then the other array elements which are remaining should be directly populated to the final array, and that will be your then sorted array as a resultant. So this is how merge sort works, and this is the merge sort implementation in Java. Now let's see what is greedy approach to programming or for any given problem. When we implement it using greedy approach, what exactly it means. So as the name again clarifies most of its definition and most of the meaning. So greedy approach to programming is that way of programming where the first solution to any given problem is taken up as the final solution. Meaning that suppose there's a given problem and you found out a solution for one half or suppose half of that problem. You will find that, okay, fine, this is only the correct solution, and you'll go to the remaining part of the problem. And whatever is that the solution, you'll combine, and that is your final solution. Meaning what? That you won't, you know, explore all the possible solutions first, and then find out one best one, right? That's not the approach in greedy. The approach in greedy algorithm, or greedy approach to programming, is that you will first find a solution. Whichever is the solution you encountered first, that is the final solution. Irrespective of, looking forward and then finding out that, okay, there are, multiple solutions to this problem. This can be better than that. Better in terms of space and time complexity in computer science language, if we talk. One example I'll give you. For example, suppose you know someone has to travel from Bangalore to Delhi, to Hyderabad to Mumbai. Okay, these are the four cities, and someone is to travel from Bangalore to Mumbai, suppose. One solution can be that you go to Bangalore to Mumbai directly, or if the constraint is suppose that you have to traverse any one of the city. So what can be the solution? That from Bangalore to go to Mumbai, either you can go to Hyderabad and then go to Mumbai, or you can go from Bangalore to Delhi and then go to Mumbai. Suppose the very first solution we figured out is that Bangalore to Delhi we can go, and yeah, from Delhi also there is a route to Mumbai. So yeah, from Delhi also we can go to Mumbai. So this is the route Bangalore to Delhi, Delhi to Mumbai, and that is your solution if you are following a greedy approach to programming, right? But you can see here clearly that if we go from Bangalore to Hyderabad and then to Mumbai, we'll save a lot of time because Hyderabad is somewhat near to Mumbai and also to Bangalore, right? But that is not into consideration. The solution which was encountered, like if there is any one feasible solution that is possible, that becomes the final solution of the problem. So that's what greedy approach in nutshell is all about. Okay, it works in a step by step fashion, finding the best solution locally. The example which I gave right now to you. So from Bangalore to go to Mumbai using any one location, the first place it encountered was Hyderabad. So it looked okay, we can go from Bangalore to Hyderabad, no issues. Fine, that became the solution. Now from Hyderabad to go to Mumbai, okay, we can go from Hyderabad directly to Mumbai. Fine, Hyderabad to Mumbai. So this is the route. Okay, from Bangalore to Hyderabad, Hyderabad to Mumbai. So it finds the best solution locally, but that solution may not be the best solution globally. Okay, best in the terms of, again I'll say, time and space complexity. So that's what your greedy approach is. Now, benefit of using greedy approach is that it gives the best solution locally, for sure. Okay, may or may not be the best solution globally, but yeah, locally it gives the best solution. A lot of applications are there for greedy approach to programming. That is Prim's spanning tree algorithm. So how to find out or create multiple spanning trees from a given graph. There are no two approach basically, Prims and Kruskal's. So Prims is one of the approach of finding the spanning tree from a given graph. So we'll see now next what is spanning tree, and what is Prim's approach to finding spanning tree, and how this algorithm, works on or functions on the concept of greedy approach to programming. Then there are many others like traveling salesman problem. So traveling salesman problem is somewhat similar to what example right now I gave you. So similarly, there are many other approach, and even when we encounter a new problem, we try to solve it using this greedy approach as well. So that's about your basic concept behind a greedy approach to programming. Now let's go ahead and see the application of it. Now let's see what is Prim's minimum spanning tree. That is Prim's minimal spanning tree algorithm. Okay. So before that, what is the tree first of all? So this concept of minimal, no, Prim's minimal spanning tree algorithm is about finding a tree out of a given graph. Okay, so the initially the concept of all these was into mathematics and mathematical computation and all, but this concept of graph or a tree is being used in computer science as well. So what is tree first of all? So tree is you can say a collection or a combination of edges and vertices. Okay, now, what is spanning tree? Now, as I said, tree is a combination of edges and vertices. Okay, but tree doesn't have a cycle in it, right? Graph may have cycle into it, but tree will never have a cycle or a closed loop there, right? Meaning, if you start from a given vertex, you should not reach back to that same vertex following any given path. Okay, so there is no closed loop in tree. Now, what is spanning tree? So spanning tree is constructed out of a given graph which spans the complete graph, meaning the number of vertices in the graph is same as in the spanning tree as well. Okay, number of edges will be one less than the number of vertices in the graph. So this is the criteria or a condition for a spanning tree. Now, what is minimal spanning tree? Minimal spanning tree is that which has the minimum cumulative weight, or you can say that it has a minimum cost to traverse from one vertex to the other vertex, right? In a graph there can be multiple paths for to go from one vertex to the other, right? But when you construct a minimal spanning tree, to go from one vertex to the other following the alternate sequence of vertices and edges, there will be only one path, and that will be your minimal path. That is, it will have minimum cost if you do the summation of the weights assigned to those edges, and that is your minimal spanning tree. Okay, a spanning tree has all vertices connected and it is constructed from any given graph. Any given graph at any point of time can have multiple spanning tree out of it. Right, there can be, if I talk just about spanning tree, then any given graph can have multiple spanning trees. For example, if I see, no, take this example itself, the graph over here, A, B, C, D, E, F. So 1, 2, 3, 4, 5, 6. So 6 vertices are there and multiple edges are there. I'm not talking about minimal spanning tree right now. I'm talking about spanning tree. Let's see how, I'll draw two spanning trees as of now and show you how it is done. So these are the vertices A, B, then C, then D, and then E, and then there is F also, right? Now, to go from A to B, there is one path. To go from A to C, there is one path. To go from, F to A also, there is a path. Then we can go from F to E, that is 9. Then we can go from here to here, that is 2. So done. 1, 2, 3, 4, 5, 6. All the vertices are connected here by at least one edge, right? So this is one spanning tree. Now in this, number of vertices are same as the number of vertices in the graph, and number of edges are one less than the total number of vertices. So total number of vertices are 6 here. So number of edges should be 5. So we can count 1, 2, 3, 4, 5. So this is a spanning tree according to the definition of a spanning tree, right? One more no spanning tree I can draw and show you here. So I'll take all the vertices. Okay, I'm not using any algorithm to draw or anything. I'm directly drawing spanning trees. So there is a path to go from B to C, okay? Then from C to D also. Then there is a path to go from C to E as well, 1. Then A to C as well, that is 6. And F to E as well, that is 9. So you can see then this also, the definition of spanning tree holds true. That is, number of vertices is same as the number of vertices in this graph. And number of edges is 1 less than the total number of vertices. That is 1, 2, 3, 4, 5, 6 minus 1, that is 5. So 1, 2, 3, 4, 5 edges. Right? So you can see right now itself I draw two spanning trees for a given graph. So there can be multiple spanning trees for a given graph. Now how many spanning trees for a given graph is a question of, again, mathematical derivation, and there's a formula to it as well. But that's not our concern here. Our point is how, to find out minimal spanning tree using Prim's algorithm, and how does this algorithm falls under the approach of greedy programming, right? So as I said, it finds the best solution locally, right? It doesn't seize the greedy approach, doesn't seize the best fit or best feasible solution overall. And that's what is the idea behind Prim's minimal spanning tree also. But before that, what is minimal spanning tree? As I said, the complete weight of the spanning tree should be minimal. That is, to traverse from a given vertex to any other vertex should be, the cost should be minimal. Now, how will you know the cost? You can see these weights assigned to each edge, a value assigned to each edge. These are nothing but weights, okay? So when you do the summation of these weights, it should come, the overall weight should come the minimal. Like for the spanning tree, if I name it as S1 and this is spanning tree S2. So for S1, what is the weight of the edges if I count together? 6 plus 4, 10, plus 5, 15, plus 9, 24, plus 2, 26. So 26 is the total weight for this, right? Let's count for this. 6 plus 3, 9, plus 8, 17, plus 1, 18, plus 9, 27, right? So you can see 27 is the weight coming here. So 26 is minimum to 27. So in these two, this is the better one. But there can be some other spanning tree which is having even weight smaller than this. So that spanning tree which is having the minimal cost, the lowest, total cost of the edges, total sum of the weights of the edges, that is your minimal spanning tree. Okay. Now there are two algorithms to find this, Prim's and Kruskal's in mathematics. But here we are going to see Prim's minimal spanning tree, because Prim's minimal spanning tree algorithm actually follows the concept of greedy approach or greedy programming, right? Now first, let's see, how to find out how to apply this minimal Prim's minimal spanning tree algorithm, like how to find out the minimal spanning tree using Prim's algorithm, and then we'll go to the logic and implementation of it in Java programming. Now let's see the implementation of Prim's minimal spanning tree algorithm. So before going to the coding or the method, code or function, how it looks in Java programming, let us try to understand, how this minimal spanning tree is constructed, that too following the Prim's approach. So there are two approaches to construct minimal spanning tree. One is your Prim's approach and the other one is called Kruskal's approach. Okay. Somewhat the time complexity is same for both of them. Sorry, the space complexity is same, but the time complexity differs. But okay, fine. Let's see the Prim's approach here, because this is what is going to follow the greedy approach to programming. And our main intention is to understand how does Prim's minimal spanning tree construction follows greedy approach. So you can see here, this is a graph which is already created here. So it is having 1, 2, 3, 4, 5, 6. So 6 vertices are there. So number of vertices are 6. Okay. Number of edges are somewhat given over here, and if each edge is having some weight assigned to it, that is a cost factor basically. So each edge is having a cost assigned to it. Fine. Now what we have to do here is we have to construct a minimal spanning tree. So the rule for spanning tree is that number of vertices should be 6 itself. Number of edges in the spanning tree should be 1 less than the number of vertices, right? That is, it should be 5. And the total cost, sum of the cost, okay, I'll represent it. Sorry, I'll represent it later. Sum of the cost of the minimal spanning tree should be minimal. This is our criteria. Right now, we'll start the construction of Prim's minimal spanning tree starts from taking the very first vertex. Any vertex you can take as a source vertex. As in numbering A comes first, let me take A as the source vertex. Okay, so A will be the first vertex here, right? When we go to programming, okay, when we go to writing down the code for this, the input to the code will be always your two-dimensional matrix, okay, which represents the weight of the edges. That is, it will be numbered from A, B, C, D, E, and F. Okay, there will be 6 rows, and similarly there will be 6 columns, C, D, E, and F. Okay, so from A to A. So one more thing is there. See, there can be self loops. Okay, if there are at all self loop in a graph or parallel edges in a graph, we remove those edges. Okay, self loop meaning if suppose from starting from A, something is there which is pointing to A back again. So we'll remove this. This kind of thing should not be there. Or parallel edges meaning 2 edges between the same 2 vertices. Like one edge is there right now between A and F that has weight 5. If suppose one more edge is there between A and F, and that is having 3 or 2 as in weight. So these are parallel edges. So that those should be removed. Now in that, which one should be removed? So the edge which is having higher weight among the 2 parallel edges, that should be removed. Okay, so although in this graph there is nothing of that sort, so we'll not go into that. We don't have to remove actually that. So from A to A there will be no path, so 0. So all diagonal elements will be 0 first of all, because from B to B also there is no edge. From C to C also no edge. From D to D also no edge. From E to E also no edge. From F to F also no edge. Now from A to B, is there a edge? Yeah, there is an edge which is having weight 4. So this value will be 4. A to C, there is an edge which is having weight 6. So it will be 6. A to D, there is no direct edge from A to D, right? So it will be 0. A to E also direct edge is not there, so it will be 0. A to F, there is a direct edge which is having weight as 5. Getting it? From B to A there is an edge which is having weight as 4. B to B, nothing is there. B to C, there is a edge which is having weight as 3. So we'll put 3. B to D, there is no direct edge, so 0. B to E, B to E also direct edge is not there, so it will be 0. B to F, B to F, okay, again direct edge is not there, so it will be 0. From C there is an edge to A, so 6. From C there is an edge to B also, so 3. C to C there won't be any edge. From C to D there is an edge, 8. From C to E also there is an edge having value 1. C to A also there is an edge having value. Okay, A is done. C to F there is no direct edge here, so it will be 0. Okay, similarly for D and E and F we can fill here. So this will be the input for the given code or a program when you will write. Output will be one array which will be having uh, numbering for all the vertices, that is 6 vertices are there, so 6 entries will be there in this one dimensional array. So A, B, C, D, E, and F. It will be pointing with 0, 1, 2 itself, guys, because that's how indexes are pointed out in Java programming. And which is the minimum edge, outgoing edge from A, or minimum edge from A, which is selected in the spanning tree construction finally. that will be here. That is from A, suppose I select this edge 4, I mean which is going to B. So we'll select from A and the value of this will be 4. That is we have selected a edge to go from A which is having a weight as 4. Getting it? This will be your no, final output array. Now you can write a print statement which properly prints that okay, there is a path from A to B which is having a weight cost of 4. Okay, that is again how you uh, decorate your program, basically how you print the output. But final output will be of this array if only this coding is concerned. Okay, so what is this? Numberings will be there for the each vertex, and the value in this array will be the minimum edge which is selected from that particular vertex. Okay, in the final minimal spanning tree. Now let's come to construction back again. I told you the input and output of the code or the program. Now what will be the process? So first is that we have to select the vertex A. Now from A, which is the outgoing edge, which are the outgoing edges or which are the edges actually connected? 4, 6 and 5. These are the three edges, right? So in 4, 6 and 5, which is the minimum one? 4 is the minimum value. So we'll select this edge from here to here, which is having 4 as a value, which is going to vertex B. Right, guys, we also have to keep a track of which all vertices are visited, right? We should not go back to the same vertex again. So to keep track also, we need one dimensional array which will have uh, true and false, which is a boolean no array, which will have values like initially all the values will be false because nothing is visited. Once you visit any node, that let's change the value for that particular index to be true, meaning that that particular vertex is visited. So if A is visited, A will be marked as true. If B is visited, B will be marked as true, and so on. Okay. So now next is that from B, which are the minimum edges? 3. And we have to also take into account the previous edges also. We should not forget that because maybe that, some other minimum edge is there to go from some other vertex to the next vertex. So we have to compare this time that from B, 4 is already visited. This edge is visited, so no need to check this one. From B, there is 3, and the earlier edges from A was 5 and 6. Correct? So among 5, 6 and 3, which is the minimum? 3 is the minimum. So we'll select 3. So we'll draw the C here and we'll select this 3 here. So now C is also visited. So mark this as true. Okay. So now from A to go next, we got 4. From B, we got the element to be 3. Okay. From C now, let's see. So from C, there are 6, 1, 8. So these are the three edges. Okay. And also there is the other two previous one, that is 9. Sorry, that is 5 and 6. Okay. So 5, 6, 1, 8. Among these four, which is the minimum? 1 is the minimum. So we'll select 1. Let me draw it once again here for you. So A, B, this is 4, and then C, which is 3. And then next we'll take E, which is 1. So we'll go to E, which is having weight as 1. Okay. So to go from C, we got 1, and E is also now visited. Fine. Now from E again we'll see this is the edge, this is the edge, and all the previous edges also which were not covered. Fine. So 9, 2, 5, 6, 8. Correct? Are the edges. So among all these, 2 is the minimum. So to go from E to D, we will select 2. So to go from E, we selected 2. Okay. And now D is also visited. So now F is left, right? And we were checking that 5, 9, then 8, then 6 are the edges left. So among all these, which is the minimum one, right? So basically to go on F, we have only these two rows, right? I mean, these two edges, either 5 or 9, right? So in 5 or 9 only we can check because others edges are not going to F, and our point is only to traverse F because that is the only edge vertex left. So to go to F, we have 5 as this minimum one. So we'll draw F over here, and from A to F, 5 is the minimum. Okay. The other numbers, if you could see here, like 6, 8, 6, 8, and 9. Although if you compare also 6, 8, 9, and 5, 5 will be the minimum one. Okay, so 5 is the next minimum value. So 5 is taken to go to F. So from F, 5 is the weight, and F is also visited. Now, what will be the final sum? The minimum value will be summation of this particular array. That is 5 plus 2 plus 1 plus 3 plus 4. So 5, 4, 9, 1, 10, 13, 15. So 15 is the total weight or cost for construction of this or for traversal of this minimal spanning tree. Okay, so this is how it is constructed. So I think you've got this idea for implementation also. Like for implementation also, I told you this will be your input, this will be your, output. The output will be this particular thing. You can print it in whatever way you want. That is a different issue again. And then internally we need this particular array to keep track of which nodes are visited, which are not. And we also need this particular array, which will keep track of the minimum weight selected from that particular vertex. Okay. And from this, two-dimensional array or matrix, what we have to do is, suppose we are traversing vertex A. So we'll refer this particular row only. Okay. In this, whichever is the minimum one, that will be selected. And also checking that that particular vertex is not visited till now. Then if you're talking about vertex B, then this particular row will be selected from this and will be given to a function, and that will select the minimum value for this, except these zeros. Now, one more thing, to represent zeros when it comes to programming, we use infinite number, some large number. Okay, because if you represent zero, always zero will be the minimum one, right? So in that case, you can't do the comparisons properly. So in this case, we will convert this matrix where wherever there is zero, you have to put some higher number. Now let that higher number be maybe, triple nine or four nines or some higher value, which doesn't comes into count when these weights are considered or this cost is considered. Like if I take some 9999, some this value, this is a very high number already. Obviously, this cost is going to be lesser than this. If at all it is not less than this, then you make sure you take a very larger value, higher value to represent these zeros. Okay, that's what called as also infinite number. So you have to take some infinite number. So infinite logic is that some larger number which is very higher than the cost of uh, each edges here in this tree or a graph. Okay, so that's it. Now let me go to the main function of Prim's algorithm. Okay, where I'll just tell you exact same thing, the logic which I explained you right now, how you can convert it to a code in Java programming. So I have written it here itself. That is, this is the main function. Okay, Prim spanning tree. These are some variables which I'm using it here so that I've initialized declared it over here. These all are integer variables. You can do this part later also once you figure out that what all variables you require to run the code. So you remember I told you that you need one-dimensional array which will keep track of which vertex is visited, which vertex is not. And that is this particular array visited. So this visited array is of Boolean type. Okay. It will have that many, the size of the visited array will be equal to the number of nodes. So let n nodes be defined somewhere in the main function of your code. Okay. Okay. Suppose n nodes is 6. Let this be 6 also from 0, 1, 2, 3, 4, and 5. Right. So this is declared initially. Now, again, min edge. So there was one more, if you remember, one more array just now I told you, which will have all the minimum edges, the weight of the minimum edges which were selected from that particular vertex. Okay, so basically this is representing A, B, C, D, E, and F. Okay, so this is one array. Now, what we have to do is when we visit the first vertex, that is your zeroth vertex is what is being represented here. A or zeroth is the same thing. Okay. So when we visit the zeroth vertex, that will be marked here as visited, meaning it will be marked here as true. Okay. So that's what has to be done. The first thing. So visited 0 will be marked as true. Next, for all the values in this visited array, we have to initially mark it as false. Starting from 1, 0th is already marked as true because that will be the first source vertex which will be visited. So that will be marked true. But remaining all, starting from 1 till the number of nodes, we have to mark all that as false initially. Okay. And min edge for 0, will be also 0. Okay, when the weight of the edge to visit that particular vertex was 0, because there is no incoming edge right now initially to 0 to A, right? So initially it will be marked as 0. After that, what is the logic? So this is all initialization part done. Now let's come to the actual comparison and finding out the minimum edge and then updating these two one-dimensional arrays. So this was our status as of now. Visited 0, 1, 2, 3, 4, and 5. And then there was what? Min edge, which was again having 6 entries, because I've assumed that, you know, 6 vertices are there. And this is marked 0, this is marked true, and all these are marked false initially. This was our status. Now, what you have to do is that starting from the first vertex to all the other to the last vertex till n number of nodes. So you have to start from here till last. What has to be done? So this xy is basically nothing but it's going to refer like coordinates, like from vertex x to vertex y. What is the edge? So how will you represent edge in any programming? This is how we represent, right? Coordinate system. So vertex x is the starting vertex, y is the ending vertex. So the edge between x and y is being considered here, right? If we have to consider just vertex, we use just x or just y, correct? But if I use in as a pair, then it means we are talking about edge between x and y. So that's what xy is being used. So initially it will be 0, and we have to start. So as it is a two-dimensional matrix, right? So we have to start from 0, both of these I and j, and we'll go till the last vertex, till the end of the array. Okay. And in this, what you have to check, this is the important part of the complete algorithm. That is, you have to check that the visited of I is true, meaning the vertex which we are considering right now, suppose A we are considering right now, so A should be already visited. So the value of visited I should be true. Okay, and visited of J, that is the next vertex whichever we are going to consider, that should not be visited as of now. Then only we have to visit, right? If it is already visited, then what's the whole point? So starting vertex should be visited, but the next vertex which we are planning to visit should not be visited. So that's what the logic is. So visited I, meaning the starting vertex should be visited, but not of visited j, meaning the visited j, that is the next vertex where we are going to visit, should be false. Not of visited j, meaning this should be false. Okay, so in that case, what you have to do, and so this is an and operator which will make sure that all these conditions are true, then only the code is executed. And then also you have to check that cost of I of j is less than cost of x and y. X and y right now is pointing to the minimum cost. Okay, so you have to check here that if the cost which you are considering, like for example, this was the graph, right? Suppose this is the graph for 2. So if this is edge being considered A to B, if this is minimum or less than the initial cost of xy, every time initialized with the first weight, like right now, suppose the minimum was 2. So x and y will be pointing to 2. Next, when you will search for the next minimum node, you have to iterate over all the edges and find out which one is minimum. Getting it? And whichever is the first edge, that will be initialized with xy. Because that's the whole logic. You have to traverse each edge and find out which edge is the minimum one. Just that the vertex is not visited. Correct? So this is what the logic is. So cost of ij is less than the cost of xy. Then your next, xy is pointing to ij, because ij was a minimum till now. And again, we'll go to the next edge and see and compare the same thing. So every time you understood, x and y is pointing to the minimum edge. Clear? So this is the main part of the complete algorithm. So once this is done and we come out of this loop, x and y will be pointing to the minimum edge among all the edges. Okay, let's go to the other half of the code now. So as we got x and y as a minimum edge, so you can print here that next selected edge is x and y and its cost is cost of xy. Okay, cost of xy is nothing but that input matrix. And then you have to make the minimum edge value to be x, and visited value you have to make it as true. So here the visited value will be marked as true if at all that vertex is visited, and this will contain that next vertex which has been visited from there. Or you can have the weight also, like from vertex A, the minimum weight which is considered is 2, suppose, so it will be 2. From 1, the minimum age considered is 3, so it will be 3. Or you can use the logic. This is just to keep track of, which all edges, which all vertices are finally considered in our complete spanning tree. Okay, so with this you can either calculate total weight, or you can keep track of also the vertices which are taken into consideration. So from vertex 1, suppose we have gone to vertex 3, or from vertex B we have gone to vertex D. So B, suppose this is pointing A, this is B, C, D, E and F. So suppose you have gone from B to D. Okay, so from B to D, so this will be D over here. So anything is fine out of these. Just the point of this vertex, this array, is that to keep track of which all vertices are finally considered in our spanning tree. Although all the vertices has to be considered, but also this will help you keep in track that from a given particular vertex, you're visiting to which vertex, like which edge is finally you have considered. So either you can store the weight itself to consider the edge, or you can store the next vertex value which has been traversed from a given vertex. Either of it is okay. So the code which I have explained you here, this is keeping track of the next visited vertex from any given vertex. Okay. So that's all about the implementation of Prim's minimal spanning tree. You can write down this code in Java programming. This code is in Java already. You can write it in any IDE or any file, and compile it and run it. Just that you have to write a main function after this, and in the main function you have to give this as an input. This will be your input, and you have to from the main method you have to call the function which I explained right now, that is Prim's spanning tree, and that will be your final implementation of Prim's minimal spanning tree in Java. Now let's see what is dynamic programming. Among the various approaches of programming, one of the approaches is your dynamic programming approach. Now, dynamic meaning at all the levels, at all in all the aspects, finding out the best possible solution for any given problem. Okay, so dynamic programming does what is that it finds the best and the most optimal solution to the given problem, right? Now, how does it finds that? So it doesn't works in, like, a step by step way. Like suppose a given problem can be broken down into some pieces, and then locally we can find the best solution and then combine together. No, dynamic programming does is it finds multiple solutions to a given problem, and then selects one, the most feasible, the most best solution, optimal solution out of the all possible solutions. Best in the terms of time and space complexity. Okay, in computer science, this is what the best defines actually, that is having the less time and less space complexity, right? So dynamic programming does that, right? So not just locally, but also globally, dynamic programming gives you the best solution. There are many algorithms which are already implemented on the concept of dynamic programming. Still, if we encounter any new problem, we try to solve it using this dynamic programming approach. Okay, so the thing to keep in mind whenever we go for dynamic programming approach for any given problem is that you have to evaluate the complete problem. Okay, find out the whatever feasible solutions are there for it, and then compare all and find out one best solution for that dynamic programming, I mean for that given problem statement. Okay, so I'll talk about the application also here to mention matrix chain multiplication. So matrix chain multiplication is one of the area or problem statement which is solved using the dynamic programming concept. Similarly, Tower of Hanoi. Okay, then even knapsack problem is solved using dynamic programming. Then so many are there, which are renowned problem statements which are solved using the concept of dynamic programming. So we'll see one of the application here, that is Tower of Hanoi. and also its implementation in Java programming. Now let's see what is this problem of Tower of Hanoi actually, and how is this using the concept of dynamic programming to solve this problem. Okay, so let me tell you what Tower of Hanoi is first of all. So you can say it's a puzzle, it's a mathematical quiz or a mathematical puzzle that involves the concepts of rods and disks. Okay, so in Tower of Hanoi, the puzzle, how it is structured is that there are three rods, okay, and there are n number of disks of different sizes. Now n number, let's take an example of three here over here and go ahead with this. That's the general value for n, but you can have more than n as well. I mean more value for n as well, like 4, 5, and so on. So there are three rods and there are three disks of different sizes. Now, the puzzle says that what you have to do. So let's try to understand in this way. So there are three rods. So let us represent this AB, tower A, tower B, and tower C. Okay, as the three rods. And there are three discs. As of now, I've taken N as three. So three discs is there of different sizes. Different sizes meaning one disc which is at the lower side will be the bigger disk, then the smallest after that, then the smaller after that. I mean the smallest one will be on the top, and then the next bigger will be after that, then the largest will be at the end. So this is how it will be arranged in any one of the rod or any one of the tower. Okay, now puzzle begins with this is the initial state for the puzzle. What is the final state or what output you have to, as gain or to solve this puzzle, is that you have to move all these three disks from tower A to any one of the tower, maybe let's see tower C, okay, by using maybe the tower B. Or if you, obviously you have to use tower B, without that it's not possible. So you have to shift all this disk from tower A to tower C, and it should be arranged in tower C in the same order how it is arranged in tower A. That is, the larger disk should be down, this disk should be over here, and this the smallest one should be over here. So the same arrangement should be copied to tower C. And you have to just make use of this particular tower, meaning you cannot remove a disk and keep it somewhere else on no surface. You have to remove the disk from here and keep it in either of the towers only. Okay, and so this is what you do, mix and match, and then finally the final state which you have to achieve out of this puzzle is that in the tower C you should have all the disks arranged in the same way. It can be tower B also, guys. You can shift all the disks from tower A to tower B by using the rod or a tower C. But okay, let's not confuse ourselves and stick to one particular frame. That is, we have to move or shift all these disks from tower A to tower C by using this tower B. Okay, but disk should be arranged in same way over here. Now this is the initial state, final state, you understood. There are some rules to be followed as well. One of the rule I said is you cannot remove the disk and keep it somewhere else. You have to make use of these towers only. Okay, then another rule is only one disk can be moved at a time. Otherwise it's very easy, right? You can shift or pull out all the three disks together from tower A, and together you can put it again the same way in tower C. Solved, right? But that's not how it should work. It should be, the rule is says that only one disk at a time can be moved from any one tower to the other, right? Meaning if you are moving the smaller one, the only smaller one can be moved, then next one you can move, then next one you can move. All together, neither two of the together also cannot be moved from one tower to the other or one rod to the other. That's the first rule. Second rule is that disk should not be arranged at any given time such that a larger disk is stacked over the smaller disk. That is, even though the final state which you have to achieve should be that its disks are arranged in the same way, like larger disk down and the smallest one above it. But not just the final output should be this, but also in the intermediate also, whenever you are stacking two disks, suppose, or three disks in some of the tower, then that two disk or three disk should also be in this order only. The largest one should be down, then smallest one above it. It should not be that the smallest one is down and the larger one you keep it above it. Like you can't do that, move this smaller one over here and then the larger one above this. That should not be there. This should not be the case. That's the second rule. Okay, so disk should not be arranged at any given time so that the larger disk is stacked over the smaller disk. Always it should be larger to smaller in order from bottom to top. Okay, so following these two rules, you have to shift all the disk from tower A to tower C. So this is the problem statement. Now, what should be the solution to this? To understand the solution, what you should do is, let's see again carefully what I'm doing here. Okay, this will also give you the logic to write the program or a code for this. So it's very important for you to understand and listen it carefully over here. So you can see here, largest one I have stacked down, then this and then this. This is tower A, this is tower B, and this is your tower C. Okay, now I have to move all the disk from tower A to tower C. What I'll do is, first I'll move the smaller one into tower C. Okay, so the smallest one, this will be moved to tower C. So I'll be moving the first disk from, so first disk is moved from tower A to C. Okay, from A to C. Smaller one is over here now. This is removed from here. Now after that, what happens is, what I'll do is, I'll move the next smaller, next larger one to tower B. So this one is moved to tower B. Okay, is removed from here and it's moved over here. So I have moved the second disk from tower A to tower B. Understood? Now what I'll do is, the larger one is there. Now all three are having one disk. What now next what I have to do is, from tower C, this is the smallest one, this is the disk one. So this will be moved to tower B now. This I can arrange because this is the second largest one and this is the smallest after that. So this can be arranged over here. Like larger and then smaller, this can be stacked in this order. So this one I will move from here to here. So what I did was, disk 1 is again moved back from tower C to tower B. Getting it? So now tower C is empty. Nothing is there in tower C. Right? I'll draw it again here. Nothing is there in tower C. And tower A is having only the larger disk one and tower B is having two disks. The second largest one and the smallest one. Now what I'll do is, I'll move the disk from tower A to tower C. This is the largest one. So I'll move the disk 3 from A to C. So from A to C, this is moved over here. The largest one is moved over here. Getting it? Now there is nothing in tower A. Now what I'll do is, I'll shift the smallest one over here to tower A. Okay, the smallest one. So the smallest one is again in tower A. So what I did is, disk 1 is shifted from tower B to tower A. Got it? Now this one, so this is shifted, so this is not there now. This one will be shifted from B to C now, because this is the largest one, this is the second largest one. So the second largest one can be stacked over here. So I have moved the second disk from tower B to tower C. Right? Now the smallest one was in tower A. So now tower A to C, the smallest one will be moved lastly. So from the smallest disk is moved from tower A to tower C. Got it? So you can see finally we have arranged all the disks. Now in tower A there is nothing in tower B also. And in tower C we have stacked the disk in the same order how it was initially arranged in tower A. Okay, so few shiftings were here and there, back and forth, and finally we got this arrangement. So if you see this trend over here, I'm telling you to analyze this trend because it will be easy to write a code for you. So it is nothing but what? Recursive call to shifting of disks, right? Okay. Now this, to understand this recursive call, we have to understand this pattern. So you can see here, the first movement of the disk was between A to C. Okay. Next movement was A to B. Then was C to B. So first three, if you see, there was a movement of disk between A and C rod. Next was the movement between A and B. Then was the movement between C to B. Then again was the movement between A to C. Then again there was movement from B to A, or you can say there is a shift of disk from between AB. If I say in a proper way, here the disk shifting was between AC, this between AB, and this one between CB. Again AC, AB, CB. Again AC, and then maybe so on. So there are only three disks, so it stopped over here. But this trend will continue if there are more number of disks. Getting it? So if you analyze this, so these three is again being repeated and then again being repeated. So three times you have to call the functions. Once to move the disk from A to C, next time to move the disk from A to B, or to move disk between AB. Okay, one time you have to call a function to shift the disk from between AC, next time between AB, and third time between CB. Then again it is repeated. See, again there is shift of disk between AC, between BA or AB, BC or CB, same thing, right? So we'll write a function. Okay, now while coming to the implementation part, we'll write a function to shift the disk from one rod to other, and three times that function will be called. Okay, and all the three times this function call is a recursive call. So it will keep on repeating until and unless there are no disk left, right, in tower A. So that's the whole idea or a logic behind the Tower of Hanoi problem. Now let's go to the implementation part of it. So now we'll see the implementation of Tower of Hanoi problem. So as a logic, I have explained you already. Now let's go to the Eclipse IDE directly and write down the code there. Okay. So I have opened the file over here. Okay. Already created a class Tower of Hanoi solution, and then there is a main method inside this. So we don't have to, separately maybe write any function or anything here. Directly we can come here and write down the logic behind the star of Hanoi, whatever is there. So as I already told you that we have to write or do a function called three times for three different shiftings of disk from one rod to other or one tower to other. Okay, that's what I'm going to write down the code also. So let's see how it starts. So first we will assign how many disks were there. So let n contain the number of disks. So n is equal to 3. You can program for n equals to any number, guys. I have taken 3 in the explanation part, so I'm taking 3 over here as well. Let's have a function uh, shift disk. Okay, so shift disk is going to shift disks between one to other. So what will be the input to these okay, let's first write down this function that will make more sense. So let's come out of the main method, and here I'm going to write public static void shift disk. Okay, so suppose shift disk is the name of the function or a method. This will take first how many number of disk is there. So n3, that should be the input to this method. Next is the towers. Okay, let me represent those towers with characters, right? Maybe A, B, and C, or tower A, tower B, tower C, anything is fine. So let's have character TA representing the first tower, then char tower B, and then char tower C. Okay, so this will be the input, the three towers and number of disks. That's what is the only requirement or use in the star of Hanoi, right? Now the condition check is that if n is equal to 1. Okay, in that case, if there is only one disk left, then what you have to do is that disk should, the last one, right, that should be shifted from A to C, and that is it. The last disk I'm talking about, the last disk left, then it will be shifted from A to C. So if n is equal to 1, then you have to call, or you have to just print that disk is shifted from A to C. So disk is shifted from tower A to maybe tower C, right? The last disk I'm talking about, only one which is left. So you just shift from A to C. Else what you have to do is, okay, what is giving error? Okay, yeah, there should be one more plus here. Fine. So else, what should be the condition that if it is not the last disk, then the intermediate operations has to be done. That is shifting, like A to C shifting is done. Okay. Now other intermediate shiftings were B to C and A to B. right? So let's do that and call the function for that. So you have to call shift disk, yeah, correct spelling. This is for n minus 1. If there's one less than the total number of disk, then in that case you have to shift from or call the recursive function from tower A, and the shifting will be to tower B using tower C, right? So this is one shift where you have to shift from, okay, this will be B. So you have to shift from A to B. So A to C is already done here. In this condition, it is checked. Then it is, you have to shift from A to B by using or making use of tower C that is there. Next, again, you have to, let's print also so that, we can understand that what exactly is happening. So here it is going to shift disk. Okay, let's print the number of disk, that is n, from the disk number, that is n, right? 1, 2, 3, which I was numbering there. So disk from tower A is shifted to tower B, right? After that, again shift disk will be called for the last operation, that was, again this will be for n minus 1. Last shift will be from tower B to tower C through tower A. Okay, so this will be the last call to this function, and then closing of if and else loop. Okay, so this should close over here. Yeah, this closes here, this closes over here, and this closes the overall function. Okay, so you can see, guys, there were three operations mainly, right? Shifting the disks from tower A to C, from A to B, and then again B to C. So these three combinations are only repeating again and again. If there are like n is 3, then it will repeat 2 times maybe, and if it is more, then it will repeat more times. But the overall process remains the same. Okay, the combinations of towers which are used for shifting the disk remains the same. So that's it about the complete program. Now let's call the function. Okay, so I'm going to call it here shift disk, and let n, that is 3, be the number of disk. Then next will be your tower A, or tower A. Then next is your character again, tower B. Then next is your tower C. Okay, and call to this function. Okay, it says, one second. Okay. Let's have one. It's a character, right? So we cannot have more than one characters here. It should be only one character. So that's it, the issue. So let's shift that from this to that. Now let's see what the output is. Is it the same which we, encountered? Okay, it says there is an error. Let's fix that. Okay. So you can see here, and let's match it if it comes the same. So first shift is from A to C, then okay, it's not writing disk number. One second, should be disk 1 is shifted from tower of A to tower of C. Disk, okay, let's give space over here. Okay. Just a second. Yeah. Okay, now it will make more sense. Let's see the output. So disk 1 is shifted from A to C. That was our first step. 2 is shifted from A to C. 1 is shifted from C to B, then 3 is shifted from A to B. No, this is not the output. It should be disk 1 is shifted from A to C, correct? Disk 2 is then shifted from A to B. It should not be A to C, right? Okay, then there is some mistake here. Let's try to fix it and figure it out. Okay, so what's the issue here is that let's check. So disk 1 is shifted from A to C. Okay, then again it is called for A to B through C. And at print disk N from is shifted to tar of B. Okay, no, this should be tar of C. Now let's see if it gives the correct output to us. Let's check. So disk 1 is shifted from A to C, 2 is shifted from A to B, correct? Then disk 1 is shifted from C to B, and 3 is shifted from A to C now. So 1 is shifted from, yeah, correct. So you can see here that the combination is A to C, A to B, and then C to B, right? And again repeated A to C, BA, B to C, then again A to C. So this is what I was talking about, right? Three combinations. The disks are moved in a certain way. So it is nothing but the implementation of tower of Hanoi is very simple, guys. You just have to do a recursive call over here for the method again and again, being very careful and analyzing this pattern. So as we analyze this pattern, there is movement of disk between AC, AB, and CB. Again, it repeats AC, BA, or AB, either of it, right? But there's a shift of disk from either of this only. Then BC and then AC, right? So this is what has to be done. You can see the recursive call to these functions has to be made for movement of different disks to different towers or different rods. So now this concept of Tower of Hanoi uses dynamic programming. So you can see here that it explores the best possible output or optimal solution out of the all possible solutions, and then it gives you the final result or conclusion. And that's what the logic behind dynamic programming is all about. So that's all in the implementation of Tower of Hanoi using dynamic programming. Now let's summarize the complete course. So in this complete course, we talked about the different types of data structures, what is data structure, and all those different types of data structures were, no, the basic concepts were discussed, and also their implementation in Java was talked about. So the different data structures like arrays, what are different methods to be performed using array, what is one-dimensional array, two-dimensional arrays, and then also its implementation in Java. Similarly, for stack, linked list, and queue, the operations which are performed on these data structures, how are these methods and operations implemented in Java programming was talked about. After that, the tree data structure, the two different variations in tree, that is binary tree and binary search tree, was discussed. Also, the traversal of these trees and creation of the tree using Java programming was talked about. Then we talked about graph data structure, how is, breadth first search and depth first search traversal is done. Moving forward, we did, understand how the searching and sorting algorithm works, how is algorithmic analysis of the complete code is done, as well as what are the different approach to programming, that is what is greedy approach, what is dynamic programming, what is divide and conquer approach was discussed all in detail, as well as with one of the application for each of these approaches was talked about, not just the logic behind it but also the implementation of those concepts in Java was talked about. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you don't miss out any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. As it said, knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I will definitely respond to your comments.